This is a light question for this morning, but can anybody remember what is the benefit of using STP over UTP? Wouldn't necessarily say more secure, but there is another. Well, it is technically because based off what it's protecting it from, yeah, it's like a security feature. So I give you that, Mr. T. Yeah, because it prevents this. Yeah. When you're too close together, what's that called? Two conversations overlap, crosstalk. Yeah. So yeah, I can kind of agree with Mr. T on that one. Prevents crosstalk, and what is the other one? There's one more. It's like when you rub your feet across a carpet. Yep. You're right, Jesus. EMI. Electromagnetic interference. Right? So that is the benefit of using that. These are the different flavors that we're seeing. 10 means 10 megabits per second. I'm pointing stuff out so if you get lost on the exam, you don't know what to pick. 100 simply means 100 megabits per second. 1,000, that's a gig. All right, so a quick reference. 10 Mbps, 100 Mbps, 1 gig. 10 gig, all right? Then you have 100 base T, which is what they call fast Ethernet, which used to be the standard, okay? Starting right here at Cat 6, this is now starting to be the standard. And hopefully they'll adjust this pretty soon, all right? Because data's moving super fast now. Then we talked about carrier sense, multiple access with collision detection. All right. We talked about when, let's say there's a bus topology, you may have 6 computers on one line trying to talk to each other. A, B, C, and D. A tries to talk to D. Well, what kicks in if there's a lot of collisions on the line and all the computers trying to talk to each other super fast, you'll see this kick in for wired connections. It's sort of like a timeout. Remember we used the analogy of a kindergarten teacher. So Brian's a kindergarten teacher. He's got 12 students. They're all trying to talk. He's like, be quiet. I'm trying to talk to James. And James getting in the corner. Just doing too much. Right, Mr. B? Right? So he's telling everybody over here. He sends a jam signal. Hold off, y'all. Back up. Back off. Let me finish my conversation and let me finish teaching. And then when I start to slow down, I notice the algorithm will notice that and then allow computers to fit in where they get in, trying to transmit traffic. Does that make sense? So that's that CSMA CD. And what is it for wireless? Ooh, I like testing y'all early when y'all asleep because I'll win a lot more because y'all not halfway paying attention. See, I take advantage of y'all in the morning. That's my plot. So if it's CSMACD for wired, what is it for wireless? This is collision detection. Yeah, buddy. I think I'm going to win this one. I give y'all 30s. Yep. Leah blew me up first, then Michael. Yep, y'all all right. CA. It's the CA, so it's CSMA, CA, collision avoidance. So I will take that, Michael. Yes. So, see, great start of the morning. Now, we moved on to fiber yesterday. As you can see, if we look at this, 100 base, right? So this is the fiber Ethernet. So this is the fiber equivalent for wired. Okay? So we're looking at here, the Ethernet equivalent to transmit fiber. 100 base T, 100 megabits per second. Pretty standard, right? But when you start seeing S and L, short range transmission, long range transmission, right? Short range receive, long range receive. Oh, get it? Now, when we get into the connections, you'll see what I'm talking about. So what you'll see here, you see the ohms. I think I got you on this one. What's the ohm 1 through 4? Dang it. You guys are too smart, man. All right, moving on. Nothing to see here, people. But typically of fiber, what you'll see, right? Fiber Ethernet standards. This is the transmit side. This is the receive side. So what you'll see is like it's like a two-headed monster, right? One fiber strand is responsible for transmit. The other is responsible for receive, period. They separate the traffic. So when you see it connected to what they call a transceiver, bringing it into a switch, you'll see a two-headed connection. That is happening. Okay. You'll also see when it's just one transmit, when traffic goes one way, that's when you'll see the long range. Okay. So keep that in mind if you see that on the exam. Yeah. Good tidbit. All right, let's move into copper cables. Let's get into it today, the connectors. There's some tools that you're going to use to get this stuff taken care of. So for the structure, when we're looking at this, it contains 2 to 18 pairs in a plastic jack. Interference, minimal EMI protection. This is for unshielded twisted pair. So when it's looking at the 2 to 18 pairs in a plastic jacket, oh my gosh. That is the structure of it. Minimal EMI use, popular for LANs because it is cost effective. You'll get grades like F5 up to 6A, and it's called 6A augmented. The A is for augmented. 5 is enhanced, 5E is enhanced, 6A is augmented. Now, when we start looking at these two flavors, because it's enhanced and or augmented, it's either letting you know it's backwards compatible, or you can get different speeds in there, right? So it can either go backwards or forwards, meaning in the speed rate, the bandwidth ratio that can go through the wire, okay? To make it simple, all right? So there's different flavors of those. Again, with the installation, avoid sharp bends. You don't want to bend this wire. And I wish we could have a lab where we can all do this stuff together and create a cable. Who's created a cable before? Mike has. Dr. Cern, have you been able to create, terminate cat a little bit? But you kind of seen it before, right? All right. It's something that takes practice. It presented, it's not like you can't do it. If you have a diagram, a wiring diagram on what's supposed to go where, you can pretty much do it in less than 45 minutes for the first time after fumbling around a little bit using the tools. After that, it becomes second nature. You'll be able to terminate the wire, okay? And we'll get back to the pin layout in a second. For shielded twisted pair, again, it's shielded twisted copper pairs. It's conductive shielding, EMI protection, reduces car talk, and you got the rest here. All right. And the key thing is avoid sharp bends in it because you will and you can kind of crack the cable. And then now you have to use tools like a wire tester to find out where the break is. So what happens is, since for those that didn't know, my mechanics and or my comm people know that if you plug in or you terminate this here into the tester, it sends a signal out on the wire, and where it's lost at, it measures how far it went, and then it disappears. But it lets you know how far it traveled and before it died, right? So then you use a cable tester to say, oh man, there's a 50 feet from here, there's a break in the line. We got to replace this whole cable. So that's what it helps you do if you have a node, host, endpoint, whatever, client that's not receiving a signal. All right, so it's a good thing. For wired implementation, when you want to use UTP or STP, a structured cabling scheme is a standard way of provisioning cable networks for computers in an office in a building. What you're looking at is the work area. If you want to do horizontal cabling, meaning you're going from the first floor, right, where cable comes into the building. Can anyone remember the closet that the demarc point is set at on the first floor in the building? What is the proper name of that area? You're correct. It is a patch panel where it will terminate and you will leaf off your different connections to go to different floors. But all in all, if I said I need you to go to this blank blank to look at the patch panel, what is that called? It's inside this room that has a name. It's not server room. Called a label before she typed it. Starts with an M. Next letter is a D. Last letter is an F. Main distribution
main distribution
frame. Yes, that is the first floor where everything comes in. Taking you back to your 1201 days. Then on each floor above that room is an IDF, an intermediate distribution frame, meaning they're funneling the cable up through plenum and all that stuff and the risers, right? They're going vertical now. Vertical. So they're bringing it all up and piping to each room. And then from that closet, then they're moving out connections from that closet. So in a building, it's like an elevator. Everybody shares the same stack, so to speak, of rooms in order to bring the signal to each floor. All right? In a telecommunication room or the equipment hub, that's a dedicated space. They don't call it that anymore. That's when phone lines used to come into a building. Then it went from punch down blocks is what they call it, where they terminate telephone wire. Then they used to terminate 110 blocks and 66 blocks, right? And they punch down Ethernet cable into a wall, and they separate the signal going out. But we'll look at a picture of that in a second. Your backbone cabling is coming from the MDF up to each floor to the IDF, so on and so forth. So that's your backbone cabling, and that is your demarc. Everything's going to be sitting in there for structured cabling. Here they call it the telecommunications closet. I have not heard that term in a long time. All right, so down here on the first floor, entrance comes in, modem, demarc. ISP brings the signal into the building. It's coming in right here. This is the building. This is outside the building. Everything is patched in. They bring it into a closet that's down here. And then from here, they do the horizontal cabling to bring it in to a switch. From the switch, everything gets parsed out to each room. This could be room 2, 110, 112, whatever you want to call these. And then you'll use PVC piping. Usually these rooms connect, and there's a closet room right up here. And then they have another switch, and then they'll do drop cables to bring everything to each room up here. All right. Usually your first switch that comes into the building right here, this is your core switch. Core switch. Core switch. I'm saying that for a reason. It is the switch closest to the exit. It is the switch closest to the exit. All right. Another term that you'll hear this called is called an edge switch. You heard that term, Mr. T? Yep, the edge switch, meaning you're at the edge, you're at the exit where ISP comes in. All right. And this is important to know that term because you'll have that big giant PBQ I was talking about. And it's going to use terms like edge switch, hierarchy, right? So we need to know the terminology on that one. All right. So this is what we're looking at here. When we're talking about the termination standards, let's revisit. Look at this, Jesus. You remember this one? Woohoo! T56A, T56B, right? This is how you're going to terminate your wires. All right? This little RJ45, you buy a whole pack of these, okay? From Amazon. You get like 100 for $5 or $10 or something like that. They got two flavors. They have the flavor where here's your unshielded twisted pair. What you do is you would cut the line here, expose all of this wire, unravel the wire until they're in separate lanes. You'll have this little piece here, this little terminator. The clip is in the back. This is the way you should be looking at it. Your finger should be hitting a clip that's in the back. Like if you look at it right now, from how stuff comes into yours, the little clips will be in the back. You're looking at it. There's your wiring standard going from left to right. Okay? A lot of folks think you got to strip these. You don't have to strip these down to bare wire. All you do is unravel them, straighten them out, and make sure they go into these positions 1 through 8. So you slide them in. The naming convention, you'll see it at the bottom. All right? G. And it should be a G with a small R for green. G, solid G, or a capital G for a solid color, and then so on and so forth. Once you slide these in, there's a terminator point. Now, some of these have holes at the top where the wire would come straight through to the top. And when you use a snipping tool, it shaves off the excess wire and crimps it at the same time. So it'll pin it in there. So there's crimps in here. When you press down and put enough force on it, it'll make these stay in place at each end so they don't move. They're like brass connect. They bite into the cable. They bite into the pairs. All right. So the T56A, I think I got y'all on this one. I think I got y'all. Y'all ain't gonna be so quick. Here's the question. Does T56A with this wiring standard connect similar devices or dissimilar devices? Ooh. That means it's A on both ends. Ooh. I was nice with that question. Nope, Elaine, it's the opposite. Good try, though.
Is that similar?
This is how it sticks, though. We have to see it. But I'm glad you tried. So we'll connect dissimilar. Not the same. So PC switch, router switch, right? B, one end will be A, one end will be B. It crosses over the pins. As you can see, the pin layout is different, right? It's different from here, crosses over the signal. You connect similar devices. PC, switch, router, right? So now I will tell you something though. I wouldn't trust too much doing these now or trying to get these pin layouts right with newer equipment because you can have both ends as an A and on the inside of the switch, it'll automatically flip it for you. It's an auto conversion. That's in the new equipment. So even if you got it totally wrong, it figures it out and they can figure out where's the receive transmit lines and switch them. But you want to learn how to do it right. But that's kind of like the fail safe. Morning, Charles. All right. So think of it like that. Just to set the expectation when you get out there, if you don't get it right. Next, patch panels. Cool. Mr. T had mentioned patch panels here probably a couple of seconds ago. Inside the closet, wire comes in, main switch is connected. You'll have the front of the switch that has ports. The back of the switch will have these little patch panels on the back. All right. Simply said, when you have a switch, and we'll get to some pictures in a minute because what I'm talking is probably a foreign language right now. But on the front of a switch, you have ports and a rack system. In the back, they'll have these patch panels that use wiring. See how it's wired? It tells you the colors of what goes where. You'll terminate there, and then on the front of it, so on the back, it'll be bare wire being punched down into the patch panel from the core switch. And you'll use a cord about this big. It's not long at all. Okay? The other end you will terminate with the RJ45, and you bring it around to the front to put it into a port. Okay? From there, you can stack switches, and now you can start moving the data to different areas. Okay? So they usually come in, they're getting away from patch panels that used to sit on a wall to moving termination points to behind the switch on what they call the rack, terminating there and bringing the signal to continue from the patch panel into a port. And then from there, that's when the magic happens. That's when you can start sharing the data with other floors and other devices. Okay? Now, when you get into this, you have to configure it. This is not something that automatically happens when you turn on a switch. You have to get inside of the switch, all right, get to the command line interface, boot it up, and you have to enable. You hit the term enable, and we're gonna get to a lesson here in a minute or an example, because I gave you a book. You remember it? 101 Labs for Network Plus. Y'all remember that book? Because if you don't have it, I'm gonna drop it in again. That's where we get into the labs using NetCat Academy, CCNA, and they'll take you to say set up a DHCP. The labs in the book walk you through how to set this stuff up and configure switches. We have to do at least 5 of those labs together because that will help you with that big giant PBQ that's like 10 minutes that's coming up on the exam. All right? When I saw it, I've been doing this for a while. When I saw that lab, I was freaking out. I said, what the heck is this? All right? So even in the new N10009, I failed it the first time. It was a brand new PBQ. I'm like, what is this? Figured it out, went back in the second time. I was like, oh, trunk lines. That's what they're looking at. That's what they want. Oh, they want me to tag VLANs, virtual LANs, so traffic can move from one street to another and talk to each other. Oh, I get it. The diagram looked kind of funky, but once I figured it out the second time, I'm like, okay, cool, good to go. Passed it. Okay? It's the shock and awe factor for the first time that you see it, even for us people that's been in for a while. Okay? All right, for the structure, here's the punch down blocks in the rear, terminates RJ45 point ports in the front. So they bring this cable around to the front, plug it in, you start negotiating or configuring the switch. Your IDC terminals, intermediate closets, terminals allow for secure compact cable termination. Bring that around, and then it supports the 2 standards. With the structured cable installation, this is the things you need to have. These are the steps. You'll see this on the Net Plus too, in various types of questions. All right, Martin. So okay, ooh, we got a question. Leah says, is that like a universal? Oh, Elaine asked that. I probably missed that, Lane. Was that talking about the patch panels? Or what was I talking about? One second, y'all. He's typing his question. Wait, might be faster to unmute. Oh, that was the cables. Okay, yeah. That's pretty universal, yes. Mm-hmm. With the structured cabling, this is what you need to do. Gather the tools, plan the route, label the cables, route the cables, bundle the cables. So they call it pulling the cables. This is, in the term here, they call these the wire dogs. There's jobs that you'll see out there on Indeed and stuff. All they want people to do, they need IT people that know how to run cable through a whole building for the first time. Okay? You'll go from building to building, contract to contract, all brand new buildings that get built from Wendy's down to a racetrack. When they're being built from the ground up, they need wire dogs to run the wire through the building. Okay? Then another team comes in, brings in the equipment. All right? They create the loop, they put in the patch panels, they set up the work areas, they terminate the cables, they put the connections, and then they test and verify, and then they document. So usually you'll see 3-step tools. So some IT companies, they'll sit down with the customer. They'll sit down with the customer and say, what do you want to do? Well, we want to build 5 racetracks in this area. Okay, cool. They'll look at the schematic, they'll make a logical map and a physical map. Okay, the physical map comes first because on that map, when they're doing like the schematics, they say, this is where I would like the TVs to go. This is where I would like the POS systems to go, right? And then now somebody has to do what they call a logical map to say, okay, now for IP schemes, this is what I'm looking at. This is where I would put a switch. Here's what the IP address would be. The blah, 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 like we did yesterday with LANs, right? Now we're looking at the logical, and I'm saying, inside this building, I have 4 different areas. Here's a core switch that leads to another switch. That's when that soldering would come into place as an IT professional, because now on the overview, you have to write down, oh, they need probably 25 IP addresses. Over here, they might need 100. Blank, blank, blank. Now you have to do what they call variable length subnet mask, meaning segmented LANs, and you have to give IP address pools and net IDs for each area. Then all of those go into the core switch, setting up DHCP segmentation for those LANs. Okay? Once they had that all down, they start executing the plan. They get contractors now to show up after the building's starting to be put up. They bring in all the cable because the walls are exposed. Easiest time to do it, right? You don't want to punch a hole in the wall after the stuff's being built. They terminate everything, cut the cables, make the connection, set up the patch panel, verify connectivity, and then now the drywall should be going on, right? And ceiling tiles. And then now they just kind of wrap up the work after that and move on to the next job. Okay? It's a pretty fun job, but you're living on the road a lot. I had a company want to hire me in California to do it when I was in Lemoore. They said, yeah, we need somebody, we need wire dogs. I said, so what's the pay? Like, it's like, oh, it's $70,000 a year. But you're always on the road though. And they want you to use your own car. Right. We'll give you a phone, but you gotta use your own car. No, we get mileage, right? Yeah. So you make 70, but they might pay you $15,000 a year in mileage. Off rip. They just put that into your salary. Because if you drive more miles, they don't have to pay you for those more miles because you accepted the mileage stipend. Wear and tear on your vehicle. But if you need the experience, hey, these are the tools that you're going to use to terminate. I'm the Terminator. Get to the chopper. Arnold Schwarzenegger, 1980. Okay, here we go. Here's your cable cutters. You're going to need those. Then you need crimping tools. With the crimping tools, this is what you're going to see. Usually right in here, that RJ11 and that RJ45. Once you put the wires in there, ooh, almost got it right. You slide them in here. That's an RJ11 right here. That's an RJ45. And then you crimp down. Boom. Seals the wire on the inside of the termination point. Okay? Then what you could do, you take it out and you can slide it over here. And here's the splicing tool that cuts off any excess wire that's on the end of it. There's a little razor blade in here. So please be careful. Don't be playing around with this thing, putting your finger in there like, ooh, you might have a missing fingertip. Don't do that. Mike's like, yup. So be careful. There's a live razor blade in there. All right. Next, here's the punch down tool. All right. This tool here has it's a little skinny razor blade on the inside. And behind it, it's a force tool. Do. So let me show you. I got a video I'm going to show you on how to terminate too. See this right here? The tool punches, it forces the wire into the colored termination area right here. It snips the wire at the same time. So it terminates, seals, breaks, done. Okay? It's a quick tool that you use to terminate into the patch panel or wire blocks. Here, self-explanatory, strippers. The cool thing about this is, just don't think, oh, they're just put in here and they know what to do. There's diameters. In your mind, I want you to think ohm. Diameter size, right, for a cable. They have different diameter sizes, starting from the very smallest wire that goes up to typically what you see. You fit the wire, you open it up, you fit the wire into the desired ohm or diameter size, clinch, spin, pull, strips the wire. It's predetermined. It's like class full. You can't mess it up. You match the wire to the size of the hole, crimp down, spin, yank, strips it for you. Easy peasy, lemon squeezy. All right? It's Friday. All right. I'm not even going to do this for you. It's just matching what's what. I think you know what's what just by looking at the picture. Sorry. Now, they have all-in-one tools. We have some at, I've used some where they're like this big, and this tool has all of these tools in one. Mike, you use those? They're expensive. I mean, you can get one off Amazon for about maybe $45-50. Sometimes they're more, but it's all you need is the one, like Neo, the one, right? Takes care of everything. Oh, cool. Moving right along. Now we're going to shift a little bit, talking from Ethernet and Ethernet standards. Is Ethernet when data travels inside of there? Is it analog or is it digital? Is it analog or is it digital? How is the signal moved? You're correct, digital. Phone line is usually analog, old school. And we're just talking wavelengths here, okay, for analog. Now, when we're looking at fiber, how is fiber traveling? How is the transmission medium? Yep, light. All right, so light pulses bouncing on the inside of the wire. So it gets to where it's going. So it can go many miles, right? Yep. So with cables, those are thin strands of glass or plastic that are on the inside of the wire. Transmit data using light pulses. The core, ultra pure strands of glass cladding reflects. So the cladding on the inside reflects the light to bounce back inside to continue. So it's angled. It's like an angled aperture. All right, to bounce it. Then you have the buffer, which is the outside protective jacket of it. Darn it. Sorry. The benefits transfers up to 800 gigabits per second. Dang! 800 gigabits per second. Long distances, immune to electromagnetic interference. However, there's been many ships out in the ocean that are doing some nefarious stuff. Transcontinental fiber lines are laying on the bottom of the ocean. There are ships out there from other countries that try to, what they call, tap these fiber lines. And they have devices that can somehow intercept the light pulses that go through. So it might be immune to EMI, but somehow, some way, they try to read the light pulses that go through there. So sometimes they try to bring up the cable off the ocean floor and tap the line or send divers down there or something down there to do it. It's so down there, diver crush, right? They pop, doop, pressure. But they may have some submersibles to try to bring it up, right? So that's why we have our Coast Guards and other merchant marine ships out there that are patrolling these areas. You're talking about miles of fiber laying between here and another continent, right? There's a world map that shows you this stuff. And so people are trying to tap those lines. With single mode and multi-mode fiber, here are some differences. So over here, it tells you the different factors that you're going to be looking at that are the same between the two, but in each column, it tells you what's happening. So for the core diameter, single mode, small core, multi-mode, large. It lets multiple light modes pass through, right? It's called CDW something. It's a couple of, I forget the acronyms for them. There's like two wavelengths that can go through with light at the same time. And that's where you get that multi-mode, you get multiple light modes that can go through at one time when they're bouncing. Light transmission travels directly down the fiber. Minimal reflection for single. Minimal reflection and attenuation. The reason why you use multi-mode in smaller runs is because the light bounces, but it causes more dispersion, separation, and attenuation. Distance and bandwidth suitable for long, best for short. Application, long haul networks, short term data centers and lands. Believe it or not, multi-mode is less expensive. Single is more expensive. That's a question on the exam. Customer wants to upgrade. What is their best choice for connecting a data center in another state? Remember this. All right. Here's that diagram I was telling you about fiber. One side could be transmit and one side can be receive. Okay? That's what we're looking at right here. Now the ends of these are called ferrules right here. Where these meet. Right there. Doink. called the ferrule. That is where that connection meets the interface. Believe it or not, for fiber, that's your most vulnerable spot. Because if you don't have a good connection at the ferrule and the information is coming in so fast, that's where you lose a lot of data quality for fiber. Okay? So it's important there to get it right. So you have three flavors of connections. You have the subscriber connector. Okay? This is the more popular use in telecommunication and data networks. Push and pull design, quick deployment, low insertion, loss, and it's very durable. So it takes up small spaces on server racks. So SC is the one that people like to use. Okay? The ferrule size gets smaller for a Lucent connector because now generally you're bringing in single mode, heavily populated patch panels and cabinets, heavily populated. Square shape, duplex header. One side is usually transmit, the other side is usually receive. So it's going in one direction, like the group, one direction. Boop, 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 boop. These have clips on the back, just like the RJ45, some kind of form factor like that, where it can release from the ports or from the transceivers, okay? Then you'll jump back up to 2.5 millimeters for size, for core size. And this is what they call a bayonet connector. See this? That's what I was talking about when we used back in the day. You had to push it in. It had two knobs on the side, and you twist. As you twist, it tightens down the connection to the interface. That's a bayonet connector, BNC. Use these for LANs data centers. Bayonet twist lock. It's older, but it's still used. This is quick. It's a quick release. Very cool. All right. So that's what we're looking at as the three connectors. As we move on, got a question for you. Which of the following is the correct order of the following fiber connectors shown above? People putting 4. Let's look at the chart.
2.
Let you breeze at that for a second. Now I'm going back. There we go. Leah got it. Mr. T got it. Michael's got it. That first one's a straight tip. Right there. Then SC, LC, LC duplex, and FC. Good job. With these different connections for fiber, you have different ways that it's going to move. These are the different wavelengths that can be transmitted to bounce light. Wavelength division multiplexing.
Oh, good morning. Currently
Unfortunately,
working
on the
on
exam,
the
when they're talking about fiber, they
Net
will
Plus,
use these words like
A
division
plus, Net
multiplexing.
Plus,
Well, you've got
Security
division
Plus,
multiplexing.
and
You're like,
CYSA.
what the heck are you talking about? Know that they're talking about different ways that the data is being transmitted in fibers. So you're halfway there. Now you have to figure out which type of fiber are you they're talking about. Allows for multiple data channels to share the same fiber using different wavelengths of light. You have bidirectional. So it's WD and BDI. I don't know how they come up with these acronyms. Supports transmit and receive over the same strand. Who believes that there's only So in multi-mode, let's look at it this way. For SR, short range or long range, usually it's one strand of
Oh,
fiber.
awesome! So you've already got
You're looking at
security
multi-mode
plus.
fiber. Now you could have a whole bunch of strands in that
So
one.
they
They're
used
all
to have it
separated.
where it doesn't
Okay.
expire.
When we're
I
looking at
think
this,
now it's
it's
just a thing
sending
that
these
you
light
have to keep
pulses
on
through
renewing
different
it.
strands from multi-mode
But
in
then you
different
don't really
ways.
have to do the test
So
anymore.
you
You can just pay to have
bidirectional
it
WDM, use your
to have it
shifted
being renewed.
wavelengths between
But that's
these
really awesome.
1310 nanometers or nano. Somebody look up NM. That eludes me. If somebody can. For transmit, and then it's 1490 for RX.
Yep.
Requires the installation in opposite pairs, and it's documented inside of the Ethernet standards for these right here for bidirectional B.
So now
transmit.
CompTIA is doing
You have coarse WDM.
is doing a lot of good things. We can see
So
now that they're one of
CWDM
the biggest
supports up to 16
recognized
wavelengths being transmitted.
certification organization
Nanometer.
that
I
is
figured
out
it was
there.
that. But I want
But
to
you
get
also
the right
have this
information.
website
for
that's
looking
called
at
Cisco that you can go to get
Typically
certified
used
as
for
well.
46
And they
bidirectional
also do a lot of the
channels
courses free.
on a single strand. That's a lot of data. All right? And used for unidirectional, 1-to-1. And then dense. This one has more channels. Has to be more precise with lasers, shooting the light. But it can support multi-channel 1, 10, 40 gigs. And transceivers are installed on each end to accommodate the data coming.
Are you currently in the field doing the
super fast? We're talking about data
or in a
center
career
fast
field that requires your security
to
plus?
process that information.
Is that a requirement for you currently working?
All right. I think it's time for a break. What y'all think? All right. Tell you what, let's take 10 and we'll meet back here at the top of the hour.
Is much improved because they're not having to go to two places, basically to the head office and then to the cloud. They're getting their data directly from that service. So some key advantages of software defined when more efficient management.
Yeah, I've seen that a lot. So a lot of job description they have other certification requirements, but it's just a plus if you have things like these.
Different vendors, but if we can use a same or similar interface in the cloud for all of our services, of course, it creates more efficient management. And again, it's a better overall experience for not only the clients at home, but the administration themselves trying to manage these networks.
Yeah, a lot of the jobs they don't mind you having the experience. The certification, I think you can still start working and then throughout the process get the certification. Especially if you have the experience already, it'll make it a lot easier for you to gain the certification. And this site that is called Cisco has a lot of the training materials that helps a lot as well. Especially if you're transitioning from one field, or even if you're already in the IT field, it makes it so much more easier.
In this video, we're going to take a look at the virtual extensible local area network. When we're talking about local area networks in a traditional,
so I've seen on the LinkedIn website that you can pretty much create a profile and put all your information there and put the specification of what you're looking for, and it'll just be a long list of job that comes up. It comes up with the requirements, the salary that you'll be getting, or the wages, and it has the application prompt there right away that you can apply for a specific job. Especially if you already have the experience and certification, it makes it a lot easier. And that is something that I recently found out as well.
Now, the idea of having things connected in their own LAN is that they don't have to be routed. The connection is very fast, and we're connecting at a layer 2 type of conversation. So VLANs have been around a long time. The way that VLANs are distinguished in the Ethernet world is part of the frame, the Ethernet frame itself, has been reserved for VLAN addresses. The maximum amount of VLAN addresses allowed in Ethernet is 406 or 4,000 networks. Now, while that sounds like a lot of networks, when we talk about virtual servers using multiple virtual hosted servers, they may need more than one MAC associated with them. So when you plug that physical machine into a network switch, there's more than one LAN associated or VLAN associated with that one physical device. And in that case, the switch has.
Thank you for stopping by as well. I appreciate you subscribing. Stop by anytime. You can comment or leave a like in any one of my videos. Just let me know that it's you.
Provider who's managing many companies and they're connecting over multiple VLANs. We can quickly run out of VLANs if we have a lot of customers. For instance, if we have 500 customers, we end up with only 8 VLANs available for each of those customers. So this becomes a problem, especially in the world of virtualization, where we might need a lot of VLANs. So this newer protocol was developed here called VXLAN, which takes the layer 2 addresses and tunnels them inside of layer 3 traffic. Now remember, layer 3 traffic is routable. I can send it through routers to the internet. And the idea here is that two computers, one on either side of a connection, will think that they're on the same VLAN because I take the physical layer information and I encapsulate it or preserve it. Now, in a normally routed network, the layer 2 information is discarded at every router hop. But in this case, we're going to preserve a VXLAN number inside of our layer 3 traffic and deliver it on the other side. So those two computers would think when they look at the physical addresses that they're on the same LAN. So some types of network traffic work better and are necessary at certain network traffic requirement points. So we can actually use this protocol instead of our standard VLAN protocol. So by doing this, it was, first of all, let's just say that it was created by the engineering task force, so it's an internet standard, and it's available because it's an internet standard. It's available on multiple newer devices. Now they understand this protocol built into the stack. So they share a single physical network of different organizations, and because we can route these things, we can connect two devices across the company through several routers or around the world through several routers and still think they're on the same system. Pretty cool. Fast. The tenant cannot see the network traffic of other tenants because we're actually tunneling this inside a private connection from point to point. No one ever sees what's going on inside walls. Packets. So what we get here is a logical tunnel between the source and destination. The MAC is inside a UDP packet, which is then addressed with an IP address, which is routed through the external network. And the encapsulation with UDP packets, as I said, get IP and Ethernet headers because it still has to travel through the physical network. Now, again, don't confuse this with the virtual LAN we place these machines on. All that's inside the frame, but when we're routing data through a network, remember that from hop to hop, it does have to get the Ethernet information or the physical layer information as it's moving through the network. And then packets are routed like regular packets, which means they can go over IP, basically anywhere around the world. So we can now, because the addressing space in this newer protocol is wider, instead of 496, hence we can have theoretically 16 million VX in this case. And we can create network segments between data centers, so two servers in two different locations can look like they're on the same physical network. Again, so we can have servers all over the world still participate in the same VXLAN. again, remember the idea about VLANs is anyone inside of the VLAN cannot see the traffic between those servers unless it's purposely routed into that VLAN. So again, they're secure, they're private, they're connected to each other, and have a LAN level connection between those two servers. So some of the benefits. They can run on any UDP capable network, which is basically any IP network. As long as it can handle IP traffic, it can handle this traffic as well. And again, the physical layout and geography are unimportant. No matter what kind of LAN they're connected through or on, they look like they're on the same LAN segment. The virtual network creation forms physical network ports. So again, they are connected at that physical layer, and they seem that they're connected directly to each other through the VXLAN. In this video, we're going to take a look at zero trust architecture. In a zero trust architecture environment, all aspects of the network are verified before access is granted to any resource or data. In the traditional network, we used to work in an office, in a cubicle, with equipment that was owned by the corporation, that was managed by the corporation, and security was really focused on the perimeter network. That is, our connection to the rest of the world. But because of the way people work these days, meaning working from home or bring your own device or those types of things, our security has to look at more than just that perimeter. And in fact, we need to place those protections as close as we can to the protected assets. Meaning, if there's a database server there that needs to be protected, we need to protect it at that location. Then, no matter which direction people are coming from, they are checked and verified before they get access to that asset. One of the portions of this is identity and access management. When we're trying to record the identity of a server or a person, it should come from what they call a single source of truth. And what that means is that there's one database that's protected and managed that contains all the information we need to verify someone or something's identity. Usually, when we provide proof of identity, we use multi-factor authentication. So the days of just having a password is gone. We use not only a password, but maybe a one-time code that's sent. So we need more than one factor to identify. Logging and auditing are also part of identity and access management, and they're there as a measure of maintaining.
All right. Welcome back from break.
We can look back at the logs and the audit logs to see.
Welcome back from break.
And further take
So,
actions to.
I'm gonna have a video that I have on the screen. It's about 8 minutes long, but I like this channel because she does a good job on showing basic networks that you can set up at home, especially if you have fiber coming into a house, you want to convert it over to Ethernet, talking about media converters, transceivers, and she just gives you a quick synopsis of what she's doing and what it looks like when it comes in, so you know what each component will do. So it's a good channel. So I'll let it play, and then we'll kind of finalize the lesson when we get back.
So you have an Ethernet network, reliable and stable, but the digital world is evolving at lightning speed. In the world where information moves at the speed of light, connectivity is king. And the upgrade from Ethernet to fiber optic network is nothing short of a technological leap. So join us today as we embark on a journey through the intricate process of this upgrade step by step. And if you're interested in exploring the future of solutions, you can visit our solution page now for innovation at your fingertip. Just click, connect, and conquer. Ethernet networks are the bedrock of wired local area networks. They utilize copper cables to transmit data through electrical signal. While Ethernet has been the go-to standard for decades, traditional Ethernet have their limitations, and they often struggle with slow speed compared to modern data demand. Moreover, susceptibility to interference from electronic devices and electrical noise can disrupt data flow, and also latency can be the issue for time-sensitive applications online gaming and video conferencing. Fiber optic network, on the other hand, represent quantum leap in data transmission technology. They rely on fiber optic cable, which use light signal instead of electrical signal, offer blazing fast speed, virtually unlimited bandwidth, and are impervious to electronic magnetic interference. Fiber optic network excel in scenario where data must travel over long distance, like data center, and they're becoming increasingly common in local network due to their exceptional performance. But before you're diving half-assed into the fiber optic upgrade, it is crucial to take a step back and assess your current network setup. Evaluating your existing setup helps you gain a clear understanding of your network requirement. You can identify pain points such as slow speed, connectivity issues, and insufficient bandwidth that need addressing. And assessing your current setup also help you plan for future. Ensure that your upgrade aligns with your long-term goals. And you can also ask yourself a few questions to determine if you're ready for an upgrade. For example, are you experiencing a slow data transfer rates or network construction during a peak usage time? Are you regularly transmitting or receiving large files or streaming high-definition media? Or are you planning to expand your network in the near future? By carefully evaluating your current network setup and answering those questions, you can determine whether you're ready for an upgrade and ensure it aligns with your network requirement and future expansion. So now we're in front of the demonstration board. Today we are going to show you a simple fiber optic network setup. So let's see what we have here. Instead of using Ethernet cable, of course we are upgrading it to fiber optic cable. This one here is factory pre-terminated and tested cable. It has stronger cable structure with protective anti-band materials. Also support up to 10G speed and available in 100, 300, and 500 meters. You can also use a coupler to get variable length. This one here is 300 meters 4-string fiber optic cable. And as you can see on both sides, we have the compact media converter. Now, media converters are very important. They can bridge the gap between your existing Ethernet network and the fiber optic infrastructure. It converts the electrical signal from your network devices into optical signal that can travel over fiber optic cable. This one can serve up to 1000 megabit per second gigabit bandwidth fast network speed and also supply up to 20 kilometers fiber optic cable. Inside, we will knit this SFP transceiver. We are using the BD SFP transceiver, and this is where we connect to the fiber optic cable. Since we're using the single mode, this one is suitable for single mode fiber optic cable. There's single mode and multi-mode. Single mode are normally for longer distance, while multiple are suitable for shorter distance. Let me put it back and remember, the fiber optic network performance and reliability are only as good as the equipment that you invest in. So offer quality components can save you headaches in the long term and ensure that your fiber optic network performance at its best. So without saying, let's do the connection together.
Well, I basically bought this roof over the internet, which wasn't something I'd ever done before.
So first we'll need a router to provide the network data. A router manages data traffic between devices and ensure data reaches its intended destination. And then I'm going to use a short patch cord to connect the router to the media converter. Since we cannot plug in the fiber optic cable directly to the router, so we'll need this to convert the electrical signal into fiber optical signal. Power it up. And this is the SFP transceiver. Plug it into the media converter and use a fiber patch cord to connect to the media converter and also to our fiber termination box. Let's plug it in this one. This is the fiber termination box. It can provide a secure and organized enclosure for fiber optic termination. Also make it easier to access and maintain fiber optic connection. This is the 300 meters 4-string fiber optic cable. I'm going to show you over this side. I already unscrewed it so you can see how it looks like. Inside we have 4th string and each string has a letter. This is letter A, so make sure you match with the letter. Over that side we plug into the first one. So on this side we also using the fiber patch cord to plug in the first one, match string A. The fiber termination box contribute to a clean and professional appearance, help maintaining an aesthetically pleasing network environment. Then I'm going to connect it to our SFP transceiver and to the media converter. Let's plug it in here, powering up our access point and our media converter. Using a short patch cord to connect the converter to our wireless access point. And this is how you do a fiber optic connection. It's actually pretty simple, and the whole connection is done now. To prepare your environment for a successful fiber optic.
Okay, that's why I like her channel. She'll show you step by step, and then she quickly puts it together, and she makes these little labs, right? So in your mind, you can now see, oh, that's how it comes in. Yeah. So it came in fiber. She put it to the fiber termination box. From there, she fed the signal coming down via light. She had to put it in a transceiver, which went into the media converter. Now she converted the light to Ethernet. Then it went to the wireless access point, and boom, the whole organization now has Wi-Fi or whatever, that room, right? So it's pretty cool. If you want this channel link, I will give it to you. She does a really good job. Let me drop this in here. Hey, Suze, can we get the... Oh, yes, sir, I just dropped it for you. Ha, 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 ha. There you go. Yep. So Fast Cabling is the name of the channel. And she has like 40,000 people that go through there to see different examples. And it's cool to see it before you actually get to the exam, too. So you kind of put it together. I mean, I'm sorry. I wish there was more we could do for our online environment to actually do exercises and do stuff. But unfortunately, with this type of learning environment, you'll have to either do VMs or get the stuff on your own and practice. So, yeah, that's the extra step that needs to be put in there. All right. Now, let's move on to our PowerPoint, our last part. Physical installation factors. These are some factors that we have to consider before we upgrade. All right, make an upgrade in our organization. These are all the things you got to think about. Now, this is definitely one question on the exam right down here, standard sizing. Yep. They're saying you want to mount some racks, some new server racks. What's the most important part? Well, sizing is one of them, and access control. But they said, what's the most important variable when installing or putting together rack systems? Yeah, it's the sizing. All right, so different components have different sizes. They got to be nested inside of the rack, okay? But again, if we recap at the other one, secure areas, make sure telecommunication, closets, server rooms, all that, have proper provisioning and access. Usually you'll put there is a PVQ that you'll see that will have a layout of a room, and I'll bring it up too when we're doing the lab for a test out. So I'll bring that back up for CompTIA. Oh, do I have that one? I don't have that one, but there's another one I can use. where it says you have to put proper security protocols around an organization. First one being, you might want to put keypads on the outside of the server room for access, right? That's one. You might have to put proper wireless access points in different areas, make sure the channels don't overlap. That's two, right? Where would you put cameras on the premises? You might have to slide a camera on the outdoor perimeter, a camera on the outside of the server room so you can monitor who's coming in and out, right? And or another secure area. So you got to start getting into PBQs where it's not just one thing to do, it's 1, 2, 3, right? Select, put it where it needs to be, then you might have to configure it. So that's why we need to make sure we're down on level 1 or 2 information, not just superficial sitting on the top. These 3 right here, temperature monitoring, you're gonna need for your server rooms, HVAC for humidity control, and make sure you have proper electrical stability. Ensures uninterrupted power supply, monitors the voltage and irregularities. Then HVAC as well, you'll have an IoT device that will see if you have a flood or something happens or excessive moisture. It could tell if that room is getting flooded or if there's a lot of water. The sensor could tell. I had a student on my last ground class. He actually, his part-time job on the weekends was working for an IT company, and he'd be on call. And what did he do is go out to different places. One night he got an alert at 2 a.m, jumped in his car, went down to Verizon at a mall. It was a store, and there was a water pipe that busted. So the IoT, the sensor went off to say something's being flooded, and the closet that was in the back of the store, it was getting flooded. It was water everywhere. Then the fire suppression system came on. It was just really bad. But yeah, he reacted to that and gave a situation on ground report what was going on. So you can do that too. That's another area you can get into in IT, first responder for IT. That's becoming really big now too. So temperature monitoring, things like that. For power essentials and power management, ensure stable power for the network. Okay, this prevents spikes, surges, and failures. So you're making sure you have the proper items in place to do that, which is going to be your battery backups or your PDUs. The load and voltage. So you have to account for, there is a PBQ that says, what things do you need to account for with items in a data center? What's important? They'll have an example to say, is it heating and cooling? Is it power, right? Or the number of IoT devices you need for sensors, for all this stuff to operate. So out of all 3 of those, when you're setting up a data center, which one do you think is the most important that you need to monitor? Power. Yep, because if something happens, what's gonna kick in to handle the load? It's just like you're having a motherboard and you want to upgrade. You look at the manufacturer specs on the total amount of power that board needs. If it was maxed out, can it handle it? Right? Plus 20%. That's the power supply unit you'll buy for your new computer. Same thing happens with a data center. Okay? Now with the PDUs, they ensure clean power signals, offer remote monitoring and control, where the battery backup is a local level storage protection. It's a universal power supply, uninterrupted power supply, that's local for the machine. You have to know the difference. So for PDUs, you can not only plug in one, it looks like a small little generator, but it has like 12 outlets. You could probably plug in multiple machines into it, It's online. It has sensors. You can monitor it. It'll send you text messages to let you know there's a problem. Okay, so you can regulate, and it'll regulate the power. Battery backups, local, one machine at a time. Usually that's when you use it for your most important machines in an organization. So they're two totally different things that do the same thing, right? For fire suppression, of course, make sure you have the proper fire extinguishers. That's one lesson that they took out of the 1201, 1202, where there was a fire extinguisher class, and it says safety, right? But Class C extinguishers, Class C can handle, is it electrical fire and gas fire or something like that? So they can go either way. So you have to have a Class C extinguisher. All right. With fire suppression systems, extinguishers and stuff like that, believe it or not, that is part of your problem. That is part of your daily walk or your quarterly walk. You have to make sure these fires, where's my safety people, my fire people that was on base? If you did it for your organization, I did. I had to do that when I was overseas. Yeah, I had to go to the fire department, base fire department, because I was in IT, do the class, get signed off. And I'm the person they asked for every time they came around and did the audit, like once a month or something. And I'd walk with them. You have to make sure these fire extinguishers are signed off, make sure they're not old or expired, and it is part of your purview. All right. Depending on where it's at. Okay. And these are the different extinguisher types. Now, on the exam, I didn't have to say which sprinkler. No, they're not going to do that. So don't worry about it. All right, so that's the lesson. Is there any questions? Any at all? Charles says it was one of the most silly. Yes, it was a silly additional duty. Why are you picking me? But it's your org, right? It's your organization that's taking up space on the base, so they want you to be responsible for it. Aaliyah says, is a PDU like a panel of controls that each with controls power for something specific? Yes. So you'll have 12 come in. You can regulate. It regulates clean power coming in. Make sure it's good to go, because you don't want power spikes and all that. It's conditioned to power, so it can provide it to several pieces of equipment. And it also serves as like an IoT device, so it can send you an alert if something's going on with the power or something like that. Yep. Charles says they did a duck, duck, goose to pick someone. You're playing. That did not happen. Y'all sat around in a school circle to do duck, duck, goose. Y'all got a fun place to work, I'm telling you. But this is pretty straightforward. So key takeaways for this lesson, though. Know your Ethernet cabling, speeds and type, and fiber connectors. The connectors, believe it or not, is the most important part when they talk about fiber on this exam, because you don't pick the right connectors. Yeah. Straight tip, LC, and subscriber connector, right? Proper use. Aaliyah says, ask because in the vehicle that I was assigned had something like that. For example, there was a switch that controlled the light specifically, controlled the ECU, and also up separated from that. Oh, inside the vehicle that was it there AMRAP? No, it wasn't. I know AMRAPs had something like, a TGS, okay. I know they're self-sufficient too. You can hit an AMRAP with mostly anything. That thing will keep going. It's got back redundancy systems in it. Run flat tires, all types of stuff up in there. Yep. All right. If there are no questions at this time, I will release you to your studying material. Yep, I've seen those. Those are pretty cool. That's the Hummer base. They've moved to the different body type now, haven't they? I think they're still in use. Calm on the move, yep. Those is cool. I'm gonna download this picture. Doink. I like that picture. Put it on my desktop. Bam. Just different versions. Okay. That is a cool vehicle. All right. So I have one person that needs to get some kind of grade on the board in Canvas. Check your grades, go into your grades, see what you got. And just move along. Everybody's moving along. Everybody's already got at least 2 practice tests done or 1. So you guys are moving. Michael says, I sued to work on the Phoenix, tons of fun. His ground antennas that connect to it also has. I asked Mike about the kind of, oh, gotcha, okay. Now it makes sense, yeah. All right, go ahead and turn to, and remember at 10 till, go ahead and step out for your break and be back at the top of the hour, so appreciate you.
Plus course with a broad discussion of something we refer to as the OSI model. This is referring to the Open Systems Interconnection Reference Model, and it's a model we use in IT to describe the process that data takes as it traverses our networks. The OSI model is not designed to be a detailed description of this data, but instead is intended to describe a broad overview of how data traverses our systems. We're also not describing the OSI protocol suite. Indeed, most of the protocols we use today are based on TCP/IP. but the OSI model is one that we can apply to many different protocols, and it works perfectly with the TCP/IP protocols that we use today. Also keep in mind that there are many different protocols that might operate at an individual layer of the OSI model. So as we step through an individual layer, keep in mind there might be tens or even hundreds of protocols that might exist and work at that particular layer. By understanding this OSI model, we can converse with other people in information technologies in a way that we would all understand. It doesn't matter if they're working inside of your own company or with a different organization. When you mention OSI layer 7 or OSI layer 4, everyone understands what that means and what effect it has on the overall operation of the network. If we start at the top of the OSI layer or OSI layer 7 and work our way down to OSI layer 1, we have layer 7 being the application layer, layer 6 is the presentation layer, layer 5 is the session layer, layer 4 is transport, layer 3 is network, layer 2 is the data link layer, and layer 1 is the physical layer. There are many different mnemonics that people use to memorize this, but if you start at the top and work your way down, you can take the first letter of each one of these layers and you might have a term such as all people seem to need data processing. That's application, presentation, session, transport, network, data link, and physical. Let's start our conversation of the OSI model at the bottom of the OSI model, or layer 1. We refer to this as the physical layer because it's describing the physical signals that we send through the cable and fibers on our network. At this layer, we really don't have many protocols to speak of because we're really just talking about getting a signal from one part of the network to another. When we refer to a physical layer problem with the network, we are referring to the OSI layer 1 physical layer. This means that we might have a bad cable, a bad fiber, there might be interference on a wireless network, and it may require us to do a series of tests to determine if we are really able to get a signal across this particular wire or this particular fiber so that we can keep this network running. A lot of the troubleshooting that you do at layer 1 is running loopback tests, testing cables and fibers, and checking different adapter cards and other devices to make sure they're working properly on the network. One step up from the physical layer is layer 2, the data link layer. This is the fundamental layer that's used to communicate between two devices on the network. We often refer to this as the MAC address layer because that is the data link control layer, or DLC layer, that is commonly associated with the network cards that are in our devices. And most of the time, these are Ethernet adapters or wireless adapters, and we refer to that physical address on that device as the data link control address, or the MAC address. In this case, MAC address is not referring to an operating system, it's referring to the media access control address. So anytime you hear someone talk about a MAC address, they are referring to the hardware address of that particular adapter card. Since the network switches that we use on our network determine how to forward traffic based on the destination MAC address, this is a layer that we often refer to as the switching layer. So anytime we're referring to a MAC address, a problem with a switch being able to operate, or anything else that may be associated with this particular hardware address, we're referring to OSI layer 2, the data link layer.
Building your cybersecurity stack isn't rocket science. Simply create your own security apps with Sola. Get answers to the security questions you really care about and act on them instantly. Set up custom alerts, build workflows, or create dashboards. And guess what? No code needed. Don't want to DIY that ish? Sola's app gallery has plug-and-play apps ready for you to use. And with Sola AI, you get your own super talented security wingman. It can do all the work for you. Whether you just need to tie together some loose ends or build up your security stack, Sola's there for your needs. It's simple, quick, and free. Get security done with Sola.
If you've been injured, we're on top of your case.
From the very beginning to the very end, when you walk out the door with your settlement check.
You just need.
The next layer up is OSI layer 3, or the network layer. We often refer to this as the routing layer because this is the layer that routers use to determine how to forward traffic. And they are specifically looking at the destination IP address in order to determine what the next hop might be for traffic traversing the network. This is also the layer that we're able to fragment these frames into multiple pieces, especially if we're sending it across a network that may require smaller frames than what is on our local network. So we can cut those frames up into smaller pieces to be able to fit them through the network and then put those pieces back together on the other side. Anytime we're referring to a problem relating to IP addressing, subnet masks, anything related to an IP address or anything about routing, then we're probably referring to layer 3, the network layer. Layer 4 is the transport layer, and as the name implies, we're referring to the ability to transport information from one device to another. You might also refer to this as the post office layer, because this is responsible for getting your letter or your information from one side of the network to the other. The protocols that are often used and operate at layer 4 of the OSI model is TCP, that stands for Transmission Control Protocol, and UDP, or User Datagram Protocol. These two protocols are commonly responsible for getting all of the information within our IP packets from one device to the other. In many cases, this involves taking a large amount of data, putting it into smaller pieces to be able to get it across the network, and then putting those pieces back together on the other side. Before we can send that information from one side of the network to the other, we may need to create a session so that a device is able to receive that data. Layer 5 is the session layer, and it provides communication management between point A and point B. Anything relating to the initiation of a session, stopping the session, or restarting the session can commonly be associated with that layer 5 session layer communication. If an application is using some type of control protocol or you're tunneling information within existing data, then you're probably using OSI layer 5. OSI layer 6 is responsible for putting all of this data into a format that we will eventually see with our human eyes. This refers to character encoding, application encryption, and decryption, and it's often combined and discussed in conjunction with the application layer at layer 7. Layer 6, or the presentation layer, is the layer that is commonly in operation just prior to us seeing this data on our screen. And the top layer of the OSI model is OSI layer 7, or the application layer. This is the layer that we see on our screen. So anytime that we are interacting with an application, we are operating at layer 7 of the OSI model. Common applications that would operate at OSI layer 7 are HTTP and HTTPS, FTP, DNS, POP3, and thousands of other application protocols. Well, that's a broad overview of the OSI model, but how do we fit things in the real world into each of those layers? Let's start down at the bottom with layer 1, or the physical layer. When we refer to cables, fiber optic connections, the signal going across those connections, or a wireless network, then we're operating at OSI layer 1, or the physical layer. When we refer to OSI layer 2, or the data link layer, then we're talking about Ethernet frames, MAC addresses, or addresses referred to as extended unique identifiers, or EUI. There are EUI 48 addresses and EUI 64 addresses, for example. And as we described earlier, anytime we're referring to the switching process, we are referring to OSI layer 2. At OSI layer 3, or the network layer, we're referring to IP addresses. So anything that has an IP address or subnet mask, or referring to the way that routers forward traffic, all happen at OSI layer 3. If you're referring to a TCP port or a UDP port, then we're operating at OSI layer 4, which is the transport layer. At OSI layer 5, or the session layer, we're using control protocols to start and end different sessions, or we may be tunneling traffic using protocols that operate at OSI layer 5. We often associate the encryption of application data with OSI layer 6, or the presentation layer. So if you're communicating to a website and you're using SSL or TLS to be able to encrypt and decrypt that data, that process is occurring at OSI layer 6. And at OSI layer 7, or the application layer, is where you are interacting with the application itself. Anything that you're seeing on the screen, the application itself, or any messages from the application are often referred to as layer 7 information. If you wanted to drill down a little bit further into the OSI model, you might want to capture some data on your network and view that data inside of an application such as Wireshark. I have a Wireshark protocol decode on my screen where I've captured data on my network, and this Wireshark has 3 separate windows that is displaying different views of the same data. The top window is a frame-by-frame breakdown. For example, I've highlighted frame 88 on this top window. The middle window describes more detail of what different information is contained within that single frame. And on the bottom window, we have a hexadecimal and ASCII breakdown of the data itself. Let's focus our view on this middle window, which is a summary of this highlighted frame 88. You can see that there are 5 different lines of data inside of this single frame, where the protocol decode has separated out the individual protocols within the single Ethernet frame. Let's start with the one at the very top, which describes frame 88, which has 2005 bytes on the wire, and 2005 bytes were captured by Wireshark. If you wanted to associate that line with the OSI model, that would be best associated with layer 1, or the physical model. Next down is Ethernet 2, which has a source MAC address and a destination MAC address. And since we are describing MAC addresses, everything within that line of the Wireshark decode is associated with layer 2 of the OSI model, or the data link layer.
Now's the time to upgrade to the new Dell AI PC. It's optimized for AI workloads and engineered for the future. So no matter what's next, you're ready.
Getting everyone in your home on the same page about energy use is hard, so we're making it easier. Xcel Energy offers programs and services like a home energy assessment and smart thermostat rewards, plus rebates to help reduce the cost of energy upgrades in your home. We make energy decisions easier. Who gets to control the remote? That's up to you.
The next line down describes the Internet Protocol, or IP. And as we described before, IP fits squarely in layer 3 of the OSI model, or the network layer. And in fact, there are individual IP addresses listed here for the source IP address and the destination IP address. And you can see there is a DNS resolution here that shows that the IP address of 72.14.247.19 is also associated with googlemail.l.google.com. As we move down this list, we're moving up the layers of the OSI model, and the next one is the Transmission Control Protocol, which means we're communicating via TCP for this Google Mail communication. Since TCP is in this list, we must be at OSI layer 4, or the transport layer, and indeed you can see TCP port numbers for the source and the destination of this traffic. Since the destination port is port 443, Wireshark has already filled in that we're communicating over an encrypted channel using HTTPS. And if we go one layer down into the secure socket layer, this effectively encapsulates the top 3 layers of the OSI model. So secure socket layer and everything underneath it are referring to layer 5, the session layer, layer 6, presentation layer, and layer 7, the application layer. Here's a summary of that protocol decode broken out into the different layers of the OSI model. We had electrical signals at the physical layer. Layer 2 at the data link layer had Ethernet frame information. Our IP addresses were at layer 3, or the network layer. Our TCP encapsulation with our TCP port numbers is at the transport layer. Our session layer linked the presentation information to the transport. Presentation layer was obviously performing that SSL or TLS encryption and decryption, and layer 7, or the application layer, is referring to that Google Mail front end and being able to send and receive emails using mail.google.com. Hopefully you're now able to see how this very broad description of an OSI model can be applied to practically any communication that's occurring over the network. And
Leah says, is there a difference between security vulnerability when choosing between IP address reservation and static?
What we're referring to when we talk about a layer 1
Yes.
problem or a layer 7
Good question.
problem.
So usually what happens when you set up a network, so your IP address could be for your router 192.168.0.1 or 1.1 or whatnot. Then you have a reservation pool. Usually when it first assigns addresses, they'll take from the higher end of the pool and work their way down to the lower number of available addresses. Sometimes when folks set up their
All of these devices work together to
IT or their server addresses and all that, they'll pull from the first 10 addresses and put it on the most important things like IP cameras, printers, and stuff like that. Sometimes that's a clue to the cyber attacker that those numbers are generally their most important assets. So sometimes you want to pull from the middle or separate, right, different IP addresses to kind of mask, so they just kind of blend in, and then put them on separate LANs. That was a great question.
These may be subnets that are next to each other in the same data center, or these IP subnets may be located in different parts of the world. We refer to a router as an OSI layer 3 device. At the OSI layer 3 or network layer, we're referring to IP addresses, and IP addresses is exactly what's used by a router to be able to determine the next hop for this information. You may sometimes see this routing functionality also included inside of an existing switch, and we often refer to these as layer 3 switches, which of course is referring to that OSI layer 3 functionality. It's not that the switch itself is now operating at a different OSI layer, it's just within that same piece of equipment, we have both a layer 2 switch and a layer 3 router, so we've abbreviated that as a layer 3 switch. These routers often connect many different types of networks. So we may be connecting a local area network or a LAN.
Yes, the static IP addresses never change, and the reason why they forbid probably static addresses is the simple fact that if somebody used like mmap or angry IP and they figure out all these IP addresses, over a period of time, they'll keep scanning and notice that they don't change. So if there's a vulnerability, they're already inside that piece of equipment. You never change the address. They can sit in there forever. It's like somebody sneaking in your house and hiding in the closet. Unless you check that closet, you don't know that they're in there.
Data link device.
Yep.
These operate mostly in hardware. The hardware inside of these devices is referred to as an ASIC. That is an application-specific integrated circuit. There are many different functions and capabilities inside of these switches, especially if you're using one designed for the enterprise. For example, many of these switches have the ability to include power on the same wires as your Ethernet connection, and we refer to that as Power over Ethernet, or PoE. And as we mentioned before, you may hear folks refer to this as a layer 3 switch if the switch includes some type of routing functionality built into the device itself. Security on our networks is also important. That's why you probably are using a firewall at home, and you most certainly have a firewall in your office. A traditional firewall allows you to filter traffic based on a TCP or UDP port number. But if you have a more modern firewall, you're probably using a next generation firewall, or NGFW, which is able to identify applications traversing your network and allow you to manage whether that application should be allowed or not allowed on your network. Most firewalls also have additional functionality. For example, it's common to find firewalls that will allow us to encrypt traffic traversing the network through a virtual private network, or VPN. It's very common to have a firewall at one remote site and a firewall at another remote site and be able to create an encrypted tunnel between those firewalls using this VPN functionality. And most firewalls can also operate as a layer 3 device, which means the firewalls themselves can act as a router. That's because they're often sitting right between the ingress and egress point of your network, where all the traffic on the inside of your network is going to the outside or internet connection, and your internet traffic is coming inbound to your local network. We rely on the firewall to be able to manage the communication between the inside and the outside of the network. To be able to perform this functionality, many firewalls also provide network address translation, or NAT, and because they are a router, it's very common to have dynamic routing protocols supported inside of the firewall as well. Many data centers might also have standalone IDS or IPS devices, although much of that functionality is also integrated into the more modern next generation firewall. IDS refers to an intrusion detection system, and the IPS refers to an intrusion prevention system. Both of these work in similar ways. They're looking for attacks that are inbound to your network and are able to identify, alert, and in many cases prevent that attack from gaining access to your network. These are commonly known attack types. These might be exploits against operating systems or the applications that you're using, and they might take advantage of known vulnerabilities with those applications or systems by taking advantage of a buffer overflow, a cross-site scripting vulnerability, or other known vulnerabilities to those systems. If you're using an intrusion detection system, it's able to alarm or alert if it ever sees any of these inbound attacks. If you're using an intrusion prevention system, it's able to go a step further and block that particular attack before it gets inside of your network. Since an intrusion detection system is not able to block that traffic, it's very common to see an intrusion prevention system used on our enterprise networks. If you've ever used a website that may be accessed by millions of people every day, you may be wondering how that site is able to remain up and running without any type of downtime. In most cases, it's because that site is using a load balancer to be able to distribute that load across multiple physical servers. As the end user, you may have no idea that this load balancing is taking place, but if you were to look at the data center for this organization, you might find a large number of web servers or database servers in farms that can be used in conjunction with this load balancer to maintain uptime and availability. These load balancers are also very good at identifying any outages to these servers. So if one of the servers happens to fail due to a hardware error or some type of software problem, the load balancer can recognize the issue, take that server out of the rotation, and continue to provide access to these services using the remaining devices that are connected to the load balancer.
Cybersecurity today is so messy and expensive. And why does it take so long? It really shouldn't be that. Get started with Sola, the studio where you can build any security hack. Whether you're the security person or just the person tasked with security, tie together some loose ends or build up your security stack. You fit Sola to your needs. It's simple, quick, and free. Get security done with Sola.
Struggling to lose weight? This is why I switched to compounded GLP-1. I have struggled with my weight since childhood. Diet and exercise was extremely difficult, leaving me sore and sliding backwards. I've lost a total of 20 pounds so far.
After 3 months, I've lost about 16, 17 pounds, which is more weight than I've been able to lose in a really long time. It's made me feel a lot more confident.
I'm a mom of 3 who works full-time, and the extra weight was just not going away. If you are wanting to start your journey towards a healthier you, I can't recommend Hers enough.
Weight Loss by Hers offers access to compounded GLP-1 injections with the same active ingredient as Ozempic and Wegovy.
I can do things that I enjoy. I don't get out of breath anymore doing normal activities like I did where I was around 200 pounds.
Hers provides sustainable resources for life after treatment. I felt heard when I didn't think a treatment was working for me, and the specialist easily adjusted. A catalyst for feeling healthy in the inside as well as the outside.
All right, let's hit up a break, y'all.
All-in pricing.
See y'all in 10
Ongoing
minutes.
care included at no extra cost. Free shipping right to your door if prescribed. Through Hers, your weight loss plan is personalized to your goals. Plus, you get access to unlimited messaging with a licensed medical provider. No insurance required, no in-person visits, 100% online. Take the free assessment to get started today.
Here's a common design for a load balancer where users on the internet would be accessing a service at a location. To the end user's perspective, they're accessing a single server, but they're really accessing a load balancer that is distributing that load between multiple servers inside of that company's data center. These load balancers can also optimize the communication. For example, it may perform TCP offloading so that the communication to all of these servers on the inside of the network are occurring as quickly as possible. These load balancers can also act as an SSL offload, which means that they will provide the encryption and decryption capabilities instead of having the servers themselves manage that process. Data might also be cached on the load balancer, so requests made to the load balancer can be answered immediately instead of going all the way down to the server to provide that data. And load balancers are also very good at prioritizing different types of traffic over others. There might be certain web pages that have higher access than others, and you can commonly perform that prioritization using quality of service, or QoS. Load balancers can also provide application-centric load balancing, where certain pages may be located on certain servers, and all of the requests to those pages would go exclusively to those individual servers. Many organizations have security concerns about individual users being able to directly communicate with a server or service that's on the internet. One of the ways that the organization can manage these connections is by putting a device in the middle of this conversation called a proxy. This proxy is responsible for taking the user's request, performing that request on their behalf, receiving the answer to that request, verifying that the answer doesn't contain some type of malicious software or malicious code, and then providing that answer to the end user. That is the purpose of a proxy, to sit in the middle of the communication and make that communication on the user's behalf. Since the proxy is sitting in the middle of the conversation, it's a perfect place to do caching, so the user can make a request to a web server. If that request has already been cached by the proxy server, the answer can go right back to the user without having to access the internet. We might also provide access control from the proxy server so that we can request a username and password from the user in order to gain access to the internet. From that point, we might want to filter URLs or perform some type of content scanning to make sure that the user is not receiving any type of malicious software. Some proxies require you to configure the operating system or the applications that you're using to identify the proxy and be able to use that to send and receive communication. But not all proxies work in that explicit manner. There are also transparent proxies that will work invisibly without making any changes to the operating system or the applications in use. It's very common to store documents and other files on centralized storage facilities inside of our data centers. One type of storage is referred to as a network attached storage, or NAS. We often refer to this network attached storage as providing file level access. That means that if we wanted to gain access to information within a file, we need to pull the entire file across the network into the memory of our system, and when we're writing information or changing information in that file, we will need to write the entire file back to the NAS. A more efficient way of communication might be through the use of a storage area network, or a SAN. This is very similar to reading and writing information from a local storage drive, where instead of copying the entire file to be able to change just a bit of information within it, we have block level access, which means that we can change just the blocks that have been modified. And when you have very large files, this could be a very efficient way to modify just a little bit of information within that very large document. Whether you're using a NAS or a SAN, you're probably transferring a lot of files to these systems. And for that reason, we want to be sure that we're using the most efficient method of communication. It's very common, for example, to put the NAS or the SAN on its own isolated network, and it's commonly a network that has very high bandwidths. If you're in your office and you look at the ceiling, you might see a device like this. This is an access point. This device allows us to communicate wirelessly from our device to the rest of the network. This is not the wireless router that you might be using at home, which is a router and a wireless access point and a switch in the same device. When you're in larger enterprise environments, you're usually using a device that is purpose-built for a single function, and having an access point means that we're using this for wireless communication and wireless communication only. On the other side of this wireless access point is very commonly an Ethernet connection. So this is bridging communication between the wireless network and the wired Ethernet network. That's why we refer to access points as an OSI layer 2 device, or a data link layer device, because it's making that translation between the 802.11 wireless network and the 802.3 Ethernet network.
Organic and dairy-free?
Here we go.
At Sprouts, our shelves are filled with new, exciting, and delicious discoveries. This is...
In most businesses of any size, you probably have more than one access point. That's because you probably have a very large building or a series of buildings, and you need to be sure that everyone is able to access that wireless network wherever they happen to be inside of these buildings. But this means that we have to manage many different wireless access points wherever they might be in our local network or in a remote site network. And we might need to manage security settings, access policies, and other configuration parameters within that access point. We also have users that may be very mobile and moving between different parts of the building or moving from one building to the other, and we need to make sure that they can seamlessly roam from one access point to the other so that they are always connected to the network. Instead of connecting to each individual access point to make these configuration changes or manage this process, we can have a centralized management tool that allows us to manage all of our access points from one central place. This is a wireless LAN controller, and it gives us that single pane of glass so that we can manage the entire infrastructure while we're sitting in one chair. From this single device, we can deploy new access points with a full configuration. We might want to set up performance or security monitoring and be alerted if we happen to see anything across any of our access points. We can also take any changes that we need to make and deploy those automatically to all of our access points with one click of the mouse. This also allows us very commonly to create reports on how much our access points are being used and be able to understand if we need to update or change any of our access point locations. These are often proprietary systems, so if we have an access point from one particular manufacturer, then we're also using the wireless LAN controller that is also from that same manufacturer. If you were to somehow get inside of the networking cable and see what was going back and forth over that connection, you would see there was a lot of different activity going on across many, many different systems. All of these are designed to focus on specific functions. For example, we may need to get a piece of data from our network to a network that is on another part of the world. Or we might need to access a system that is already located somewhere else and provide technical support or be able to share a screen. There's also a need to have traffic management on our network so that certain applications have a higher priority than other applications. And lastly, we need to be sure that all of our systems are up and available, and it may take specialized protocols to make sure that that occurs every step along the way. One way to speed up the process of getting access to data is through the use of a CDN. This is a content delivery network. And as the name implies, it is designed to provide a way to get data very efficiently from one central point to an end user. These are often set up in geographical areas. So there might be a CDN server in North America, South America, Africa, Asia, other parts of the world, and you're able to cache information at each one of these points. It takes time to get data sent from one part of the world to the other, so if you can have all of your North America users access the North American CDN, it's much faster than having them all go out to a centralized server that might be located in Europe. So if you're watching this video on YouTube or on the Professor Messer website, you're using a CDN right now. It's a way for very small or very large sites to be able to distribute their data to users all over the world and make sure that that data is as accessible and efficient as possible.
People who pick post-university choose our 100% online Master of Education program so they can learn practical.
For those of you that work outside of your corporate facility or perhaps do a lot of work from home, then you're probably already familiar with a virtual private network or a VPN. This allows you to connect to a remote network while sending all of this data encrypted across the network. It's a very secure way to transfer data, even across networks that would be inherently insecure, such as the public internet. VPNs often use a device called a concentrator or a head-end device to be the central connection point for all of the users who are accessing that VPN. This is often a purpose-built appliance that's designed to do high-speed encryption and decryption of network data in real time so that you can have many people being able to send secure data across the network decrypt all of that data, send it to the inside of the network, and then reverse that process to get the response back to the user. This can be a standalone device, but very commonly we integrate this VPN concentrator function within a next generation firewall itself. Because of the encryption and decryption process required to perform this VPN concentration, we usually will use a purpose-built appliance or piece of hardware to be able to do this. That provides very high throughput and can support hundreds or even thousands of users simultaneously. But if you have a smaller network, you may not need a purpose-built appliance, and there are many VPN concentrators that will run as software on an existing operating system. You may have to install a specialized piece of software to be able to use a manufacturer's VPN, although there is VPN software that does ship with Windows, Mac OS, and Linux operating systems so that you can connect to many different kinds of VPNs using that generic software. Not all applications are designed to run simultaneously on a network, and certainly some applications may have a higher priority to your organization than other applications. For example, there might be a real-time audio or video stream that has a higher priority than a file transfer. Because of these requirements, it's very common for network administrators to provide some type of prioritization to these applications. This is often done through a quality of service or QoS configuration. You might also refer to this as traffic shaping or packet shaping. This allows the administrator to control what type of applications can flow through their network, usually based on bandwidth usage or particular data rates. This might allow your real-time applications to have full control or access to the network and put a lower priority on other applications that may simply be transferring files. To control this quality of service, you may need to make configuration changes inside of a firewall, a router, or a switch. These devices might have a pre-built list of applications and might also allow you to add your own applications to the list. And at that point, you can decide what priority the applications might have relative to everything else that's running on the network. One of the challenges we often run into with technology is that it's very good at performing a task. And often it can perform these tasks over and over and over again without any type of human intervention. Unfortunately, this could also put a device into a state where it's performing the task over and over and over again and never finds a way to complete or end that particular task. For that reason, we've often built in different functions with our protocols so that we can recognize when a task may be going on too long and simply remove that task from the network. One common way to provide this identification is through the use of a time to live, or TTL. A time to live is effectively some type of timer. This timer may be based on the time of day, or it may be based on the number of iterations that a particular task completes. Once that timer hits 0, we can then have that task stop what it's doing, or we can drop that task from the network. There are many different cases for a time to live. One is a packet that is constantly looping between different routers. We might want to have that packet automatically dropped if that loop occurs a certain number of times. Another good example of a time to live might be to clear a cache, where we might access a website, have that website stored in a cache, and then that cache is only available for the next 60 seconds or number of minutes. When that timer hits 0, the cache is cleared, and the next time that website is accessed, you would have to go all the way out to the site to be able to bring that information back, at which point that is placed in the cache and another timer starts. Another example of using a time to live to stop traffic that is looping around your network is through the use of a routing loop. This is a really good example of where you might have router A thinks the next hop is router B, and router B thinks the next hop is router A. And what you'll find is that the packet goes back and forth between those routers over and over and over again. If you were going to perform a trace route, you would see this loop in the trace route itself, where the route goes to 10.1.10.1, then it goes to 10.2.10.2, then back to 10.1.10.1, then back to 10.2.10.2, and so on. And this will continue all the way through until it reaches a time to live.
Thank you for calling Capital One.
My team's Gen AI tool helps you answer customer questions faster.
We use RAG with LLMs
And customize.
This is something that does occur occasionally because you might have many different routers, and those routers have many different routes. So it's very easy to make one single IP address mistake in a static route and create this routing loop on your network. For routing loops, we use a TTL field inside of the IP packet itself. This allows us to identify and stop a loop automatically if one occurs. In this example, we have router 1, and router 1's next hop is router 2. We've configured router 2 with a next hop of router 1, which means that this packet is going to go back and forth between these routers until something stops that loop from occurring. Fortunately, we built functions within IP, or the Internet Protocol, to look for this loop to occur and stop it if it finds that it's occurring over and over again. In IP, the time to live is referring to the number of hops that a packet will go through a router. Each time a router processes a packet, it decreases the time to live by 1. And when that value gets down to 0, it discards the packet, effectively ending the loop. The default time to live for Mac OS and Linux is usually 64 hops, and the default time to live for Windows is 128 hops. Since the router is decreasing the time to live by 1 each time the packet goes through, it's watching that number decrease every time it goes through a looped connection. And when the time to live gets to 0, the router drops that particular packet. If we were to look at the frame of IP, you can see there's version numbers, header length, type of service, total length, and other fields within the IPv4 header. The one we're interested in is the one called time to live, and that's the one that the router will use to determine if it's gotten down to 0 and if it should discard this packet from the network. Here's a very simple protocol decode of an IP header. You can see this is frame 1. We have the Ethernet information with the MAC addresses for the source MAC address and the destination MAC address, and this is an IP version 4 header. You can see the source IP address and the destination IP address in the header itself. If we were to break this header open and look at those individual fields that we mentioned from that previous slide, you can see there is a differentiated services field, a total length field, an identification field, and right here is a time to live field. The time to live for this particular packet is 58 hops. So this packet would need to go through 58 more routers until this got down to 0, at which point it would be removed from the network. In most cases, our total number of hops between us and the destination that we're trying to visit somewhere on the internet is usually around 12 to 16 hops, sometimes more and sometimes less. But that's a relatively small number when you consider that the total default time to live on macOS or Linux is 64 hops, and the default on Windows is 128 hops. That gives us plenty of room to be able to get data from one side of the internet to the other and not have that information accidentally dropped by a router. Depending on the protocol you're using, time to live may have a different definition. With routers, time to live is associated with the number of hops. But in DNS, or the domain name system, the time to live is associated with the total number of seconds. Let's take a scenario where we're performing a DNS lookup, and you can do this yourself by using NSLookup or DIG, and you can resolve or look for the device www.professormesser.com, and your DNS server will return some type of IP address associated with the Professor Messer web server. Inside of that DNS resolution is information about time to live. This tells us how long we should cache this local entry on our system. So we want to cache it for a certain number of seconds. How many seconds? Well, we're going to cache it for the time to live seconds. The time to live is included with the configuration on a DNS server. And this is the output from the command dig www.professormesser.com. You can see that the answer section, where the DNS server is providing us information, says that the server www.professormesser.com has a time to live of 300. This is an internet address. The A is for address. And then we have 3 different IP addresses associated with my web server. This 300 value is the one telling our local machine, keep this IP address in your cache for 300 seconds. If you do the math, that is 5 minutes. Once that 5 minutes has elapsed, our local cache removes that particular resolution And if you want to know the IP address for that same server, you would need to perform another DNS query to update your cache for another 5 minutes. This allows me, as the administrator of my web server, to be able to change the IP address in my DNS configuration, and I can feel relatively secure that most people will have an updated version of that IP address within 5 minutes. We use time to live for many other protocols as well, so make sure you look at the documentation for that protocol to understand exactly how we're measuring time to live for that particular protocol.
When Verizon gives you a free phone on any plan,
Gemini, show me the concealer.
you use AI a lot.
The long, thin tube in the middle.
Yes, boyfriend of the year. Did we say a lot? We meant a lot.
Gemini, is my houseplant leaning away because it hates me?
Nothing personal. It's leaning away for more sunlight.
Come here. Gemini, any pointers on my downward dog?
But hey, it's the new Google Pixel 10 Pro, plus Google AI Pro for 6 months.
Ah, appreciate it.
Okay, if there's one AI site builder you need to be, this is Dope Tech from Wix. Now this whole flow is a conversation, so your words actually build your website. I'm going for a store, and after a free-flowing conversation, I get this detailed site brief. And just like that, my first draft is ready.
Cloud computing has undeniably changed the way we approach technology. With one click of a button, we can deploy an application and multiple services, all seemingly with unlimited resources. We're able to scale up and scale down these applications as we need, providing elasticity, especially in times when we have large demand, and scale it back down when that demand goes away. We also have applications that we can now scale up or scale down and access those applications from anywhere in the world. Cloud computing also uses multi-tenancy, where many different kinds of infrastructure. This allows for efficiency in the use of technology and efficiency in how much it costs to use this technology. Not only do we have virtual servers that can live in that cloud computing infrastructure, we can also have virtual networks. Let's take the scenario where we might have 100 individual servers that are running in our data center. That's a relatively large farm of servers. We've designed this infrastructure to have redundancy in the network. There are multiple servers. We've got load balancers and multiple firewalls, and we've designed it for uptime and availability. But now let's take this entire physical infrastructure and let's move this infrastructure to the cloud. We're going to migrate 100 physical servers to effectively one very large physical server. Inside that one very large physical server, we will run 100 virtual servers inside of it. Now that we've taken these 100 physical servers and migrated them to a cloud infrastructure, what do we do with our networking infrastructure? Not surprisingly, we will virtualize this network infrastructure as well. This is referred to as Network Function Virtualization, or NFV, where we can replace our routers and our switches and our other networking devices with virtual versions of those networking devices that are running in this virtualized environment. Although our firewall and our switches and our routers are no longer physical, they still have the same functionality. We can see those devices, our network interfaces, and everything about the network configuration all from our hypervisor. So we have the same functionality, it's just now in a virtual appliance. Just as we're able to push a button and deploy a new server, we can push a button and deploy a new firewall or a new switch or make a router configuration all within this virtualized world. This gives us a lot of flexibility for deploying applications, designing the network connectivity for those applications, and connecting our different cloud infrastructures wherever they might be in the world. A common application instance inside of a cloud infrastructure might include a web server, a database server. There could be load balancers, virtual switches and routers, and virtual firewalls. All of these will run inside of a virtual private cloud, or a VPC. It's very common, especially in larger environments, that you would have separate VPCs.
I just graded everybody's practice exam submissions and stuff, so it's good stuff so far.
This allows you to keep all of these systems separated, but still allow you to manage all of them as individual virtual appliances. Although these VPCs may be different application instances, we might still want to have devices within those separate VPCs be able to communicate with each other. To provide that communication, we need a device in the middle called a transit gateway to be able to connect all of these VPCs together. You can think of this transit gateway as a cloud router that allows us to connect and allow communication between all of our different VPCs. If you need connectivity to these VPCs from the outside, you may need to add additional security in the form of a VPN connection. This allows someone who may be at a remote site to be able to bring up a VPN tunnel, connect to the transit gateway, and effectively have communication to all of your different VPCs. It's very common to use a VPN at a remote site or from a user's workstation to be able to gain access to these private VPCs. But there may be times when you want to make your application instances available to anyone on the internet. In that scenario, you might want to use a VPC gateway, or what we refer to as an internet gateway, so that users anywhere in the world will have access to your applications. We might also want to have these devices in each of our VPCs communicate outbound over the internet to other resources. We would use a VPC NAT gateway to provide this communication, and the NAT stands for Network Address Translation. Our VPCs and the private networks that we're running inside of those VPCs can translate to a public IP address to be able to communicate out over the internet. This includes security rules so that your VPCs can connect outbound to internet resources, but you may not necessarily allow inbound access from external devices. And it's not uncommon for many organizations to use multiple cloud providers, but still require connectivity between those cloud providers. We can provide that connectivity through the use of a VPC endpoint, where we create a direct connection from a VPC on one cloud provider to a VPC.
Tackling your security concerns starts with a prompt. With Sola AI, you get answers to the security questions you
on another cloud provider. Here's an example that has a number of different VPCs. We've got a virtual private cloud with a public subnet for public applications that people can access from anywhere on the internet. We also have a private subnet on this same cloud provider where we have a private virtual machine. Well, if we have a different storage network, which certainly could be at a different cloud provider, that cloud storage can easily connect to the public subnet over the existing internet and using a VPC internet gateway. But our private subnet is not accessible from the internet, so we need to add a VPC endpoint that will allow our cloud storage to communicate directly to what is a private subnet and virtual machine. Many cloud providers will include additional security that you can layer on top of your VPCs. Security groups and lists are effectively a firewall that's created for your cloud-based services. This allows you to control what traffic can go outbound and inbound to your VPCs. Most of these are based around a series of port numbers and protocols. So you can define a TCP or UDP port number and add that to your inbound or outbound rules in your security groups. You can also add layer 3 addresses to this, so you can add IP addresses that are individual addresses, maybe an entire block of addresses using CIDR block notation, or specify IPv4 or IPv6 ranges directly within your security groups. This is very similar to configuring a traditional firewall, which operates looking at TCP or UDP port numbers. In this example, the inbound rules have a number of predefined rules, but you can customize these as well with your own port numbers specific to your application. In your cloud provider's front end, you would include in your network security list the list of rules that you would like to assign. For example, I have a rule that is inbound using TCP port 443, and any IP address is allowed to communicate inbound with that rule. I have another rule that's an inbound rule for TCP port 22, and it's the same broad range of any IP address. Once you define your network security list, it will be applied to all of your virtual private clouds. You can see that I have a virtual cloud network for subnet X, subnet Y, and subnet Z. These very broad network security lists will automatically be assigned to each one of those individual networks. One of the challenges with these network security lists is that they don't provide a lot of granularity. When you configure a network security list, it's automatically assigned to all of your virtual cloud networks, even if you don't need that particular rule in that cloud network, and even if you need additional rules for one of the individual cloud networks. Fortunately, there are ways to add additional granularity using a network security group. With a network security group, I can assign rules to individual virtual network interface cards, or VNICs. So you can see I have similar security rules that I've defined as a network security group. I have network security group A, which is inbound TCP to port 443, and I have a network security group B, which is also an inbound rule to TCP port 22. I've identified these as the network security group A with the green shield and the network security group B with the blue shield. And you can see that I can assign those network security groups to individual network interface cards that may be inside of a virtual cloud network. This one is on a single subnet where I've defined different rules for different interface cards within the same virtual cloud network subnet. You can see by using these network security groups that we do have additional granularity that we can bring down to the individual interfaces. But this also increases the amount of administration required to manage all of these different lists. If you find that you need additional security above this, you might want to look into a virtual firewall or other virtualized platform to include additional security to your application instances. When you're deploying a cloud-based application, you also need to consider who will be accessing that application and from where. If you're creating an application that anyone on the internet would need to access, then you would probably want to include it in a public cloud so that everyone can gain access. But if you're building out a cloud-based application that is for internal use only, you may want to deploy this to your own virtualized local data center where you have a private cloud. In many organizations, we often use both of these, and we need a hybrid configuration of both public and private clouds for all of these applications. One type of cloud model is software as a service, or SaaS. This is commonly associated with software that is on demand. You have a login screen on your browser, you log in, and now you have access to the application. Someone else has written the application, someone else manages the application. Your data is stored somewhere within that application, and you don't have to do anything else to be able to use that particular app. You don't have a local installation of software, you don't manage or upgrade any of the software itself. Instead, you simply log in and use the app. This allows for centralized management of the application and the data that you're putting into the application, which means everything is being stored on a third-party cloud platform. This is a complete application offering, and you don't have to do any type of development work to be able to use that app. A good example of software as a service would be an app like Google Mail or Office 365, where you simply log in and use the app. There may be times when you would like to build your own application and deploy and manage your own data, and all you really need are the computing resources to be able to run that application. In that model, you want to use infrastructure as a service, or IaaS. Sometimes you'll see this referred to as...
You got to sing the song, Charles.
Or
Bits,
HaaS,
frames,
because you're effectively
packets,
using hardware
segments,
in the cloud and then using your own
bits,
software on top
frames,
of that. This means
packets,
you would be responsible
segments.
for
There you
installing
go.
your software and managing all
Gotta
of
do the
data
jingle,
associated
man.
with that software. If the software needs to be upgraded, you would be the one.
Yeah, like I read the hint in the question,
as a service model.
and then I don't
The application that you're
put it in the
using and data
answer,
that
you know?
put into that application is
The layers, right?
but you have much more
One of these
control
days.
over the access
Yeah.
and
So layer one,
of that data
physical,
when you're
how it's
using
moving.
infrastructure as a
So
service.
like through
An
wires,
example of
through
infrastructure as a
wireless,
service is with web
through
service
digital.
providers, where you can
Layer
buy
two,
time on a
frames,
web server
has to go
and
through the
make that
switch.
server available to
It's
everyone on
switching.
the internet.
Yep.
A middle ground
Layer
between
three,
software as a service and
packets,
infrastructure as a
routing going through a router. Layer 4 segments. Now it's being transported.
All of the development efforts to
Yeah, you got to do the dance like Kevin said. You got to do the wiggle wiggle.
The cloud provider gives you all of the tools necessary.
Bits, frames, packets, segments. You got to put a shoulder into
You
it.
can think of this as a series of building blocks provided by the platform
Bits,
as a
frames,
service infrastructure, and then build out those blocks to create your.
Oh my God, y'all get me into trouble,
The
boys.
underlying engine that runs the application is the responsibility of.
Josh go look at this video like, what are y'all doing?
Your responsibility is to build and maintain the apps that are
Like, join in, Josh. It's fun.
as a service. A good example of a platform as a service infrastructure would be something like Salesforce.com, where they give you all of the tools necessary to create a customized application running on the Salesforce.com platform. Here's an example of a cloud responsibility matrix that
Now,
you
if we
might
can get
find
Jesus to
with
break
any
dance,
cloud
that'd be
service
great.
provider. In this chart, I've separated out
Give
software
him some
as a service,
cardboard, you can
platform
pinwheel.
as a service, infrastructure as a service, and then an on-prem device
Like the
that
80s.
you would manage yourself.
Not the Carlton.
On-prem, everything from the data to the applications to the physical data center are all the responsibility of the customer. But with infrastructure as a service, you have the physical data center, the physical network, and the physical host, all provided by the cloud provider, and then you handle all of the other pieces of that particular application. With platform as a service, you can see that network controls, applications, and the identity and directory infrastructure may be shared between the customer and the cloud provider, but you'd still be responsible for the accounts, devices, and the information and data. With software as a service, much more of these are provided by the provider themselves. For example, everything associated with the applications is clearly in the responsibility of the provider. Everything above that would still be the responsibility of the customer. So depending on the type of infrastructure you want and the type of responsibility that you're willing to take on, you'll need to pick the right cloud model for your application deployment.
At Sprouts, our wide open layout.
In this course, there will be a lot of conversations about TCP/IP, moving packets across the network, and very often we lose track of exactly what that means. So I thought it would be good if we start with an overview of Internet Protocol and how it operates. The goal, of course, is to get data from one side of the network to another. And there are a number of different processes involved in being able to transfer large amounts of data from one computer to another. In the analogy that we use today, we're going to describe this transfer of data from one device to another as using a moving truck to get data from one house to another. We can also think of the roads that we're using as the network that we've created. This might be a wired Ethernet network, a wireless network, a wide area network technology, or many different types of network
Hours
connections.
update as of yesterday at 6 o'clock.
Those network connections are referred to as the road that our moving truck will drive on. In this example, this truck is the Internet Protocol. It's the one that is doing the heavy lifting and moving that data across the network. Just as we might pack up items or objects in a room into a box and put that box onto the moving truck, we do effectively the same thing with our application data. We package that information into a virtual moving box, and we put that moving box onto the truck, which in this case would be IP. So now we have a highway, which would be our network. We have a moving truck, which would be the Internet Protocol. We have boxes within that moving truck. We commonly refer to those boxes as the TCP or UDP protocol. And then inside of those boxes is application data that we need to transfer from one device to another. This process of encapsulating data within other protocols, which are then encapsulated within even larger protocols, is a fundamental process when we describe the transfer of data across the network. If we were to visualize the Ethernet frame that we use on our networks, it would look a lot like the one that we have on our screen now. We have a client that is communicating to a server, and information is being sent between those two devices. You'll notice there is an Ethernet payload in the middle of this frame. At the beginning of the frame is an Ethernet header, and at the end of the frame is an Ethernet trailer. If we were to provide a little more detail about what's inside of that Ethernet payload, you would see there would be some IP information, and within the IP header, the rest of the packet has the IP payload. Deconstructing this further, you can see that the IP payload consists of a TCP or UDP header, and inside of that part of the packet is the TCP or UDP payload. So if we were to look at a protocol decode of a single frame on our Ethernet network, we would see an Ethernet header. Inside that Ethernet header would be an IP header. Inside the IP header might be a TCP header, which would hold HTTP or website data. And then finally, at the end of the frame, we would have the Ethernet trailer. You'll notice that inside of that IP header, we had either TCP data or UDP data. So it might be useful to break out those two protocols and describe what the differences might be. Both of these protocols are very similar in their function. They're obviously moving data from one device to another, but the internals of how those protocols work are a bit different between the two, and an application will use the one that makes sense for its particular function. If you recall our video on the OSI model, you'll remember that TCP and UDP operate at OSI layer 4, or the transport layer. It's in this layer that we're able to send many different applications across the network simultaneously between exactly the same devices. We refer to this as multiplexing, and it describes the efficient process of transferring multiple applications simultaneously between multiple devices. Let's first look at TCP, or the Transmission Control Protocol. We refer to TCP as a connection-oriented protocol. That's because there is a formal process to set up the communication between two devices, and when that communication is done, there is a formal process to tear down that particular session. One feature that makes TCP different than UDP is the ability for a station to acknowledge that it has received data. We refer to this as a reliable delivery method. That's because sending data to another device will always result in an acknowledgement that that device has successfully received that data. This means the sending station will always know if information was properly delivered to the destination. This also means that the sending device can recover from any type of errors. If it doesn't receive an acknowledgement, it can assume that that information was not received by the destination device, and it will resend that information to ensure that it is able to receive all of the data. These packets are also numbered, so the receiving device will also be able to request anything that may have been lost along the way without having to resend multiple packets and recreate that data. Having this conversation between these two devices about how well traffic is able to be transferred allows the receiving station to configure flow control. This describes the process of the receiving station telling the sending device to either send data slower or speed up the transmission. UDP, or the User Datagram Protocol, is a much more bare-bones protocol. There's no formal process to set up a session between two devices, and no formal process then to tear down that session. We refer to this as a connectionless communication because there's no setup or warning that information may be inbound to a particular device. This means that we can send packet after packet of UDP data from one device to another, and no UDP acknowledgement is ever sent back to the originating device. We refer to this type of communication as unreliable, not because there is a higher chance of having problems communicating. In fact, UDP and TCP are able to communicate in exactly the same way with exactly the same probability of getting that information sent across the network. The difference is that we don't receive any acknowledgements when using UDP, so we can't guarantee that that information has truly been delivered. And since there's no acknowledgement and no notification that anything has been delivered, there's no way to perform any type of error recovery or be able to retransmit portions of the data which may have not been received. And because there's no ongoing communication back and forth between these two devices using UDP, there's no way to configure any type of flow control. The receiving station can't reach out and tell the sending station to speed up or slow down because nothing is ever sent back to the originating station. Now that we've loaded our boxes of data into our IP truck, we need to tell the truck driver where to take this information. And in the moving truck, we do this by giving the truck driver the destination address for the truck. In the world of IP, we give it a destination IP address. But of course, in a house, we have many different rooms that we might deliver these boxes to. Some boxes might be for the bedroom, others might be for the kitchen or bathroom. And when we bring the box into the house, we can take that box directly to the appropriate room. IP works in a similar way, where each box of data is provided a room name. And in the world of IP, it's provided via a TCP or UDP port number. Instead of having bedroom, living room, kitchen, or bath, there will be a number associated with that data, such as port 80, port 443, port 123, or port 25. When those TCP or UDP boxes arrive at the house, we simply look at the TCP or UDP port number and deliver that box to the appropriate application running on that server. If you were to look at a protocol decode of IPv4 traffic being sent over the network, you would see a set of IPv4 sockets for the server and for the client. This socket is a combination of data that consists of an IP address, a protocol, which would be TCP or UDP, and then there would be an application port number. For the server side, there would be a server application port number, and on the client side, there's a client port number. Once both sides of the conversation know what the IP address is, they know the protocol, and they know the port numbers of both the server and the client, we're able to send information properly between both devices to the appropriate application. If you were to look at well-known applications that are using TCP or UDP, you'll notice that many of those port numbers are from 0 through 1023. We refer to these as non-ephemeral ports, which means they are permanent port numbers. If we need to communicate to a web server, we're almost always going to use port 80 and port 443. Those are very common and permanent port numbers that you would find on almost any web server. On the client side, we tend to use port numbers on a temporary basis. We refer to those as ephemeral ports. Those are ports that are commonly associated with 1024 through 65,535. Although it's very common to find applications using non-ephemeral ports and the clients using ephemeral ports, the reality is any device can use any port number that it would like to. And although we commonly associate servers with non-ephemeral ports and clients with ephemeral ports, the reality is you could find application servers using port numbers within the ephemeral port range. So you can see this is not a hard and fast rule, but instead broadly describes the way that we use these port numbers on our networks. Anytime you see a TCP or UDP port, it can be a number between 0 and 65,535. That is a lot of room to be able to use different port numbers for different applications. Most servers, as we mentioned, will use non-ephemeral or non-temporary port numbers, but that's not always the case, and you could see applications using port numbers that are in the ephemeral port range. Remember that changing port numbers is simply a way to designate what room inside of the house will be receiving that particular data. It's used for communication, and this is not a security mechanism. You'll still need a firewall to decide whether traffic is truly allowed or disallowed through the network, and simply changing a port number doesn't increase or decrease any type of network security. If you're connecting to a web server, your browser automatically knows that it should be looking for port 80 or port 443 and will use those ports by default. If you change the port numbers of the server, your browser will no longer know how to connect to that web server. That's because we expect web servers to always use port 80 or always use port 443. These are well-known port numbers, and if you change those port numbers, you'll have to make sure that all of the clients use the new port number instead of what normally would be well-known. Also keep in mind that TCP port numbers are different than UDP port numbers. Although both of them can be between 0 and 65,535, TCP port 80 is a different port number than UDP port 80, and you could theoretically use two different applications with both of those protocols at the same time. Here's how this might be practically configured on our network. In this example, we have a server. Its IP address is 10.0.0.2, and we have a client at 10.0.0.1. These two devices are communicating across the network using 3 different applications. The server has a web server at TCP port 80, a voice over IP server at UDP port 5004, and it's also providing email services over TCP port 143. This means the client can communicate to the server with all 3 of those applications simultaneously because they all have different TCP and UDP port numbers. If we were to then look at the IP data that was being sent on a single communication, you can see that this IP address of 10.0.0.1, our client, is sending information to this 10.0.0.2 address. You'll also notice that the client is using a temporary port number for this session. In this case, the randomized temporary port number is port 3000. And this device is communicating to the web server, so it's using the well-known port number of port 80. And you can also see there is HTTP data contained within this packet as well. This data is received by the server, and when the server needs to send information back to the client, it simply reverses the TCP source port and destination port and the IP source and destination to be able to send that information back to where the original request was sent. This same process occurs if you're using voice over IP data. In this case, the client is using a source port of 7100, and the UDP destination port would be 5004, which would be the voice over IP service on that server. And for email data, the source port that's being used is a random number of 4407, and the destination port is the well-known port for email, port 143. So every device on the network that is communicating via IP is using this fundamental process to transfer data. This allows us to scale up into a worldwide internet and be able to send data between 2 devices anywhere in the world.
Get fresh groceries delivered to your door with Kroger Delivery proudly serving King Soopers.
Wash it smells so clean. Deli rinse and refresh, it's a dream.
As a networking professional, you may be asked to configure port numbers associated with a particular application. So in this video, we'll look at the well-known port numbers associated with those apps. We'll start with a generic form of file transfer that's used across many different operating systems. This is FTP, or the File Transfer Protocol. This is a very common and generic form of file transfer that can be used on Linux, Windows, Mac OS, and practically any other operating system. Unlike many applications that use a single port number to communicate, FTP is configured to use 1 or 2 different port numbers, specifically TCP port 20 and TCP port 21. TCP port 20 is commonly associated with the file transfer process itself, and port 21 is commonly sent to send control information between one device and another. FTP has an authentication method, so you can use usernames and passwords, and when you're transferring information, you can choose to not only transfer the file, you can list information in a particular directory, add different files, delete, rename, and perform other types of file maintenance. TCP port 22 is commonly associated with SSH, or Secure Shell. This is a way to communicate to a remote device from a console. So you have this text-based front end, and you're able to configure and manage this device over this text-based command line interface. An important characteristic of SSH is the secure part of SSH, because all of the communication between your device and that remote device is all sent across the network in encrypted form. Well, if there's encryption being used with Secure Shell, it would be great if we could use encryption with our file transfer protocol. So, of course, there is a version of the FTP called Secure FTP, or SFTP. This allows us to transfer files from one device to another, and that entire communication across the network is all encrypted by default. Interestingly enough, Secure FTP is really using the SSH protocol to be able to perform this encryption. So SSH and SFTP use the same port number of TCP port 22. And just like our FTP protocol that allows us to perform file management of that device, we can also perform the same file management using the secure version of FTP. So you can view the directories, you can make changes to the directory names, you can modify files, delete information, and perform all of the normal file management from the Secure FTP application. Both Secure Shell and Secure FTP have that foundation of SSH as the underlying protocol, so not only does Secure Shell allow you that remote terminal communication, you can also have remote file transfer communication, and all of that communication will be encrypted using the SSH protocol over TCP port 22. Before we had encryption over SSH or Secure Shell, we used a non-encrypted form of terminal communication referred to as Telnet. This stands for Telecommunication Network, and it commonly uses TCP port 23. Visually, this looks almost identical to what we use with Secure Shell. The difference, however, is the communication that we're sending between our device and the remote station is all being sent in the clear. There's no encryption that's taking place across the network. This means that someone could potentially capture those packets and view everything that's being sent back and forth over the network, including your login credentials. It's for this reason that you don't commonly see Telnet being used on our network, and instead we'll use SSH to ensure that all of this communication will always be encrypted. Another important application on our network is the use of email. And of course, we need protocols to be able to transfer these emails from one email server to another. To be able to do that, we use SMTP, or the Simple Mail Transfer Protocol. SMTP is commonly associated with server-to-server email transfers using TCP port 25. All of this traffic sent over TCP port 25 is sent in the clear, or in plain text. There's no encryption that's automatically configured when using TCP port 25. That's why many SMTP servers will use TCP port 587, which is SMTP using TLS encryption, or the transport layer security. SMTP is also used from client devices that are sending email messages, and it's often sending those to a mail server using this SMTP protocol. For receiving email messages and being able to manage your email inbox, we often use other protocols such as IMAP or POP3. So anytime that you are sending email or you're transferring email between email servers, you're probably using SMTP or the Simple Mail Transfer Protocol. We don't often memorize the IP address of devices that we communicate with. Instead, we use the Fully Qualified Domain Name, or FQDN. And the way that we translate between the fully qualified domain name and the IP address is we use a DNS server, and that stands for Domain Name System. DNS commonly uses UDP port 53 to be able to perform this name query. So we'll ask a DNS server what the IP address of www.professormesser.com might be, and it will respond back with the IP address that your device can use to communicate to that server. For those small queries, we commonly use UDP port 53, but if there's a large transfer of data from one DNS server to another, we commonly would use TCP port 53. These DNS servers are obviously very critical resources because without them, we wouldn't be able to communicate to servers such as ProfessorMesser.com. This is also a very common protocol to find on the network, and if you take a packet capture, you're almost guaranteed to capture some type of DNS traffic. We've become very accustomed to simply plugging into a network or connecting to a wireless network and automatically being able to communicate across that network. But behind the scenes, there is an automatic IP configuration process using DHCP, or the Dynamic Host Configuration Protocol. This is the protocol that allows us to automatically configure IP address settings for anyone that connects to the network. By default, DHCP uses UDP port 67 and UDP port 68. To be able to use DHCP, we need a DHCP server. At home, we commonly use a DHCP server that's integrated into an existing wireless router, but in an enterprise network, there are often standalone DHCP servers. We usually configure a pool of IP addresses on DHCP, and anyone who connects to the network will be automatically assigned an IP address from this available pool of addresses. There's also a lease time associated with this IP address, so you're only able to use that IP address for a certain amount of time, and if you are still using that address at the end of the leasing period, you can choose to renew that lease with the DHCP server. We can also configure certain devices to always receive the same IP address every time they connect to the network, and we associate that IP address with the MAC address of that device. We configure that in the DHCP server. That's often referred to as a DHCP reservation. All of this communication that occurs across the network for DHCP will almost always use UDP port 67 and UDP port 68. We talked earlier about the FTP, or file transfer protocol, that we use to send files from one device to another. And we described the process of authentication and the many different management functions associated with FTP. But what if you just needed to transfer a small bit of configuration information from one device to another? You don't need to view the name of a directory or change any of the file names. You simply need to transfer a small amount of information very, very quickly. To be able to do that, you might use TFTP, or the Trivial File Transfer Protocol, and by default it uses UDP port 69. You'll often see TFTP used for very simple file transfers. Usually this is something that doesn't require any type of authentication or login process, so it may be something like a voice over IP device that has no IP address and no configuration. And when you plug it into the network, it is powered on using power over Ethernet. It uses DHCP to get an IP address, and then it uses TFTP to be able to download the latest configuration file from the server. This is a quick and easy process. It transfers data without any extra overhead. It's able to do that very efficiently and very quickly using UDP port 69.
Nature's Bounty helps you grow thicker, fuller hair with 1 pill a day of advanced hair complex. It's in your nature to grow.
HTTPS. This stands for Hypertext Transfer Protocol, and it's a communication that is commonly associated with browser-based communication. If the information between your browser and the web server is being sent in the clear without any type of encryption, it's commonly using TCP port 80. If you need to perform encryption of that data, and that is probably the default for most websites that you'll visit these days, it is using SSL, that stands for Secure Sockets Layer, or a newer version of SSL referred to as TLS, or Transport Layer Security. If this is encrypted data, then it's probably using TCP port 443, which is sending HTTPS for secure. Another thing you may notice with the devices that are connected to the network is they all tend to have the correct time and date, down to the second level. We're able to do that through an automated process called NTP, or the Network Time Protocol. Every device on the network, operating systems, routers, switches, and any other device, can use NTP to stay synchronized with their clock across all of those different devices. By default, NTP uses UDP port 123. Being able to synchronize these clocks is more than simply a convenience. In fact, it can be a very critical part of synchronizing log files between very diverse devices. This allows us to go back in time and piece together communications, even though that communication occurred on many different devices. This is a process that usually occurs automatically behind the scenes, and many devices...
All right, everybody, let's do our last break before lunch. Let's hit up 10 minutes. See you when you get back.
You might also be able to configure this process. Maybe you'd like a device to update its clock every hour, or maybe simply updating once a day is sufficient. This is also a very accurate way to keep these clocks in synchronization. And usually we get about a 1 millisecond difference between devices that are all on the same network. This provides a level of granularity that's sufficient for most applications, and it's something that occurs automatically using UDP port 123 and the Network Time Protocol. As a network professional, you'll be responsible for the uptime and availability of routers, switches, firewalls, and many other devices on the network. One way to manage those devices is through a protocol named SNMP, or the Simple Network Management Protocol. By default, SNMP uses UDP port 161 to query devices and receive information about how that device may be performing. For example, we might have a management station, and we might be querying a device to determine how much traffic has traversed that particular device over a certain amount of time. And then it can provide us with a summary of how much data has been transferred over that time frame. We can then store that data, create graphs, reports, and other information that allows us to manage that device. You might also find that different versions of SNMP may be used on your network. Version 1 of SNMP is the original version. This allows your management station to perform a single query to this device and receive a single response, and all of this is sent over the network in the clear with no encryption. Version 2 of SNMP allowed for bulk transfers, so we can ask for many different variables from this device and receive a large group of data from that device, which simplified the network communication and made it much more efficient. But it didn't provide any type of encryption. All of this information is still being sent across the network in the clear. A more modern version of SNMP is what you may commonly find on your network today, which is version 3. This is a more secure standard for SNMP, which allows message integrity, authentication, and encryption of the SNMP data. One of the things you'll find with this default use of SNMP is the management station is interactively making a query and then receiving a response for that query. So it's up to the management station to initiate that communication. But it would be nice if these devices could identify problems and proactively send that information down to the management station. We can do that by using a feature of SNMP called an SNMP trap. This allows these notifications to be sent directly from these devices using UDP port 162. Many organizations may have hundreds or thousands of devices on their network, and it may be a challenge to be able to keep track of what devices are on the network, what users are connecting to those devices, and how the relationship might be between the user and the device. We're able to maintain a database of all of these devices and all of these users through a protocol named LDAP. LDAP stands for Lightweight Directory Access Protocol, and it commonly uses TCP port 389. LDAP allows us to very easily query these databases and retrieve information that we may have stored. There's also a secure version of LDAP called LDAP Secure. It uses TCP port 636. LDAP uses a hierarchical structure to be able to lay out the network and the devices. This is a graphical view of an LDAP database. It starts with the root of the database, which is an organization. In this case, the organization is Messer Studios. We've also grouped together like devices into organizational units. There is a production OU, a support OU, and an engineering OU. Within those organizational units, there may be common named devices. For example, there may be users such as Jack and Daniel, or there may be a database or storage device named TechDocs. We're able to organize and access these devices through this structure, making it a very common and simplified way of gaining access to this data. Microsoft Windows has some very unique features when it comes to data transfer. Microsoft stores information on the network in a file share. You can also share printers through Microsoft's operating systems, and there's also authentication built into this entire process. To be able to provide all of this functionality, there is a specialized protocol named SMB, or Server Message Block, to be able to share files, share printers, or authenticate to the network. You might also see this referred to as CIFS, or the Common Internet File System. SMB is integrated into Windows itself. You don't need to add additional software. There's no additional FTP or SFTP process. Instead, built into the Windows Explorer or the File Explorer within Microsoft Windows is the SMB functionality that allows us to access file shares, print to remote printers, lock different files on the network, and provide processes for authentication and permissions for all of that data. Early versions of Microsoft Windows used the NetBIOS protocol to be able to facilitate this communication. But most modern versions of Microsoft Windows communicate directly across the network using IP, and TCP port 445 is the one that is usually associated with Server Message Block, or SMB. As a network professional, you'll find that you are constantly referring to logs that are being kept on your routers, your switches, your firewalls, your servers, and almost any other device that's connected to the network. One challenge is being able to consolidate all of these different log files to one single location. And there is a standardized protocol for transferring these log files called syslog. Syslog commonly uses UDP port 514 to be able to transfer this log data across the network. You'll often use syslog in conjunction with a security information and event manager, or a SIEM. This is a consolidation point where you can have all of your log files transferred into one single consolidated database. So if you're using syslog and transferring that over UDP port 514, then you're probably transferring it to a very large drive array or some other device where you can collect that log information over an extended period of time.
Thales is a global leader in cybersecurity, securing what matters most.
We store a lot of very diverse information on our databases, but fortunately there is a very common form of storage and retrieval for those databases referred to as a structured query language, or SQL. Some people refer to this as SQL. This SQL database uses a standard language that you can use to be able to query and retrieve information from that database. Microsoft has its own form of SQL database called the Microsoft SQL Server, or MS SQL. Stands for Microsoft Structured Query Language, and very commonly uses TCP port 1433. There are other types of SQL databases you might find on your network, and they usually use different port numbers. So if you see TCP port 1433, then you're probably using a Microsoft SQL Server. Many of us start on the help desk to be able to provide support for our end users. And one way that we're able to view the remote desktop of those devices is through the use of RDP, or the Remote Desktop Protocol. RDP uses by default TCP port 3389 to be able to view that remote desktop. The Remote Desktop Protocol is commonly associated with a service that's running on a Windows device. But fortunately, there are many clients that can use RDP to connect to those Windows devices, so it's not unusual to find RDP clients for Windows, Mac OS, Linux, iPhone, Android, and many other operating systems. There are many different protocols used for voice over IP. One of the most popular is SIP. This is the Session Initiation Protocol, and it commonly uses TCP port 5060 and TCP port 5061. SIP is commonly used as the control protocol that we use when we pick up the phone, we dial the number, it initiates the phone call, and then when the phone call is over, it disconnects the session. You might also see SIP being used for extensions of voice over IP that provide video conferencing, instant messaging, and even file transfers. All of this takes place using SIP over TCP port 5060 and TCP port 5061. There will be many times as a network professional when you'd like to know if a device is on the network and operating. And one protocol that can provide you with that is ICMP. This is the Internet Control Message Protocol. You can think of this as a way to check in with that device, very similar to sending a text message to see if you get a response back from someone. ICMP is another protocol carried by IP, but it doesn't use TCP or UDP. Instead, ICMP is its own protocol. Although ICMP can be used for a number of administrative tasks, it's most commonly associated with a way to send a message to a device to see if it's alive and operating on the network and see if you can get a response back from that device. Whenever you use the ping command to ping an IP address on the network, it's using ICMP to provide that ping functionality. But ICMP can also provide you with information about other things that may be happening on the network. For example, if you're trying to access a network that is not accessible from your location, ICMP will give you a message that that network is not reachable. Or ICMP can tell you that the time to live that's inside of data that you've sent has expired and it's received an ICMP time exceeded message from that device. Another common protocol on our network is GRE, or the Generic Routing Encapsulation Protocol. If you're creating a tunnel between two endpoints, this is commonly done with VPNs, for example, you're creating this tunnel using GRE. This allows us to encapsulate information within an IP packet send it across this GRE tunnel, and decapsulate it on the other side. This does not, however, provide encryption of this data. We'll need to provide additional VPN protocols to encrypt the data that we are encapsulating in a GRE tunnel. These VPN protocols are referred to as virtual private network protocols, and it's very common to use these VPN protocols to encrypt or protect any data being sent across one of those tunnels. It's often common to use a purpose-built appliance to provide this encryption and decryption process at the central point. We refer to this as a VPN concentrator. Sometimes this is a standalone unit. It's very often integrated into an existing firewall that's connected to the network. These concentrators are often hardware devices with specialized encryption hardware built into the device to add efficiency and throughput. But if you have a limited number of users, it's also possible to use your VPN concentrator as software in an operating system. This is a common site-to-site VPN configuration where a corporate network may be connected to a remote site over a public network such as the internet. We'll have VPN concentrators, which are usually firewalls or routers. Those are connecting these two sites together over the internet, but all of this traffic that's being sent across that public internet is being encrypted using this VPN technology. One of the popular protocols used to provide that level of encryption over those tunnels is IPsec. This stands for Internet Protocol Security, and it's one of the most popular ways to encrypt data being sent across these VPNs. Not only does IPsec provide encryption for confidentiality, it can also provide digital signatures of every packet, which includes integrity and anti-replay functionality. This is also a very common protocol, and it can be used across many different manufacturers' devices. For example, you might have a firewall from one manufacturer on one side of a VPN tunnel, and a firewall from a completely different manufacturer on the other side of the VPN tunnel. Because IPsec is such a standard protocol, those two firewalls can easily connect to each other and transfer information over that IPsec tunnel.
Spending time with the ones you love is priceless. That's why Kroger Delivery, proudly serving King Soopers, makes grocery shopping effortless.
When you're using IPsec, there are commonly two primary protocols that are in use. One is the authentication header, or AH, and the other is the encapsulation security payload, or ESP. In order for IPsec to be able to send this encrypted data across the network, we first need to create this tunnel. And we do this by performing a series of steps prior to sending any data. Those steps are referred to as the Internet Key Exchange, or IKE. Internet Key Exchange allows both sides of the conversation to agree on the encryption and decryption keys that will be used for the duration of that VPN tunnel. We refer to this agreement as a security association, or an SA. There are two phases to this key exchange process. The first phase commonly uses Diffie-Hellman to create a shared secret key for both sides of the conversation. This usually operates using UDP port 500, and we refer to this as ISACAMP. This is the Internet Security Association and Key Management Protocol. In phase 2, we coordinate which ciphers should be used for the encryption and the key sizes that would be appropriate, and it negotiates both the inbound and outbound security association to be used for this IPsec tunnel. So visually with phase 1, we're building the ISACAMP tunnel over UDP port 500. In phase 2, we're including the encrypted data over the encapsulation security payload, or ESP tunnel. This gives us the foundation we need to be able to send this encrypted data over the IPsec tunnel. If you're building your own IPsec tunnel, you may be asked whether you'd like to use transport mode or tunnel mode. Both of these work differently and will protect data in different ways. Let's take the original packet, which includes an IP header and some data within that IP packet. We would like to send that over an IPsec tunnel. If we use transport mode to send this IPsec data, we're going to insert an IPsec header between the IP header and the data. All of that is going to be in the clear. Anything within the data portion of that IP packet will be encrypted, and then the IPsec trailer is put at the end of the packet. Notice that the original IP header is not encrypted when using transport mode. And if someone does capture this data, they'll be able to see the original IP header and be able to understand where this traffic is intended to go, even if they can't see the encrypted data within the packet. A much more secure method of using an IPsec tunnel is tunnel mode. In tunnel mode, the original IP header and data is all encrypted, and even if you capture this data, you'll never know what the original destination is for this data. Tunnel mode adds a new IP header, which includes the destination of the IPsec concentrator and includes the same IPsec headers and IPsec trailers that we saw in transport mode. It's probably not too surprising that most implementations of IPsec are going to use the tunnel mode to ensure the highest level of encryption of your original data. Earlier, we mentioned the two protocols that you commonly see associated with IPsec. One of those protocols is the authentication header, or AH. AH is used to validate the information that you're receiving over an IPsec tunnel. And if you're only using authentication header mode, you're sending all of this information over the network in the clear, but you're including some additional hashing to ensure the integrity of this data. However, in most cases, we want to be able to encrypt the data that we're sending over the IPsec tunnel, and for that reason, we'll use Encapsulation Security Payload, or ESP. This protocol is going to encrypt that original data and encrypt the trailer that we're associating with ESP, and then put around this packet a new IP header, an ESP header, and an integrity check value at the end of the packet. This is going to encrypt all of your original data, but also provide the authentication that you need to ensure that the data is received properly on the other side.
When Verizon gives you a free phone on any plan, you use AI a lot.
Gemini, show me the concealer.
The long, thin tube in the middle.
But hey, it's the new Google Pixel 10 Pro.
A unicast is one of the more popular ways of sending information across the network. It is when one station sends information directly to another station. This is a one-to-one relationship, and nothing within that conversation is ever sent to anyone else on the network. If you need two devices to be able to send information to each other and no other device on the network will be involved with that conversation, then you're probably using a unicast. So anytime you're connecting to a website, you're transferring files, or you're checking your email, it's probably all taking place with a unicast communication. This one-to-one relationship is also one of the disadvantages of unicast, especially if you need to send information to many people simultaneously. With unicast, you would have to build separate one-to-one communications with all of those individuals, and you would
All right,
have
we
to
got some
send
time before
separate
lunch, so I'm
data
gonna hit
for
you
each
with
individual
IP
device.
address and
But
cider.
for single communication between you
Give
and
you time
another
to work on
device, whether you're using IPv4 or IPv6, you're probably going to use unicast. To be able to efficiently send data to multiple devices at the same time, then you'll probably want to use multicast. Unicast is a one-to-many of many communication, so when you send information out, it is sent to multiple recipients all simultaneously. These recipients are usually subscribing to your multicast feed. So if someone is trying to receive multimedia, they're receiving stock exchange information, or maybe a device is sending out routing updates, you can send those out via multicast addresses. Multicast is relatively specialized, and it requires that equipment understand and recognize how to deal with multicast communication. This is why we don't use multicast when we're sending information across to a different network or even within a very large network. But we do use multicast quite a bit with IPv4 and IPv6, and in the right environment, it can be a very efficient way to send and receive traffic.
You can submit your answers in the
One
chat.
device needs to send to many devices. Anycast is used when one device needs to send to one of many devices. This is where a single destination IP address may be sent to one of many different devices that are on the network, and it's something
That second one says, what are the two slashes you'll be using
IPv6. In this scenario,
for each LAN?
the devices that are receiving the Anycast communication are all configured in very similar ways. This allows the originating device to simply send data to the unicast address, and whatever device is closest is going to receive that traffic. A good use case for Anycast would be something like Anycast DNS, where a DNS query can be sent out on the network, and the closest data center will be able to respond to that anycast DNS request. And if you want to send a frame to everyone who's on your network, then you'll want to send a broadcast. This is a one-to-all relationship where a single packet is sent out and everyone on the network receives that single packet. Fortunately, the scope of this is limited to your local broadcast domain, so there's no way to send a broadcast frame from your local network and somehow have that frame appear everywhere else on the internet. This is a type of communication that's best fit for something like routing updates or ARP requests.
I dropped a snapshot from yesterday to help you.
Commonly find with IPv4, we decided with IPv6 to remove broadcast completely and go to a multicast form of communication instead. If you connect to a network at work or at home, then you're probably very familiar with wireless networks. You may also notice that no matter where you go with your wireless device and whatever network you connect to, you always seem to have the required connectivity. This is because there is an international standard for wireless network that's managed by the Institute of Electrical and Electronics Engineering, or the IEEE. The IEEE standard for wireless networks is in their standards committee for the 802 series, specifically 802.11. So anytime you hear anyone mention 802.11, they're referring to the standards associated with wireless networks. Another interesting characteristic of wireless networks is that they are constantly evolving and constantly changing. So you'll want to check in with the IEEE standards to see which type of wireless network you're using. There's another organization involved with wireless networking called the Wi-Fi Alliance. You'll notice there's a Wi-Fi trademark logo on every device that the Wi-Fi Alliance has tested. This ensures interoperability with the standards that are set by the IEEE. In the past, we used to refer to these wireless networks with their standards name. For example, 802.11b or 802.11ax. We've recently added additional names to these standards to make them a little easier to understand for everyone who's connecting to these wireless networks. For example, if you're using the 6th generation of Wi-Fi networks, then you're connecting to an 802.11ax network. But we also refer to this network as Wi-Fi 6. This chart shows a list of all of the major Wi-Fi standards listed by their 802.11 name. I've also included the new generational name for those standards, the frequencies they happen to use, and the maximum theoretical link rate for each of those standards. The first three of these standards, 802.11a, b, and g, are rarely used today, and we did not formally set a generation name to those, although you could colloquially refer to these as Wi-Fi 1, Wi-Fi 2, and Wi-Fi 3. The newer standards of Wi-Fi 4 through Wi-Fi 7 are covered through the standards of 802.11n through 802.11be. You'll also notice there's a difference on the type of frequencies that are used for each of these standards, and most of these refer to the 2.4 gigahertz, the 5 gigahertz, and the 6 gigahertz ranges. There are a number of differences on how these wireless standards can be implemented. There might be a different number of antennas or a different number of radios, and that accounts for the differences in the theoretical link rates that you see in this final column. Notice as we've introduced newer standards of wireless networks, that we've also increased the overall link rate of those networks. Well, we use more than our local 802.11 networks for wireless networking. If you have a mobile phone or a mobile tablet, then you're probably using a wireless provider's network that uses 4G, LTE, or 5G technologies. LTE stands for long-term evolution. It is what we refer to as the 4G technology, and it was a conversion between different standards of GSM and CDMA into a single standard that every provider can use. These 4G networks supported download rates of approximately 150 megabits per second, and the improved version of LTE, which is LTE Advanced or LTE-A, supports download rates that double that to 300 megabits per second. A more modern version of mobile networking is the 5G
everybody doing okay so far?
Introduced in 2020. This greatly
Let me know if you need a
improves the
hint.
performance of wireless mobile networks, and with the right configuration, the goal will be to have 10 gigabits per second as the overall throughput. And in other implementations, you may see more reasonable speeds such as 100 to 900 megabits per second. 5G has dramatically changed the way we look at mobile connectivity.
The hint is,
especially since we're now able to get
because you're going to see that on the exam. I'm glad you asked. Variable length subnet mask, meaning you will pick a subnet that will fit the required IP addresses that you need.
This means we can transfer much more
Insider, so you can create. That's simply variable length subnet masking. You're choosing what you need to accommodate what you need, but leaving a little room if you have to.
There may be times when an organization might have a remote location that is not accessible through any type of traditional internet connectivity.
When you get into the exam room, on that piece of paper is a cheat sheet.
Known as satellite network.
You want to write this
You can
down.
add a satellite dish to a location and begin sending and receiving data from the satellite. This obviously
Because if you write that down,
complexity and the speeds of satellite networking.
I simply say, I need two 128s. I need two 128s. I need two 128s. If you write that, you got it. I need two 128s.
This means that if you have
And then you write the /25, you can build this out from anywhere. You can, all you need is that.
directly to the internet.
Does everybody understand that? I need two 128s. Once you write that in that /25, you'll know what to build out going this way. This is divisible by 2 going to the right, and this is multiplied by 2 going to the right.
Each conversation to and from the satellite took
The last one is just adding 128 to 64, 192 to 32, 224 to 16, and you can build the top chart. That's it. But if you have this written, you can answer any question on the exam as far as what should be where.
This means if anything does get between the satellite receiver and the satellite, then we may have a decrease of performance or lose connectivity altogether. For example, if a thunderstorm was to come through, we would suffer through what we call...
As a refresher, this is the bit position from the first octet, first position, all the way to the fourth octet, last position. So the slash is simply the bit position in the octet. The chart that we use to turn decimal to binary and binary back to decimal is the simple chart we've always been using, 128, 64, 16. That's the number of hosts you can put on the subnet you created. And simply the subnet mask is where all those addresses will live.
If you've connected your computer,
if you need to build subnets, you have to use the host block numbers to figure out those subnets you're building.
Able to connect to an Ethernet network. There are also many different types of Ethernet.
Meaning, if I wanted to, I could build 256 subnets.
Use the connectors at the end of these cables and the type of equipment that's required to connect.
That means I can go 1, 2, 3, 4. Here I have to build them out by 2. 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2 is 8. Get what I'm saying? Block size is 4. 4 plus 4 is 8. 8 plus 4 is 12. 12 plus 4 is 16. Get it? That's how you're building your 64 subnets. And don't forget to back that thing up.
IEEE is the Institute of Electrical.
See, here's the block sizes right over here. 0 to 32. 32 plus 32 is 64. Oh, I got to back up 1. 63. 32, back up 1. 31. There's your block. There's your... That's all I'm saying.
Ethernet network would be 1000 base T. This is a gigabit Ethernet network that operates over twisted pair copper cabling and operates at a speed of 1 gigabit per second. A newer version of that standard is the 10G base T, or the 10 gigabit Ethernet network. This also uses twisted pair copper cabling and operates at a speed of 10 gigabits per second. There are also Ethernet networks that use fiber optics. An example of that would be 1000 base SX, which is a gigabit Ethernet network that uses fiber optics and operates at a speed of 1 gigabit per second. This is just a sample of a few of the more popular Ethernet standards, but there are many Ethernet standards to choose from using different types of media and supporting different speeds. The IEEE has told us that the names they use for these standards don't necessarily correlate back to the details of the standard, but there's usually some information that we can discern from the name itself. For example, if we look at a standard such as 1000 base T, we should be able to break that term apart and determine what type of media and technology is used as part of that standard. For example, the number that's used in the name of the standard is often related to the speed of the standard itself. For example, the 1000 base T, that 1000 refers to the 1000 megabits per second, or 1 gigabit per second overall speed. If this standard started with 10G, then it would be related to a 10 gigabit per second network. We often see the term base in the name of the standard, and that's referring to the term baseband, which means there's a single frequency that is used to be able to send this data over the network. This is in contrast to something like broadband, which uses many different frequencies to be able to communicate across that network. And very often you can determine what type of media is associated with that standard by looking at the additional letters at the end of the standard. For example, 1000 base T has a T at the end, and we can assume that that T means that this is twisted pair copper. If there was an F at the end, it's very possible that this particular standard would use fiber optics. There may be additional letters at the end of the standard. For example, if there is an SX at the end of the standard, it might be referring to a short wavelength light that is sent over that
When you
fiber
think you
optic
got it,
connection.
submit your
As
answers
mentioned
in the
previously,
chat
IEEE tries to put the name and terms
for the
within
whole
the
problem.
standard so that it would be recognizable. That is not a requirement for the name of the standard itself. If you were interested in the details of what that standard supports, you would need to read the entire standard and not just look at the name of the standard.
Are the LANs under the same subnet? No, not for my example.
In stock and ready to ship free the next day. Zorro.com. Tools, parts, and supplies for your business.
Many of us are accustomed to using twisted pair copper, especially if we have networks that we use at home or even at our office. But you may occasionally have a need for fiber optic connectivity, and that fiber optic connectivity allows you to send traffic across the network using light. These are often used on very secure networks because it is very difficult to tap into a fiber optic connection without having some type of notification. This is very different than a copper-based network, which uses RF and is relatively easy to tap and gain information from. Fiber optics are also used over very long distances because the signal doesn't degrade as fast as a radio frequency might. So the same signal that we can send over 100 meters of a copper network might be able to be sent over kilometers if you were using fiber optics. And of course, light is not susceptible to any type of radio frequency interference. And if you're working in an environment where there is interference, you might want to use fiber optics to avoid any type of problem with your network. Just as there are many different standards and many different connectors for copper-based networks, there are also many different standards and connectors for fiber optic networks as well. So you'll want to check the configuration and documentation of your devices and make sure that the fiber optics that you're connecting are using the right type of fiber and the right type of connector. If we were to deconstruct a fiber optic cable, you would have something very similar to this. On one side of the cable is the light source. This might be an LED or a laser, and on the other side is the receiver. This LED is sending a light through this fiber optic. That consists of a core that is very reflective, and you can see the light bouncing through this core as it receives on the other side. Around the core is a low reflective cladding, and the entire fiber optic run is protected with a buffer coating around the outside. Here's the connector that's at the end of a fiber optic cable. It has a protective ferrule around the outside of the fiber, and if you look very closely at the very middle of this connection, you can just barely make out the core of the fiber that's in the middle. I'll highlight it here so that you can really see where that happens to be. Let's remove that highlight. Now you can start to see that discoloration where the fiber is connected on the end of that cable. We will generally install one of two different types of fiber optic cables. One is a multi-mode fiber and the other is a single mode fiber. Multi-mode fiber is commonly used for relatively short range communication. This would be up to around 2 kilometers in distance. And often this uses an inexpensive light source such as a light emitting diode or an LED. The core of the fiber optic is relatively large, certainly larger than the wavelength of the light, And because of that, the light itself can use different modes to be able to transmit through that fiber, and you can see the different modes bouncing off the edges of the fiber optic cable itself. Because there are different modes that are being communicated through this fiber, we refer to that as multi-mode fiber. If we're communicating over a much longer distance, we may want to use single-mode fiber. Some standards of fiber-based Ethernet can communicate up to 100 kilometers without a need to regenerate the signal. Because we're going a longer distance, we may be using a very bright and intense LED, or we may be using laser to be able to extend this signal much further. A single-mode fiber also has a smaller core, which can only allow a single mode of light to propagate through the fiber.
I wish we could actually catch up.
Whoa, you have a genie? Actually, I'm her. That's better. Now you can actually catch up over new DiGiorno wood-fired style pizza. Right from your oven. Perfectly crispy and airy crust you thought you could only get at a restaurant. Hey, we'll have to chase down that friend who always says he'll pay you back later. It's not delivery. It's new DiGiorno wood-fired style pizza.
Cabling is the foundation of everything we do in networking. Whether you're using a router, a switch, a wireless access point, or any other infrastructure device, cabling is going to be a critical part of that communication. Once the cabling is installed, it's very difficult to uninstall or remove that cabling and replace it with something else. So make sure you're using the right cabling for the right infrastructure. And even if your network happens to be mostly wireless, eventually that wireless connection will need to connect to a cable. So you need to make sure you have the right cables installed in the right place to be able to provide the best possible throughput of your network. One of the most common cable types is the twisted pair copper cable. This is something we use for practically all wired Ethernet connections, and it usually consists of multiple wires twisted together within a single sheath. You'll often see that the cables themselves are paired together. That's because there's often one type of signal on one of the wires and a reverse of that signal on the other wire. You may see this written as transmit plus or transmit minus, or receive plus and receive minus. The reason that we have the same signal being sent in different forms is so that we can recognize and correct if there happens to be any type of interference. This twist in these two wires means that at least one of these wires will always be moving away from interference. This allows us to compare these signals on the receiving end to determine what the actual signal should look like. Another interesting part is that the different cable pairs have different twist rates. So if you look very carefully at an individual cable, you'll notice that some pairs of cables are twisted much tighter than other pairs. One common misnomer that I often hear about cables is that a certain cable has a particular speed. But in reality, the cable doesn't have any speed at all. The copper is literally just sitting there in the cable. The cable itself is supporting a signal, and that signal is allowing us to send a certain amount of data over that particular type of connection. The specific Ethernet standard that you're sending over that wire determines just how much data you'll be able to move across that particular cable. If you're ever wondering what type of cable you should be using for the type of Ethernet network that you have, you should go back to the 802.3 standards. Those standards will specify the minimum cable type that's allowed for that particular standard, and it will specify the type of signal and the total throughput expected over that cable. To be able to easily determine the type of cable that's appropriate for a specific Ethernet standard, we've created a set of standards for the cables themselves. We refer to these standards as a category of cable. For example, you might find category 5, category 6, or category 7. If you check the Ethernet standard, it will specify the minimum category of cable that is required for that particular standard. For example, if you're using 1000 base T, you can look at the 1000 base T standards from the IEEE, and it will tell you that the minimum cable category for that specific Ethernet standard is a category 5 cable. If you install category 5 cable or anything above category 5, it will work properly with the 1000 base T standard. Although twisted pair wiring is very common for our local area networks, another type of Ethernet cable that's very often used is a coaxial cable. This describes a cable where two or more forms within that cable share a common axis. For example, you can see the single wire conductor that's in the middle of this coaxial cable. There's also an insulator, a shielding, and a jacket that are also sharing that same axis. One common type of coaxial cable, especially on our Ethernet and internet connections, is an RG6 cable. If you have a cable modem or you're bringing in a cable modem connection into your data center, it's probably being brought in on a coaxial cable. If we put two conductors inside,
Great question.
then we have a twin axis.
So when we're coming down to reserve out of your pool of addresses, all I need you to do is reserve those static IP addresses, meaning the start of the addresses you want to use to the end of those 5 addresses you'd like to use out of your pool. Those are your reserved addresses. They will never be given out when people want to join a network because they will always be assigned to a static item forever.
If you're at work and you look at the ceiling, you may notice that you're not seeing the actual ceiling of that floor. Instead, you're seeing a drop ceiling and something like acoustic tiles that is sitting above the actual ceiling. There is a space between this drop ceiling and the actual ceiling. We refer to that space as the plenum. Inside the plenum, we may have network cables, there might be heat sensors, you might have cables for power.
The end of the question? Or which one?
Yeah, the end of the question. Inside the plenum as well. In some environments, there may be a drop ceiling, and above the drop ceiling may be ductwork where all of the air supply happens to flow. You may have air supplied as part of a heating or cooling system in that ductwork, and there may be return air that's using additional ductwork to go back to that heating or cooling system. Since a plenum...
Now let me clarify with VLSM, variable subnet mask. You don't have to have precisely the number of addresses that you need, but if it fits into there, cool. If you have to bump up for another LAN or something, it's cool to have some built in. There's not a problem with that either. So, got to figure out which direction you want to go. What fits better?
Network cable type that produces a large amount of smoke or perhaps even hazardous fumes if it was to catch on fire. If this was in a plenum, that smoke and those fumes would be distributed to everyone in the building. This means we need to make sure we're installing the correct if we happen to be installing this.
All right, Leah, here we go.
Plenum. Ethernet cables have a jacket on the outside of the cable, and many of those Ethernet cables are manufactured with a polyvinyl chloride or PVC manufacturing. If you're putting this cable into a plenum, then you need a plenum-rated cable, and that cable is usually manufactured with a fluorinated ethylene polymer, FEP, or a low-smoke polyvinyl chloride, PVC. This plenum-rated cable is designed to be much safer in a fire than one that is not designed for a plenum. One challenge when working with plenum-rated cable is it may not be quite as flexible as
Okay, what slashes are you using
So if you're going around a lot
for
of
each one, each
turns,
LAN?
it may be a bit more of a challenge to install that cable into the plenum. So if you're installing cable into a new building or you're replacing cable in an existing building, make sure you see where that cable is being run and you use the correct type of cable for that location. Transceiver is a combination of two words, transmitter and receiver, and these are usually combined within the same piece of equipment or the same component. A transceiver allows for modularity. You may have a switch like this one. You can see there are a number of open interfaces in this switch. You slide in the transceiver that's appropriate for the media or the network type that you would like to use, and now that particular interface will operate with that particular configuration. So if you need a copper configuration for gigabit Ethernet, you slide in a copper gigabit Ethernet transceiver. Or if you need a fiber-based 10 gig connection, you slide in a 10 gig fiber.
If we were to troubleshoot, if I were to troubleshoot right now, we just set this up, one of these LANs will work, one won't.
Depending on what transceiver you are planning to use. There are different types of transceivers, different form factors.
It'll be dead air on one of your LANs.
Transceivers depending on the media. For example, if you are using an Ethernet switch, you need an Ethernet transceiver. If you're using a fiber channel switch, then you will need a fiber channel transceiver. You can't use fiber channel transceivers in an Ethernet switch or vice versa. This means you get to decide what media type works best for your configuration. If you need copper connections, you can use a copper transceiver, and if you need fiber connections, you can use a fiber transceiver. And if you need to change those connections midway through your installation, you can remove the copper transceiver and replace it with a fiber transceiver. This type of modularity often comes at an additional cost, but it does provide you with a way to plug into whatever network type you might need. One common transceiver type is the SFP type.
Okay, let's walk through your first example.
Form factor pluggable.
LAN number one, you say you want to use net ID 192.168.0.0 Class C address. Okay. So the one thing I asked, I'm assuming 25 is for the first one, correct?
Gigabit Ethernet, so that's 1 gigabit per second.
All right. So immediately my eyes are going to go to /25.
Form factor pluggable or SFP plus.
You want to put 128 hosts on the first one.
Oh, no, 25 is for the second one.
Okay. Up to 16 gigabits.
So 27 you want to use for the first one. So immediately when I ask the slash, I'm going to go here. /27, number of total IP addresses I can put on there is 32. Usable is 30.
First, the equipment is only 19 inches wide.
The question I asked is I need to have 25 devices. I also need 5 devices to have a static. Cool. So 2 ways she can do this. She can say I need a total of 30 devices, which still fits inside of 32. Right? Or she can say I have 25 devices, but 5 of them need to be able to have static addresses. So she can go 20 if she wanted to. Either way, she's still on a /27. So good job. So you can go either way with that. I just needed the requirements there. So as we go up, her block size is 32. So her net, so when she's looking, she's going to start with 0. She's going to go to 32 because that's her block size. Either way, if she said 30 or 20, they both fit inside right here. See that? They fit right in her pool. So she's like, okay, got it. My net ID .0, as I can see over here, she's got that right. Her broadcast ID 31, from what I can see, she's got that right. Her pool is 1 to actually 30. Okay.
I changed it because they were static, so I didn't know if that counted in the pool.
Gotcha. Makes sense. So your total pool will be 1 to 30, but you're going to reserve 5. So there's a reservation inside of the DHCP where you'll say, okay, what are your reserved addresses? Where are they going to start in? Now from there, you would put, they'll start at .26 and end at .30. Does that make sense? Okay, and I'm glad we're going through this because this is what you'll see on the exam. So she'll say my total reservation is 1 to 25 or 1 to 30, excuse me. When she goes into her reserve block, all she has to do is put the IP address of the starting address she wants to reserve and the ending address that she wants to reserve, and she's good. It all now knows they can't give those out. Okay. So that means her reserved address will be 5. Okay. Now the subnet mask.
Super helpful.
See if you can save money at
your computers.
Thank you.
Something's not talking. All these computers will not talk. Can you see why? Why?
When working with fiber optics, one of the first things you'll notice.
I put the wrong number at the end of the subnet mask. The first one's supposed to be .224, and the second one's supposed to be .128.
Bingo, you just solved the problem.
We also have other names
okay.
associated with this connector. One is
now here's the cool thing.
Because the connector itself.
One thing Leah figured out
You might also see this referred to as a standard.
She can have
connector,
two separate
although there's
LANs,
certainly other
and she can
types of fiber
use
connectors that you
the
might
same
use.
addresses
An
if
SC
she
connector
wants
simply
for two
pushes
separate
into the
LANs.
connection
Why?
and snaps in place with a lock. Once you have that connector in
Does it
place,
actually like
you don't
covers?
accidentally slip out of that connection.
Explain, Michael. I'm
Or you
sorry.
have to pull
Like
on connector to
the
unlock
slash
it,
that
and then it
covers
can be removed
the
from
IP
that
addresses
circuit.
she's gonna be using.
This is a common connector
Correct,
type, and
but
if you
there's
plug it
one
into
main
your
reason
connection in
why
Ethernet,
she
you're
can
probably using
use
some connections
the
that are
same
identified as
IP
SC.
range
The
for
connectors themselves
two
support
separate
individual fibers,
LANs.
but they're often combined together
Why?
into a pair because one of these is commonly used for transmit and the other is commonly used for receive.
Is it the subnet
Another
mask?
common fiber connector is the LC or local connector. This
I'm
is
gonna tell you why.
slightly smaller than an SC connector,
Ports,
and as you can see, it has a
switch
clip on the
ports
top to lock
separate
it in place once you put it into
domains.
the interface. This
So
also means
each
that it won't
port has
accidentally
a
get pulled out of
separate
an interface,
LAN.
and to remove it, you need to push down
So she
on the
can
clip. That will
configure
release the lock and allow
both
you to easily
ports,
remove it from the interface.
right? Because they're
Instead of
separate
local
LANs. They
connector,
will
you might
not,
also see this
there's no
referred to
way,
as a
there's
loose
no way
connector or a
you
local
cannot
connector.
have the same
The
IP
LC
address
connector can
range.
also be combined
Two
into
computers
a
cannot
like
share the
this.
same
You
IP
plug both
address
of them in
on one LAN.
simultaneously, and again, one is used
But
to
since she's
transmit
using
and the
two
other is used
separate
to receive.
LANs, they can
Another
use this
fiber on our list
the
is
same
the
IP
ST
address
connector
pool.
that stands
Does that
for
make sense?
straight tip. It uses a bayonet
Now in the
connector.
IT
You
world,
push it into an interface, give it
I
a
would
slight
have
twist,
asked
and it
Leah
is
to
locked in
separate
place.
these two.
This will not easily get removed from the interface unless you reverse that twist.
Well, it's the same pool, so this is what we would do. And I'm glad we're walking through this.
Rack, and there's a
There's a
large
little bit
number of
more
cables
seasoning
and
on
fiber.
top.
It can be very easy
So
to
for the first
accidentally
pool,
dislodge.
I would urge
That's
Leah to
why
do
we
this
have all of these
for her
different
first
locking
range, for her first LAN,
mechanisms.
192.168.1.
Here's a closer view of the SC connector. There's a protective ferrule around
For
the fiber,
LAN.
which you can barely see in this picture, and you can easily see the bayonet connector where you would plug it in and twist it in place so that it is locked.
For her
into that
second
interface.
one, I would go
One of the challenges with the connector types that we've seen so far is that those fiber connections take up a lot of real
for
estate.
LAN
It would be a lot
2.
more efficient if we could put more fiber into a smaller connection, and there is a connector type for that called the
Does that make
MPO,
sense?
which is multi-fiber push-on. Inside the MPO are 12 individual fibers that are contained in that
Who does not
single
understand what
connection.
I'm doing here?
This also has a lock.
Basically, Leah will use a naming convention
where you would push it in
and
place
separate her
pull it out
LANs.
slightly to unlock it from the interface. You might also see this
It's okay.
referred to as an MTP.
Can we just
That's
decide
what
to
is
change that
provided by
number at
Corning.
will? Yes,
They
you
refer
can.
to this as an
As long as they all live on the same
MTP
subnet.
connector. Here's a side
Okay.
view of the connector.
And
It
it's
has
a
this
Class C
lock on
address.
top, and the individual fibers
All right.
are these smaller dots.
So what you'll find is
Picture. If we look at it
naming
straight
conventions,
on,
IT administrators will go, because I can pick any numbers I want if it's a Class C address, as long as it falls in that private range, right? So that's what I would do. Right, so that means all of her IP addresses in that range for LAN 1 will be 192.168.1.0. It'll start there. On her second LAN, she just used 192.168.2.0. That's it. That way, if I ever had to troubleshoot and I kept my book where all my IP addresses belong and something was wrong, I know exactly which LAN to go to. Does that make sense? And this just takes practice, that's all. Who came up with something similar to Leah's?
So, let's see. We got.
Y'all were that far off, huh?
One common copper connector we use on our.
Michael said I got as far as /25 and 27, which is good. That's a good identifier, yes. I'm glad you got that far.
We only use two conductors inside of this connector.
Mr. T dropped something in. LAN number 1, 25 devices, synthetic, /27, private, net ID 224.
Connector with an analog telephone, but you'll also see RJ11 use
Net ID
cell connection, since those use exactly
224.
the same wires as a telephone connection.
That's probably your
Here's a better view
subnet
of the
mask, right?
RJ11 connector, and
Yep.
you can see the 6 positions.
Broadcast 31,
3, 4, 5,
pool 1 to,
6,
yep, 1 to
where we
35
are.
addresses,
But you
yep.
notice that there are the two conductors in the middle that are used
Broadcast
for
ID,
RJ11.
127.
If you're using an Ethernet connection, then you're using an
Who
RJ45
wants, so, okay, so you
connection.
designated
It stands for
where you want to
registered
start at with
jack
IP addresses, right?
45. It is an
Yeah.
8-position connector with.
But you have to use your block size to make sure you're falling within that range, okay, which he did, if you see it.
Connection.
Because he used
Slightly larger than an RJ11
a /25, you can put total available IP addresses is 128. If you back out 2, now you can fit 126 available addresses, and there it is right there, 1 to 126.
You can see that
Yep.
they're very similar in shape.
That means his broadcast ID is 127. His net ID is .0 though.
If you're using a cable modem connection, then you're
1.0.
probably bringing coax connection.
Because it's the beginning address.
To a cable modem, and the connector that you're probably
All right.
using is the F connector.
So it's cool. It still falls in there. 90 falls in that range comfortably. See my requirement? I need another LAN with 90 clients. So all you do is go down. I could fit 90 where? Oh, right there. Boom. That's how it became a /25.
Data over cable service
Oh,
interface specification.
James says he needs 30 computers or 20. Whichever way you wanted to hook it up, you'd be like, oh, does 20 or 30 fit in here? Oh, yep, fits right inside of there. So that's a /27.
That F connector connected to.
And then the rest, all you're doing is following the chart all the way up to give me the rest of the answers.
Is a B and C connector. This is a bayonet connector.
Yep.
What the B stands for, where you push it.
Who wants to try one more? Well, it's lunchtime. Which you do?
The NC.
Jesus said he does. Yep, we're trying another one.
Complement. This stands for
Yeah, but you give it an answer after lunch.
Okay.
How about
They
that?
both were involved in creating this.
Okay, this is what I need.
BNC connection. If you're bringing in a
I'm just gonna
WAN
use this up here,
connection or
okay?
any other type of
I'll just
coax,
type it in.
It's very possible you might use a BNC connection to lock
LAN
this
number
in place.
1.
That is one of the benefits of using BNC, is that you're able to push the connector in and twist it, and it's not going to easily remove itself. from
flash
that
is a
connection.
29.
You would need to untwist before removing that from the interface. Here's a close-up view of the BNC interface.
The class
on a
is a
device.
C.
You can see where you would plug in the BNC
This is the address.
connector. You twist that connector slightly, and it's locked in place onto that device.
I need the information on that. I need all it. I need this information.
What do roaches
I need a net ID, broadcast ID, pool, and
Okay.
what LAN it sits on.
you at all. They think about me.
I need the LAN number up here.
SC Johnson.
Networks can connect to each other in many different ways, and in this video, we're going to look at a number of different network topologies and how those.
Don't forget
different
about,
network
don't do
topologies
reserved addresses. It doesn't apply to this question
This
here.
would be very useful during
This is
the
what I'm
planning
asking you.
process
I need all the
for designing
telemetry
network.
on that
It's also useful during the
/29.
troubleshooting process so that you can tell how different networks are connected to other networks. This is also useful during the troubleshooting process so that you can visually see how one network.
That's okay,
is connected to
Michael and
data
Jesus.
to
This
another
is good practice though. The more you see it and you look at the chart, more familiar. You'll start pointing out familiar stuff on the exam like, oh, I know what that is. Oh yeah, I've seen that
This is
before.
what we
Yep.
use in most large networks to connect devices together.
B, you
There's
good
a
down there?
central device that is used as the
He's
central
like, oh,
network
hell no.
component, and then everyone on the network is all connecting to that same.
Well,
central
jump in. Let me
device.
know
An
where's it
example
at.
of a star network or a hub
Martin says I
network
need an
is
insane
one
amount
that
of
we have
repetition with this.
switched
If you don't mind me always
Our Ethernet
challenging you,
switch
I
sits
will.
in the middle of the network, and all of the
But
other
if you're not
devices connect
understanding,
to
you gotta let me
that
know.
same Ethernet switch. If each of these spokes
And I'm glad y'all are
around the
saying
network
something.
would like to communicate with
Because
each
we
other,
can
they
walk through
all
it.
must
The more we walk through it,
this
eventually
central
something
hub.
about bing.
Yeah.
A mesh network design is in one location.
So that's not a
the
problem
device
at all.
Connects to another location or device
got
over more
29.
than one network connection.
Right,
This means that we
IP.
could have one link communicating to another, and it might follow one path to get to that location, or it may follow an alternate path to be able to get to that location. One reason we
IP.
designed the network this way
So
is so that if
29.
one link in the mesh was to fail, we can use one of the other links to complete that communication. We might also perform load balancing over these links where half of the data is sent over one connection and the other half of the data is sent over a different connection. Although we can certainly design mesh networks for local
Broadcast
area
IP.
networks, We often see them deployed in wide area networks that
No problem,
will
Mike.
maintain
We got you.
connectivity to a remote site, regardless of what network connection might be available. If you were to look at a large enterprise network, you would notice there are a number of different architectures all being used in different parts of the network. And when we combine all of those together, we've created a hybrid network. One part of the network might be a star network, another part of the network may be point-to-point, and a third part of the network might be a mesh network. Once we combine all of these together, we've created a hybrid architecture. Many data centers take advantage of a spine and
One of y'all might be
architecture. This is
quick
where you
enough
would
to
have
find out that there is a shortcut in
switches
this
at the
one.
top that are the spine of the network. There would be switches in the middle that are leaf networks, and then you would have different devices.
Okay, for those that are still kind of trying to figure it out, I am going to help you walk you through the first steps, okay? Here we go. B, Martin,
leaf switches
Jesus.
do not connect directly to each other, and the spine
Here we go,
switches
Mr. T.
also
What did he do?
do not connect directly to
Slash
each other.
29.
This works very well
Broadcast
for architecture
ID.
we use in many
Nope.
data centers known as top-of-rack switching.
Nope. I'm gonna tell you why.
Top-of-rack
You could
switching,
probably see
every
it.
rack has a leaf switch at the top of every
Good try
rack.
though. So let's
We would then connect
reevaluate.
all of the physical devices in
When
that
I give
rack
you a
to the
number,
leaf
you're looking where
switch
that
at the
fits.
top of that rack. This keeps your cabling
Remember?
very simple.
Yeah.
Because all the cabling is
Okay.
self-contained
So
within that
here we
same
go.
rack. There is redundancy.
When I give you, when you see this on the exam and you know it's a class C,
This also increases the overall performance.
we know the subnet is
of the network.
255.255.255.0.
If your data center only has a handful of
The
racks, this
IP
makes it
address
relatively inexpensive
directly
to connect
correlates
all
to the
of
street that it lives on because it turns on all the bits.
tens or
So we all know, we know.
thousands of
We're
racks
trying to
in
figure
your
out the
center.
host.
You would need a separate switch for every
That
rack.
number needs to
Therefore,
fit
the cost
somewhere.
of that will increase
It'll tell us
for each
all
rack
the
you add to the
telemetry.
network. When looking
So
around the
what I
network,
do
you would
is
find
I
some
say
wide area network
200/29.
connections that are point. And as the name implies, there is a
First thing I go to
connected to
when I
a
wrote
single
this
point.
chart down,
This was a
I got
very
it in the
common
exam room
design
on my paper.
older wide area networks where you would use
29.
something like
Okay.
T1
8.
or
8
T3
is my block
connections.
size.
We refer to those as point-to-point T1.
Now you start
point-to-point T3.
0
We might also
to
use
8.
this design in local
8
area
to
networks.
16.
If you work on a campus,
16 plus
you
8
connect
is
one
24.
building to another over two
24 plus 8 is
connections.
32.
The connection between those two buildings
32 plus 8 is 40. You get what I'm saying? How many, look at this. I can build 32 subnets. That means I have to do that adding 32 times. This host number is in one of those lanes. I need to find it. Meaning, when you start from 0, that's land number 1. Land 0 is land number 1.
Enterprise networks take
0 to 8, the 8
three-tiered
is land
architecture.
number
This is a
2.
very common design, and you'll find
8 to
many
16,
organizations
that's
using
land number
three-tiered
3.
network design for their network.
Now you see what I'm
Starts with
saying?
the core of the
Ah.
network, and this is where we might have the
16
central
plus
point
8
for all of
is
our resources.
24.
So
That
our
means
servers,
24 is
our
land number
applications, our databases, and other critical points
24
are going to be contained
plus
within
8
the
is
core of the
32.
network.
32 is
The
land
second
number
tier in the
5.
three-tiered architecture is
Who's
the
following
distribution
me?
layer. This distribution is the midpoint
Yep.
between the users and
Hopefully
those
that
core
helped you.
resources. This is usually a series of switches that provides redundancy and connectivity for those users to access those critical
200.
resources. And lastly, our users need somewhere to connect, and they often connect to
Pool
an
7,
access layer. These are switches that are usually located very close to the user, usually on the same floor of a building, for example. And the access layer allows us to connect to the distribution, which then connects to the core of the network.
Here we go.
This three-tiered architecture is very common to what we might see in a large city. The downtown area.
This is the easy way I would do it.
Core of the city.
0,
All of the major resources
16,
for that city may be located
24,
in a very small
32,
geographical area in the center or core
40,
of that location.
48.
To be able to get to downtown, we need
48
some
plus
type
8.
of distribution method. For example, we need some
56.
type of highway that might connect our homes to the downtown area.
56
and our homes
plus
are usually connected to these
8,
larger highways,
64.
access roads. This allows us to use our local roads
72.
for all our daily chores, but when we need to get to the core
80.
downtown, we may need to use
88.
those distribution highways.
96.
Here's what this three-tiered architecture
What's
looks
that?
like in a network diagram. The core of the network usually has
Somebody help me
4
out.
routers that are allowing us to connect to
Is that
other
104?
resources in the core. The distribution layer in the middle is the one connecting the core to the
Yeah,
access
I believe it's
switches.
104.
And at the very bottom, the access layer is the one that
112,
all of the
like the
users
group.
are connected to. Notice there are multiple links between the access and the distribution.
8, now we're at
and occasionally
120.
you might even find multiple links between the distribution and the core. So if one component happens to fail, we can always use other parts of the
128.
network to complete that communication path.
What's next?
This is often combined with multiple buildings. So here on a
130.
single campus,
You laughing at me, Charles. I ain't good at this. Darn it.
connected on each
What,
floor of the
36?
building to an access switch. Each access switch in the building is usually connected
We're back at
to
what, 144?
one or more distribution switches, and those distribution switches are connected to the core of the network, which may be located in a
152?
central data center. If you're a smaller organization, there may not be a need for a
160.
much larger three-tiered architecture.
168.
Instead, you might want to use a
Jeez.
collapsed core architecture. This is
Is that
a
176?
three-tier architecture that combines the core and the
180.
layer into a
128,
single collapsed core.
136.
And you can see the access layer is still exactly the
4?
same as it was before.
Golly.
This allows for a more simplified design
192.
and hopefully a much easier design when you're troubleshooting.
200.
This is also a lot less expensive
Uh-oh.
because you have less devices that
Just
you have
found
to
it.
purchase and install
1,
onto the network.
2, 3,
However,
4,
as you can tell
5,
by
6,
this
7,
diagram,
8, 9,
there's
10,
not a lot
11,
of
12,
options for
13,
redundancy,
14,
so
15,
this may not
16,
be
17,
quite
18, 19,
resilient
20,
if you have
21,
to
22,
use
23,
these
24,
individual
25.
components.
It's on land number
When you're
25.
describing the flow of traffic within a data center, it's important to know where the traffic
Now give me the telemetry, Mr. T.
for that traffic. One way to describe traffic flow is
It's land number
the
25.
direct traffic flow. This means that the origination and destination for this data
I'm gonna
flow
give you the first
is
one.
all within
The first one
data
number in
center.
all the
This
pools is
also means
always
that
the
we
net
probably
ID.
have very good response times from one device to another, since they're all located on the same local network. If the traffic flow is one that is leaving the data center or is coming into the data center from an external source, you would refer to that as north-south traffic. This would probably have a bit of a different security posture than something that is east-west traffic, because we really don't know where this traffic is going once it leaves the data center, and any inbound
Dot
traffic
200 is the first IP address in the
Here's a better
range.
view
It
of the
landed.
traffic type.
Your
If data
pool is
coming
what?
into the network from the
201,
internet,
2.
or we're sending information out to the internet, we refer to that as
206.
north-south traffic. Any traffic that is inside this local data center, for example, if we have a file server that sends
206.
information to an image server, all of that traffic is staying within the data
Whoops.
center and would be considered
Put that in the wrong
east-west
place.
traffic.
Sorry. Broadcast
207.
207.
Love your plugins but wish you had
Subnet
more
mask.
control? Meet the Febreze Plug Scent Booster.
248.
Enjoy the same 50 days of continuous scent as Febreze Plug, including a cord for flexible placement options
You're
and
done.
a boost button for extra scent.
Good job.
Febreze Plug Scent Booster.
Just found my actual dream bag on eBay. This super rare center from the southern.
That's how you find out the telemetry. When I walk up to you and say, we have an issue with this IP address, you need to go fix it. That's how you find out where it belongs. Because the DHCP will say, oh, it's on this land. You go straight to that land. You go straight to that department. Oh, this is in finance. Let me go to
In the next part of
finance.
this course, we're going to talk a
Right?
lot about IP
That's how you
subnetting.
find it.
And a big part of subnetting is the ability
Yep.
to convert between decimal and
All right, good
binary.
job. Everybody go to lunch. See you in an hour when you get back.
In this video, if we step through the fundamentals
Good stuff.
of performing binary calculations. Binary, of course, is a type of numbering that
Don't forget to
uses
clock out for
different
lunch.
numbers, either a 0 or a 1. This means that there are only two possible options when doing mathematics in binary. The answer is either going to include a 0 or it's going to include a 1. Each one of these zeros or ones is referred to as a bit. And when we combine 8 of these bits together, we have a byte. Occasionally you will see a byte referred to as an octet to be sure that everyone understands that this is an 8-bit byte. In this video, we're going to perform a lot of calculations between binary and decimal. So what we need to create is a conversion chart to convert between binary and decimal. We'll create this chart by starting on the right side, and we'll simply put the number 1. Then we're going to double that number and put it to the left. So doubling 1 makes the number 2. If we double the number 2, we have the number 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32, and so on. This is the conversion chart that we will use for almost all of our decimal to binary conversions. We created this chart with 8 individual places, but you can keep moving to the left with this chart and go past 128, we'll double it to 256, we'll double that to 512, and so on. You can keep continuing this process so that if you have a very large binary number, you can still perform the same type of conversion back to decimal. Let's now use this chart to answer this question. What is the binary 00000010 in decimal? First, let's write down this value in decimal. So it's 00000010. And of course, we want to know what the decimal equivalent is of that binary value. We'll then layer on top of this our conversion chart. So of course we start on the right side with a 1, then 2, 4, 8, 16, 32, 64, and 128. Now we have everything we need to perform this binary calculation. In each of these places where we have a binary 0, we're going to bring that 0 down to the bottom line. In every place where we have a binary of 1, we're going to take the number just above that and bring it down onto the bottom line. We're then going to add all of these numbers together on the bottom line. So 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 2 plus 0 equals 2 in decimal. So the answer to this question of converting binary 00000010 is the same as 2 decimal. Let's do another one. What is the binary 10000010 in decimal? We will write down our binary value, and then we'll layer on top of that our conversion chart. Every place there is a 0, we're going to pull that down and put a 0. And every place there is a 1, we're going to pull down the number just above that 1. And you can see we only have 2 binary 1s in this number, and that's associated with the 2 and associated with the 128. So we'll bring down the 128, we'll bring down the 2, we add those together, we've got 130 in decimal. So the binary value 10000010 is the same as 130 in decimal. And finally, let's do one more binary to decimal conversion. This binary value is 1111. We'll bring down that binary value and we'll layer on top of that our conversion chart. And because each one of these spaces has a 1, we're going to bring down all of the numbers of our conversion. And if we were to count 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, we would have the value of 255 decimal. So the conversion of 1111 in binary is the same as 255 in decimal. Now let's do the same conversion, but in reverse. Let's take a decimal number and convert it to binary. This question asks, what is the decimal 154 in binary? It's the same process. We're going to bring down our binary number, but of course we don't know what that binary number is yet, so we'll put some place marks here, and then we'll layer on top of this our conversion chart. Now we need to determine which one of these binary values will be a 0 and which one will be a 1 to make up 154 decimal. And there is only one combination of 0s and 1s in this chart that would equal that decimal value. We'll start on the right side where we have our 128 column, and we'll ask ourselves, is 128 less than or equal to 154? This is obviously less than 154, so we'll put a 1 in that column, and we'll bring down the 128. Now let's look at our next column of 64, and we'll combine that next column with the numbers that we've currently brought down previously. In this case, the number 128. So 128 plus 64 is 192. And we have to ask ourselves, is 192 less than or equal to 154? In this case, 192 is more than 154, so the answer is no, and we'll put a 0 in that column. Now we move to the next column, which is our 32. We'll add 32 plus anything that we brought down. That would be 128 plus 32, which equals 160. Is 160 less than or equal to 154? It is not, so we'll bring down a 0 in that column. We'll continue with this process by looking at the fourth column, which is 16. We'll add that to anything that we brought down. So 128 plus 16 is 144. Is 144 less than or equal to 154? It is. So we'll put a 1 in that column and bring down the 16.
in stock and ready to ship free the next day. Zorro.com. Tools, parts, and supplies for your business.
New Cloud Paint Flash Blush for a pillowy, soft, sunset-inspired blush.
Our next column is the 8, so we'll add 8 to anything that we've previously brought down. So 128 plus 16 plus 8 is 152. Is 152 less than or equal to 154? It is, so we'll put a 1 in that column and bring down the number 8. Our next column is the number 4. We will add 4 to everything that we brought down into that bottom row. So that all adds up to 156. And is 156 less than or equal to 154? It is not, so we'll put a 0 in the 4 column. The next column is the number 2. We'll add the number 2 to everything we brought down so far. And if we add all of those up, it would be 154. Is 154 less than or equal to 154? It's obviously equal to 154. So we'll put a 1 in that column and bring down the number 2. And obviously we've hit the number 154, so we know that the number 1 on the last column will not be added to this final value. And if we add up everything in that last row, we see it does equal 154. And now all we have to do is look at the middle row to determine what the binary value of this is, and it would be 1001, 1010. If we look at 154 decimal, we know that that is exactly the same as 1001, 1010 in binary. With these 8 individual bits, we can convert any number between 0 and 255. So take any number you would like, put it into this particular format, and see if you can perform the conversion between binary and decimal. As you're increasing the number of bits in a binary value, you're increasing the total possible number of decimal results. For example, if you have 2 bits, there are only 4 possible outcomes: 00, 01, 10, and 11. And if you were to perform that conversion between binary and decimal, that's the same as 0, 1, 2, and 3. If you have 3 bits, then you can have 8 possible outcomes. If you use 4 individual bits, you have up to 16 different options. 5 bits moves you up to 32, 6 would be 64. 7 bits is 128 possible options, and if you were to increase the number of bits into 9 bits, 10 bits, 11 bits, and so on, you would also increase the total decimal number. You can see that this value is listed in this chart, and notice that I've also added the powers of 2 on top of this. This is effectively what we've been doing the whole time. 2 to the 0 power is 1, 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and so on. So as we increase this powers of 2, we are also increasing the total decimal value.
People can get crazy trying to stop a cyber attack. Acronis, take the headache out of IT security.
I'm not really one for the spotlight, but there is some gravy to be had. You know, I always seem to get primo parking. But you don't have to be a VIP to get more than just savings with Geico. Every customer gets tip-top service with 24/7 fast, friendly claim support.
I never do this, but could I get a picture?
Yeah, it's not like you run into animal celebrities every day.
Stop. It's Doug the Pug! Doug!
Stand corrected.
I literally never do this.
Get more than just savings. Get more with Geico.
If you've done anything with networking, then you've probably run into an IP version 4 address. In this video, let's look at the different configuration options for IP version 4. The IP address is the unique identifier that every device on the network must have if it wants to communicate using that IP protocol. An IP address is a series of 4 numbers separated by a period. This would be something like 192.168.1.165. To be able to properly communicate on the network, every device needs to have its own unique IP address. The IP address is combined with another value referred to as the subnet mask. The subnet mask is also a 4-octet value, for example, 255.255.255.0. The subnet mask is used in conjunction with the IP address to determine what IP subnet this particular device is on. This isn't something that's usually transmitted across the network. It's instead used by your local device to make the determination of what devices are local on this IP subnet and what IP addresses may be outside of this local IP subnet. This becomes especially important when you need to send traffic outside of your local subnet, and you do that through the use of a default gateway. The default gateway is the IP address of a device that's on your local subnet that allows you to communicate outside of this subnet. For example, if we have an IP address of 192.168.1.165 and a subnet mask of 255.255.255.0, a common default gateway could be 192.168.1.1. This is an IP address that is configured and assigned to the router on your local subnet by your network administrator, and it must be an IP address that is on your local network. There are also other IP addresses you should be familiar with. One of these is a loopback address. This is a way to define your local device without having to know a specific IP address. Every device on the network has a loopback address, and it's a number that is between 127.0.0.1 through 127.255.255.254. So if you wanted to ping your local device, you could ping 127.0.0.1. Hopefully your local device would be able to respond to you. This is often used to confirm that your local IP stack is working properly, and it would then be able to communicate to other devices. We also have a range of IP addresses that we've set aside as reserved addresses. This is a range of IP addresses that should never be assigned to other devices. They're used for future use or for testing in the future. This range of reserved addresses is 240.0.0.1 through 254.255.255.254. Anything that is a Class E address is also a reserved address. We'll talk about classes of addresses in just a moment. And another address type you might run into is one that is not real. It's a virtual IP address, or a VIP. Virtual IP addresses are not associated with a physical Ethernet adapter. Instead, VIPs are addresses that you would assign to the internals of a device so that you can always reference that device using that virtual IP address. For example, you might assign a VIP to a virtual machine, or the VIP may be part of an internal address that you're associating with a particular router. The IP protocol and IP version 4 operate at OSI layer 3. So anytime you're working with an IP address, you're working at that network layer of the OSI model. Let's break apart an IP version 4 address and really see what it's made of. Let's take the address 192.168.1.131. We refer to these 4 values as octets. That's because they consist of 8 individual bits. And you can see the representation of that same IP address broken out into those 4 groups of 8 bits. Sometimes you'll see these 8 bits broken out and described as 1 byte, or sometimes 1 octet. So if you were to count up all of these bits, there are 32 total bits in an IP version 4 address, and that is the same as 4 bytes or 4 octets. Since each one of these individual groups inside of IP version 4 consists of 8 bits, the maximum value that you would ever have in decimal for any of these groups would be a maximum of 255. In the early days of networking, we had to manually configure the IP address, subnet mask, and default gateway all in a manual way. We had to visit that device, change a configuration file, and then that device would be able to communicate on the network. If anything changed with our network configuration, or we needed to change the IP address of that device, we had to revisit the device and manually make those changes. Today, of course, we can plug in any of our devices and it automatically receives an IP address. The way that we are able to receive this automated IP addressing is through a protocol known as DHCP, or Dynamic Host Configuration Protocol. When we plug into a wired Ethernet network or a wireless network, and we're automatically able to communicate out to the internet, it's because we've received all of our IP configuration settings via DHCP. But if you've ever connected to a network that does not have a DHCP server, you may notice that you're still assigned an automatic address. But this address is not quite as capable as a DHCP address. Instead, it's what we call a link local address because it can only communicate to other devices that are on your local subnet, and we cannot route that traffic outside of your local subnet. For example, if you're assigned a linked local address, you can't communicate to the internet because that's outside of your local subnet. In IP version 4, this linked local address is assigned through a process known as Automatic Private IP Addressing, or APIPA. This range of IP addresses automatically assigned through APIPA is 169.254.0.1 through 169.254.255.254. There are also reserved sections of that range. The first and last 256 addresses are reserved and they're not assigned to end stations. So if you receive an APIPA address on your device, it's between 169.254.1.0 through 169.254.254.255. Just as DHCP works automatically to assign your address, APIPA also has an automated process to assign this address. It uses ARP to confirm that no one else on your local network has that linked local address, and if nothing responds to that address resolution protocol query, then it will assign a random number between that functional block.
Zibo works 24/7 to kill 99.9% of bugs trapped.
One of the challenges with IPv4 is that there are far more devices in the world than there are IP version 4 addresses. And in recent years, we've used up all of the available blocks of IP version 4 addresses. There are no other IP version 4 addresses that can be assigned in these blocks, so we need to find other ways to be able to communicate via IP version 4. One way that we've been able to extend the functionality of IP version 4 is to create an assignment of IP address ranges that can only be used on the inside of a network. We refer to these as a private IP address range, and anything that is a private IP address cannot be routed on the public internet. Fortunately, these are very large ranges, and we're able to use those ranges on the inside of our corporate networks. If you were to look at the IP address that's assigned to your device right now, it's likely that it's a private IP address. So if your device is currently using a private IP address and you're watching this video on the internet, how are you able to communicate on the internet with an address that is not able to be routed across the internet? We're able to do that through a functionality called Network Address Translation. This allows us to convert a private IP address into a public IP address and use that public IP address to communicate on the public network. We'll learn more about network address translation as we go through this training course. If you want to learn more about private IP addresses, you may want to reference a request for comment, or RFC. RFC 1918 is the standard that defines these ranges of private IP addresses and how they can be used on our networks. If we were to look into the details of RFC 1918, you would see 3 different ranges have been set aside for private IP addressing. These 3 ranges are 10.0.0.0 through 10.255.255.255. And if you were to count up all of the possible addresses in that range, it would be over 16 million addresses. We often refer to this as a single Class A block of addresses, and we often write it as 10.0.0.0/8. If you were to write out the subnet mask of that /8 address, it's 255.0.0.0. This means the host size of this particular IP address range is 24 bits in length. Another range is 172.16.0.0 through 172.31.255.255. This gives us a total of just over 1 million addresses that we can assign in 16 contiguous Class B address ranges. If we were to write this out in CIDR block notation, it would be 172.16.0.0/12. The decimal subnet mask for a /12 network is 255.240.0.0, which means our host ID size is 20 bits in length. And the last range is 192.168.0.0 through 192.168.255.255. This allows us to assign over 65,000 addresses as part of 256 contiguous Class C address ranges. The CIDR block notation for this would be 192.168.0.0/16, and that /16 subnet mask is the same as 255.255.0.0. Half of this address is assigned per host, so your host ID size is 16 bits in length. As we step through the next series of videos, you'll learn more about CIDR block notation, the different classes of IP addresses, and other details that you see associated with these private address ranges.
In stock and ready to ship free the next day. Zoro.com. Tools, parts, and supplies for your business.
I heard someone was playing Stegosaurus in her school play. Still taking yours?
Every day. Nature Made. Clinically studied probiotics that support your digestion. Take charge of your gut with Nature Made. The #1 pharmacist recommended vitamin and supplement brand.
When you start working with IP version 4, one of the things you'll hear about are classes of IP addresses. And in casual conversation, we might even refer to an address as a Class A address, a Class B address, or a Class C address. This was a method of describing an IP address as it related to its subnet mask. Anything that is a Class A address has 8 bits assigned for the network address and 24 bits that are associated with the host address. This means that the subnet mask for a Class A address would be 255.0.0.0. A Class B address default subnet mask is 255.255.0.0, and the default subnet mask for a Class C address is 255.255.255.0. This style of class-based subnetting is one that we have not used since 1993, but we still refer to some of these addresses in a very colloquial sense. And although you may hear someone refer to an address as a Class A address or a Class C address, in reality, we no longer use a class-based form of subnet masking. So if we don't use classes, why are we doing a video on class-based networking? That's because these classes do act as a starting point when we begin any type of subnetting on our networks. If you're going to subnet a network, it's important to know where to begin the subnetting process, and this class-based system is the starting point. These Class A, Class B, and Class C addresses have an obvious demarcation between the network part of the address and the host part of the address. With Class A, that line is drawn after the first 8 bits. In a Class B address, that line is after the first 16 bits. And in a Class C address, that line is after the first 24 bits. Here's a table that defines the different subnet classes for Class A, Class B, Class C, Class D, and the reserved Class E. And you can see if you look on the right side, the default subnet masks are the ones we just saw, where Class A has a default mask of 255.0.0.0, Class B is 255.255.0.0, and Class C is 255.255.255.0. The way that you can look at an IP address and tell immediately what class that IP address is associated with is the very first octet of the address. If the decimal octet is between 0 and 127 as the first number of that IP address, it's a Class A address. If the first number of the IP address is between 128 and 191, that's a Class B address. And if the first number is between 192 and 223, that is a Class C address. If you were to look at that address in binary, if the first bit was 0, it's a Class A address. If the first bits are 10, it's a Class B address. And if the first 3 bits are 110, it's a Class C address. Class D addresses are used for multicast communication, and therefore they are not assigned to an individual device. But there is a range for Class D addresses, and that is between 224 and 239, or the first 4 bits of a Class D address are 1110. And there is a range of IP addresses that are not used for any purpose. This is a reserved range. We refer to this as the Class E range between 240 and 255, or the first 4 bits of 1111. So based on that chart and those ranges of IP addresses, let's see what class a particular IP address would be part of. Let's start with the IP address of 17.22.90.7. To be able to determine the class, we need to look at the first octet, which in this case is the number 17. And if you refer back to that chart, the number 17 is in a Class A address. Let's do another one. IP address is 220.10.77.40. If we look at that first octet, it is 220, and 220 is in the C class. The next IP address is 165.245.0.1. We need to look at that first octet. In this case, that's 165, and 165 is in the range of a Class B address.
Spending time with the ones you love is priceless. That's why Kroger Delivery, proudly serving King Soopers, makes grocery shopping effortless. Get $20 off your first order. We'll deliver your groceries in our refrigerated trucks and bring them to your door. King Soopers, fresh for everyone.
When Verizon gives you a free phone on any plan, you use AI a lot.
Gemini, show me the concealer.
The long, thin tube in the middle.
But hey, it's the new Google Pixel 10 Pro, plus Google AI Pro for 6 months. Boyfriend of the year.
Next on our list is 128.90.10.2. That first number is 128, which means that is also a Class B address. The IP address of 191.77.24.250 has the first octet as 191, and if we refer to our chart, 191 is in the range of a Class B address. And lastly, 192.1.12.5, we're looking at that first octet of 192, which falls in the range of a Class C address. When you start calculating an IP subnet, there are 4 different values that are very important to know. The first is the IP address associated with the network address. This is the one that defines all of the other devices on this particular subnet. To calculate a network address, you set all of the host bits of that address to 0 and then determine what the decimal representation of that might be. The second important piece of information you need for an IP subnet is the first usable host address on that subnet. This is always going to be one number higher than this previously defined network address. You also need to know the network broadcast address. This is the last IP address of this particular network address. To be able to calculate the network broadcast address, you would set all of your host bits to 1, which is the same as 255 decimal, and perform the conversion between the binary and the decimal. And just as you need to know the first usable host address on the network, you also need to know the last usable host address. And to calculate that, you look at the network broadcast address, and it's one number fewer than the broadcast address. So let's calculate those 4 important subnet values. And let's start with the IP address of 10.74.222.11. If we look at our chart, we know that this starts with the number 10, therefore this must be a Class A address. And the default subnet mask for a Class A address is 255.0.0.0. Since we're using this Class A subnet mask, we know that everything that's on the left side of our bar, or this first octet, is going to be our network address, and everything on the right side will be associated with the host ID. So let's add those to our chart. We have a network column and a host column. Obviously, the 10 dot is going to be in the network column. That's what's on the left side of that bar. And then everything on the right side is going to be the host address. We first need to calculate the network address, and to do that, we set all the host bits to 0. This means that everything in that second column will be 0, and the network address, therefore, will be 10.0.0.0. The first host address is one more than the network address, so our first host address would be 10.0.0.1. To calculate the broadcast address for this subnet, we set all the host bits to 1, which means that the broadcast address is 10.255.255.255. And as you recall, to calculate the last usable address on this subnet, we need to subtract 1 from the broadcast address. So the last usable address on this network is 10.255.255.254. With these 4 values, you'll be able to determine the network address. You'll know if an IP address happens to be one of the usable addresses within that range, and you'll know what the last or broadcast address is for that entire network. Let's do another one. In this case, the IP address is 172.16.88.200. If we look at that first octet, we can see that that is a Class B address, which means the default subnet mask for this network is 255.255.0.0. This means that we would draw our line right in the middle between the first 16 bits and the last 16 bits. So everything on the left side is associated with the network address, and everything on the right side is associated with the host address. Now let's perform those exact same calculations. We want to determine what the network address is, so we will set all host bits to 0. This means that the network address for this particular subnet is 172.16.0.0. To be able to calculate the first host address, we need to add 1 to that value, or 172.16.0.1. To calculate the broadcast address, we set all host bits to 1, which means the broadcast address for this subnet is 172.16.255.255. And to define the last usable host address on this network, we subtract 1 from the broadcast address, which means the last usable address is 172.16.255.254. Let's see if we've figured out this process and step through another IP address, in this case 192.168.4.77. Looking at this first octet of 192, that fits into the range of a Class C address, which means the default subnet mask is 255.255.255.0. If we were to draw our line, the network side of the address is the first 3 octets and the host side is the last octet. Let's put that into our chart. So our first 3 octets, 192.168.4 is the network side and .77 is the host side. To be able to calculate the network address, we set all host bits to 0, so the network address for this particular subnet is 192.168.4.0. If we add 1 to that address, we get our first host address of 192.168.4.1. To be able to calculate the broadcast address, we set all host bits to 1, which means the broadcast address is 192.168.4.255. And if we subtract 1 from that broadcast address, we get the last host address. That would be 192.168.4.254. Although we no longer use class-based subnetting, we can still use this same process when we look at anything that may be class or non-class based. And as we go through our additional subnetting videos, you'll notice that this same process is used over and over again, regardless of the IP address and the subnet mask.
New Cloud Paint Plush Blush for a pillowy, soft, sunset-inspired blush.
At Tropical Smoothie Cafe, hitting your protein goals is a breeze. It's tropic time.
In a previous video, we talked about class-based subnetting and how IP addresses can be assigned a Class A, Class B, or Class C address. But since 1993, we've not used class-based subnetting. Instead, we use classless subnetting. Sometimes you'll see this referred to as classless interdomain routing, or CIDR. This classless addressing means that we can assign a subnet mask that doesn't fall into those same Class A, Class B, or Class C arrangements. And instead of referring to the subnet mask in its decimal form, we can simply refer to it as the number of bits. That number of bits is referred to as a CIDR block notation. For example, a decimal subnet mask of 255.0.0.0 is the same as a /8 CIDR block notation because it has 8 individual bits as part of the subnet mask. So it would be very common to see an IP address written as 192.168.1.44/24. Everything with the /24 is referring to the number of bits in a subnet mask, and a /24 mask would be the same as 255.255.255.0. When you're configuring a device, you're often giving it an IP address, a subnet mask, a default gateway, and very often a series of DNS servers. Most of the time, an operating system is expecting you to put the subnet mask in as a decimal mask. So for example, in Windows, you may put the IP address and then you might add in the decimal version of the subnet mask. But if you're using a router or a switch, it may be expecting the CIDR block notation for those masks. So instead of using 255.0.0.0, you would simply input /8. Make sure you check the documentation of the device you're using to see what notation it prefers for the subnet mask. As you've probably seen in our previous examples of subnet masks, the mask consists of a contiguous series of 1s followed by 0s. So the 1s would be on the left, the 0s would be on the right. For example, here is a subnet mask. You can see the contiguous set of ones on the left and the zeros that are on the right. In this example, you can see 3 separate octets that are set to 1. So there are 24 ones in this particular mask, and there are 8 zeros at the end. If we were to write this out in decimal, it would be 255.255.255.0. And if you were to write this out in cider block notation, you would count how many ones are associated with this subnet mask. In this case, there are 24, so the cider block notation would be /24. The subnet mask is obviously used to separate the network part of the address from the host part of the address. So for this particular subnet mask, the network address is 24 bits in length, and the host address is 8 bits in length. Let's convert a binary subnet mask to one that is the cider block notation for a subnet mask. And we'll take this subnet mask that we have on the screen, which has all ones in the first 2 octets and all zeros in the last 2 octets. If we were to count the number of ones in this subnet mask, we have 8 in the first octet, 8 in the second octet, none in the third, and none in the fourth. That means the total number of ones in the subnet mask would be 16, so the cider block notation would be /16. This means that the first 16 bits of this subnet mask are associated with the network, and the last 16 bits are associated with the host ID. Let's do another one. In this example, the first 3 octets are all ones, but the last octet has 2 ones and 6 zeros. So let's count the number of ones in this subnet mask. There are 8 in the first octet, 8 in the second octet, 8 in the third octet, and 2 that are in the fourth octet. If we count all of those together, we have 26. So the cider block notation of this subnet mask would be /26. The /26 means that the first 26 bits of this address are the network part of the address, and the last 6 bits are reserved for the host ID. And here's one more. In this subnet mask, we have the first octet of all ones. The second octet has 4 ones and 4 zeros, and then the third and fourth octets are all 0. Since we are counting number of ones, we have 8 in the first octet and 4 in the second octet. And if you count those together, the subnet mask in cider notation would be a /12. That means that the first 12 bits are for the network ID, and the last 20 bits would be for the host ID. We've looked at the subnet mask in binary, and we've calculated the cider block notation, but we often refer to the subnet mask as a decimal value. If we were to convert these binary subnet masks into a decimal value, there are only a certain number of these that you would run into. For example, all zeros would obviously be a decimal 0, but anything that starts with a binary of 1 and the rest zeros would be a decimal of 128. If there are 2 ones, it's 192, 3 would be 224, and so on. This means that you could create a chart that shows all 8 of the bits within a single octet and what the decimal equivalent would be. We can now use that chart to calculate the cider block notation and what the decimal representation of that subnet mask would be. So let's look at a subnet mask of all ones in the first octet. There are 4 ones in the second octet, and the rest of this would be all zeros. If you refer to our chart, you can see that all ones is 255, 4 ones and 4 zeros would be 240, and then of course all zeros would be 0. And if we recount the number of ones, we know that correlates back to a /12. So a /12 cider notation is the same thing as 255.240.0.0 in decimal notation. And of course, since there are 12 ones, the network section is 12 bits in length, which leaves the remaining 20 bits available for the host ID. Let's look at a subnet mask we've not seen yet. This one is all ones in the first octet, all ones in the second octet. There are 3 ones in the third octet, and of course the rest of this is zeros. If we look at our chart, we can see that of course all ones is 255, and in the octet that has 3 of these ones, we refer to the chart that is the same as 224 in decimal. And obviously all zeros in binary is the same as 0 decimal. If we then count the number of ones in all of these octets, they all add up to 19. So your cider block notation would be /19, which corresponds back to the decimal representation of 255.255.224.0. This, of course, means that the network part of this address is 19 bits in length, and the host section is 13 bits in length. Of course, we can do this in reverse as well. Let's say that we have a subnet mask that's been given to us as a /26 in CIDR block notation. If we were to write this out in binary, that means that we would have all ones in the first 3 octets and 2 ones in the last octet. And if we were to refer back to our chart, all ones would obviously be 255, and the last octet that has 2 ones correlates back to a 192 in decimal. So a /26, where your network ID is 26 bits in length and the host ID is 6 bits in length, is the same as a /26 in CIDR block notation, or 255.255.255.192 in decimal. Let's do another one where we've been given a /20 in CIDR block notation. That means there are 20 ones in this particular subnet mask. So your first 2 octets are all 1, and third octet has 4 ones and 4 zeros, and of course the last octet will be all 0. If we refer to our chart, we know that the decimal version of that binary subnet mask will be 255.255.240.0, which is the same as a /20 CIDR block notation. That means the network part of this address is 20 bits in length, which leaves us 12 bits available for host IP addresses. In this video, we're going to look at a detailed calculation of subnets and hosts using IP version 4. If you stumbled across this video, I highly recommend you go back and look at our video on binary math, classical subnetting, and IP4 subnet masks. As we've been going through these subnet videos, you may be asking yourself, why do we have to go through this process of calculating IP addresses, their mask, looking at default gateways, and understanding what the first and last available IP address might be? Well, that's because it would be functionally impossible to have one device that would know where every other device in the world might be. Instead, we create smaller networks and we build routers that are able to get information between all of these smaller networks. This allows us to communicate to anywhere in the world without knowing exactly where that destination location might be. We simply send out the packet, and the routers every step of the way allow us to get that information to the final destination. Well, this means that we need to create these smaller networks, and we do this by using a process known as VLSM, or Variable Length Subnet Masks. As the name implies, these subnet masks are not like the class-based networks that we looked at earlier, which have a very fixed number of bits in the subnet mask. Instead, we can create a subnet mask that has a different number of bits on every network, therefore creating a variable length of a subnet mask. This means you, as the network administrator, can build a network that is exactly the right size with the right number of networks and the right number of hosts. And you have complete control over what the subnet mask might be for that network. This is a lot like cutting a pizza into smaller pieces. How many pieces do you need in the pizza? Should the pizza be cut in 2 pieces? Should it be 4? Should it be 8? Or should it be even more than that? If we apply this to IP, we can look at a Class A network, which has 10.0.0.0 and a subnet mask with a /8. But if we wanted to cut that pizza into smaller pieces, we might have a subnet mask of a /24 or even a /26. Since we're using a different number of bits than 8 in the subnet mask, we're using a variable length subnet mask that we can define to be whatever we'd like. Let's perform some of this variable length subnet masking, but let's first look at the default subnet mask for a Class A address. This would be 10.0.0.0. The default is Class A, since that starts with the number 10, and the default subnet mask for that would be 255.0.0.0. This would be the default subnet mask if all we did was have classful addressing. If you were to look at this classful address in binary, the first 8 bits would be 1 and the remaining bits would be 0. In decimal, that means it would be 255.0.0.0, and if you were to use the CIDR block notation, this would be a /8 subnet. This means that the network bits would be those first 8 bits of the address, and the host bits would be the last 24 bits of the address. Since this is a /8 subnet mask, we are drawing our line after those first 8 bits of the subnet mask. But in reality, of course, we could pick a different number of subnet bits. We just need to decide what works best for our network. For example, let's draw our line right after the 3rd octet. This means that we still have our default first 8 bits as part of that class A address, but we're going to borrow the middle 16 bits as what we call our subnet bits. This means those subnet bits would now be turned into 1, and the host section of the IP address would shrink down to 8 bits. This means that the decimal subnet mask would be 255.255.255.0, and the CIDR block notation for this new subnet mask would be /24. We've been doing a lot of these calculations in binary, and then we've been converting that binary back to decimal. But that process tends to take time, and one of the faster ways to perform these calculations is to look at a list of the powers of 2. For example, you can look at 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, and so on. If you want to calculate the number of subnets and the number of hosts, you can calculate the number of subnets as 2 to the number of subnet bits, and the number of hosts per subnet would be 2 to the number of host bits minus 2. That subtraction for the 2 means that we are subtracting the number that we would use for our network address and the number that we would use for our broadcast address. Everything in the middle would be our host addresses. So let's now use this chart with our powers of 2 to calculate the number of subnets and the number of hosts per subnet. Let's take the IP address of 10.1.1.0/24. If we perform our calculation in binary, we would write out all 24 of those bits as 1s, and the last 8 bits would be 0. The default for a class A address such as this one, though, would normally have our network address as the first 8 bits. But we are moving that line another 16 bits over so that we are borrowing an additional 16 bits for the subnet. That leaves us with 8 bits left over for the host. If we were to calculate the number of subnets using these powers of 2, we would take 2 to the number of subnet bits. And since we have 16 subnet bits, 2 to the power of 16 is 65,536. If we were to calculate number of hosts per subnet, it's 2 to the number of host bits minus 2. We have 8 host bits, which means 2 to the 8 minus 2 is 256 minus 2, or 254. So for this IP address of 10.1.1.0/24, we can have a maximum number of subnets of 65,536, and on each of those subnets, we can have a maximum of 254 devices. Let's calculate another one. We'll look at an IP address of 192.168.11.0/26. If we were to write out that /26, you can see there are 26 ones. That leaves us with 2 ones in the last octet, and we have 6 zeros left over at the end. If we calculate the class of this address, we look at the first octet, which is 192, which means this is a Class C address. That means it has a total number of 24 bits as the network address by default. But we borrowed a couple of extra bits into the last octet, so there are 2 additional bits available that we will call our subnet bits. And then of course we have the last 6 bits available as the host bits. Let's perform our calculation again. To calculate the number of subnets, we use 2 to the number of subnet bits. We have 2 bits left over as the subnet bits. 2 to the second power is 4. To calculate the host per subnet, we have 6 bits, so we take 2 to the 6th power and subtract 2 from there. That means we have 64 minus 2, or 62. So for this IP address of 192.168.11.0/26, we can create a total of 4 subnets, and on each of those subnets, we can have a total of 62 devices. This same process works with any type of subnet mask. Let's take, for example, 172.16.55.0/21. If we looked at this in binary, we would have 21 ones, which means we have 8 in the first octet, 8 in the second octet, and 5 ones in the third octet. Everything else, of course, would be zeros. And if we look at this IP address, it starts with 172, which by default would be a Class B address. So by default, the first 16 bits would be your network address. We borrowed some additional bits, in this case, 5 additional bits to be our subnet bits, and then everything left would be our 11 host bits. Performing our calculation again, we have 5 subnet bits, so to calculate the number of subnets, it's 2 to the 5th power, or 32. We have 11 host bits left over, so if we calculate that as 2 to the 11th power minus 2, that would be the same as 2048 minus 2, or a total of 2046 devices. So for this IP address of 172.16.55.0/21, we can have a total of 32 subnets, and on each of those subnets, we can have a maximum of 2046 devices. If you use this powers of 2 to perform these calculations, it can be a very quick way to determine what the number of subnets might be and what the host per subnet might be. But there are some shortcuts available that might get you to these values much faster, and in the next couple of videos, we'll give you some different options for calculating this process using those shortcuts.
When too much work bogs you down, Asana helps you handle it. That's because Asana is where humans and AI coordinate work together. AI makes it easy to hand off routine tasks, streamline workflows, and keep everyone focused on the work that matters most. That's how work gets handled. That's Asana. Visit us at asana.com. That's ASANA.com.
If you've been with us with the videos just prior to this one, then you've learned a lot about subnetting, masks, CIDR block notation, and other important fundamentals when it comes to subnetting via IP version 4. All of that work has brought us to this point where we can start to answer questions like this one. Here's a network layout, and it says, here's your IP address assignment. We've been given the IP address of 192.168.1.0/24. And this says we need an IP addressing scheme with more than one network address that can support 40 devices per subnet. That is the optimal number we're looking for, and we need to determine how to subnet this network address to be able to get 40 devices per subnet. Now you could of course write out all of the possibilities in decimal and binary and be able to calculate what the differences are with the number of networks and the number of hosts per network. For example, if you look at the default subnet mask that we were given, which is 255.255.255.0, you can see this is the binary representation of that subnet mask and the CIDR notation, which is a /24. That gives us one single network with 254 hosts per network. If we borrow 1 bit from the host side, so that we are at 255.255.255.128 as our subnet mask, or a /25, we would be able to create 2 networks with 126 hosts per network. We are getting closer to that number of 40. Let's keep going by borrowing another bit so that our subnet mask is 255.255.255.192, or a /26. This allows us to have 4 networks with a total of 62 hosts on each of those subnets. This is certainly getting close to 40, but let's go one more step to see if we're getting even closer to that 40 value. The next step would be to borrow 1 more bit from the host side. So now we're borrowing 3 subnet bits, which means our subnet mask is 255.255.255.224, or a /27. If we subnet in this way, we can have a maximum of 8 networks, but it would only allow for 30 hosts per network. This means that the optimal subnet mask, if we're looking for a total of 40 devices per subnet, would be the next one up, or the /26, which would give us 4 networks and a maximum of 62 hosts per network. Now we can certainly speed this process along by performing a calculation based on powers of 2. Let's look to see how we might do that. We have a starting IP address of 192.168.1.0 and a subnet mask of 255.255.255.192. And based on this information, we can show the network address and the subnet mask in binary. And you'll notice in the subnet mask, we have the default number of bits for that address, plus the 2 extra bits that we borrowed from the host side. Visually, you can see where the 24 subnet bits might be, the 2 extra bits we borrowed for the subnet, and the 6 bits that are left over on the host side. If we were to now calculate the number of subnets and the number of hosts per subnets using this powers of 2 formula, we would take 2 to the second power, because the second power would be 2 bits, and that would be a total of 4 networks. We would determine the number of hosts per subnet by taking those 6 host bits that are left over at the end and calculating 2 to the 6th power minus 2, which would be 64 minus 2, or a total of 62 hosts per subnet. This is a relatively straightforward way to calculate the number of subnets and the number of hosts per subnet.
All right, welcome back from lunch, everybody.
A binary conversion and then
Good to see
the
you.
number of bits to be able to calculate what that total might be at the end.
All right.
There are some shortcuts that we can use.
It's kind of
In
picked
this
up
video,
where we
we're
left
going to
off
look at a
at.
shortcut that uses the magic
I'm
number.
sharing my screen, and
These calculations are intended to give us 4 separate pieces of
see, there's a new
information.
angle.
First,
We get
need
to add a
network
little
address
bit more
or
stuff on
subnet
each time we
ID.
do this, and this might help you out, Brian, too.
We also need a broadcast address.
If we
and
look
last
at-
address in the subnet. We need the first available host address.
Right here.
This is an address that
How we figured out it
can
was on
find
LAN
the
25.
subnet. And then we need the last
We use the
available
/29.
host address. We need to be able
And this
to
is the quick
calculate
math.
these as quickly as possible.
/29 tells
Now,
us
obviously, we could
we'll
calculate this
use
by
8
converting
as a
everything
block
to binary,
size to figure
looking
out
at
where
subnet
200
bits
fits
and
in at.
calculating for every possible
Right?
scenario what this particular
So if we know we have-
might be and the subnet
here's the
mask
shortcut.
for each one of these.
If we know we
And
can
for this
make
particular
32
IP address,
subnets,
we determined there were 4 separate
all we do
subnets.
is
These are all the
we could do
calculations
8
that
times
we would need
32.
to be
It'll
able
give
to
us
calculate
our
all of
beginning
that
number for our net
information
ID.
for all 4 of those subnets.
But in this case, we
Then
did
see,
8
this
times
way, there
25.
are a lot
It's
of
quick
separate
math
binary
to
decimal
quickly find out
conversions
where
you
is
can
that
do just to
200 at.
calculate those specific
So if we
details
can
for
make
all 4
up
of
to
those
32
subnets.
subnets, all we do is take
We
the
can
block
simplify
size
this process
times
by using the magic number
25,
shortcut.
because it was on the
This allows us
25th
to
set of
perform
subnets we made.
quickly and very
And there it is.
All of these calculations
There's the
in
first
Excel.
address,
There's still
200.
a little bit of math involved with the
Does that make
magic
sense?
method, but it's limited to
This is
power
multiplication.
some very simple addition
That's how you
and
can quickly
subtraction.
find out. So somebody
You could even
let me
create
know
charts that might help
if I
you
did
with the
this.
process, but once you get accustomed to using this method, you'll find that you memorize very easily what's in the charts. You may not have to write them down at all during your exam.
Subnet's
One
gonna,
chart that
everything
might
is
help
gonna
you is a
change.
chart that
The
easily converts
LAN will
decimal
change,
block
not the
notation
subnet.
and the decimal
So what I'm saying
subnet mask
is,
notation. You can see an example of this.
if you want to quickly find out where a host number will land, and you know the slash, just multiply the block size by as many lands as you can make. So 16 times 1, there's your first subnet. 0 to 16, right? It's in there somewhere. 16 times 2.
So we could write this chart
16 times 3.
that shows a slash
16.
nine,
You can
slash
go all the way up to
17,
16
and
times
slash
16,
25
and you'll have
is
all your
128
first, your net ID numbers. Those are your beginning net ID numbers. Do you follow me?
Different tasks that we perform based on the octet.
So you can go all the way up to 16 just by multiplying. Let's try it out.
To have something that's a little bit different. For example, if you wanted to see the cider
16
notation for
times
interesting octet 2, you can see it ranges from a /9
1
to /16.
is
Cider
16,
notation for
right?
interesting octet 3 would be /17 through /24, and
But
the
in
cider
binary, we start at
notation
0,
for
right?
interesting octet 4 ranges from
16
/25
times
to
0, that's your
/30.
first LAN.
You
Your
notice
first
that
ID
we don't
is
use
0.
/31 by default because it doesn't leave any room for any hosts on the subnet.
Let me type it out so
And
you
we
can see what I'm
don't
talking
use
about.
the /32 because that leaves 0 bits available for any host. For each of these columns with the cider block notation, you'll notice there is a magic number. And in a moment, we'll learn
So your
how to
address
use
is going to
that
start
magic
there.
number value.
16 times 1 equals 16. So your first net ID address for that block is going to start there. What's 16 times 2?
For the ones who get it
32.
done, the most important part is the one you need now. And the best partner is the one who can deliver. That's why
Guess what?
maintenance and repair.
Your net ID for your third LAN starts with
where you can take
.32. Do you see how it coincides? So right now we've already made three LANs. One with 0, one with 1, and one with 2. It's just quick multiplication to figure out where your host LAN's at. Okay? So for instance, if I went back up here and changed it from 200 to 215, this is what I would do. Since I know we were on LAN 25 and we were doing 8s, right? 208. All I'm doing is adding 8s. That's my block size. 216, boom, that's where it lands at. LAN number 27, things change. This is no longer, this IP address is on LAN 27. Right? And now equals 216. That's the quick math to figure out where this host number lives. Subnet mask and everything remains the same. All right.
So James, for clarification, if we're just starting with the bit, let's say we're starting with 29 or 27, and we are to work backwards to get the IP, the net ID, broadcast, and all the information. Can you just go through that steps? Because I think that if we're working with limited information and we don't have so much information to start doing the calculation, because that last one was a bit easier, even though it was still complex. But let's say we have limited information, like just a bit, like B29. Can you just go through that step?
Sure, I can do that. Let me go down to this one since it's fresh. Okay. All right. So you said, for an example, what if what if the only thing you have is the slash, right?
Yeah.
All right. We're going to use this. Now, in Cider, we'll use the same example. Slash. No, we'll do a different one. That way it jogs the memory. Let's just keep it at a slash 25. How about that?
Yeah.
Let's say I use a lane, for example. Say a lane, I need a slash 25. His first question to me is, okay, you need a slash 25. When we bring this up, in his mind, he already knows. James either wants me to he needs 128 addresses so he can put 126 usable devices on there. His mind's gonna go there already. Are y'all with me already? So it doesn't matter what the IP address is. Elaine knows, oh, James needs 126 usable addresses. That's all he knows in his mind. So, now the thing is, Elaine's next question is, what addresses do you want me to use? Now he's really breaking the rules. He's like, do you want me to use a Class A, Class B, or Class C? Because I can really do whatever I want. Because what remains consistent is that he's in the 4th octet, using 4th octet numbers. No matter what I tell him the IP address is, he's always going to come out to a 255, 255, 255 dot something. Let me show you why. Say Elaine just wants to he's feeling froggy today. I say, Elaine, just pick an address. He says, cool, all right. I want to start this other LAN at 172.16.0.88. It's going to be a slash 29. Who's with me? Now, in this case with Cider, this is what the trash you'll see on the exam. So as many times we got to walk through this. This is only day 2. I can create whatever IP address scheme I want. The only thing I pay attention to is that right there, which dictates what subnet mask I'm going to use. All right. Who's with me? All right. What matters is the slash bit position that is going to give me all of my telemetry as I go up. You do not need another chart. Nope. Let me give you an example. I can use whatever address I want. I'm breaking the rules. Elaine says we're going to start with 88/29. I already know my subnet mask because where that bit position is, it's already 255.255.255. something. And it's a 29. So I'll go back to my chart. Oh, excuse me, 25. I'm sorry. 25. I do apologize. I go back to my chart. Well, I know what my subnet mask is. Anything I put on here is going to be a 128.
128.
All right. Now it's up to me to figure out what my lands are. All right. So this is what I do. If I do the quick math, what's 128 times 2?
156.
256.
256, sorry. 256.
I know I can make 2 lands. So what I do is, here's the long way that I showed you guys before. Start with your bit size. Start with 0, go to 128. Then I told you what's 128 plus 128 is 256. Boom, we can't go past 255. Right? Then I said back it up so you know where your pool ends and where your pool begins. Remember I said that? My usable addresses, 1 to 20, 126. My usable address is in the middle, 129 to 254. I'm done. I can't use 256. There's my 2 lands right there. I can make 2 lands by using the block size, 128, starting with 0.
127, okay.
So Elaine, after doing that, where does this host number live on these 2 lands?
Your host number would be
land number 1 or land number 2? You are correct. It fits right in here. That means he just found the rest of my telemetry right here. The network ID is the first address, 172.16.0.0. The last address is the broadcast ID, 172.16.0.127. The subnet mask, well, the pool is .1 through .126. And the subnet mask is 128. It's right there. It's in the column, /25 at the top, subnet mask. Who caught that?
The 128.
Need some feedback, some yeses, some no's, some chat, something.
And
okay. And then how do you do the reserves? Now the reserves are later, but this is how you would do it. My pool of addresses are here. All I would do is this. Say like I have 5 devices that need static addresses. I do not want these to move. So all I'm going to do is I'm reserving in the DHCP. This is only for learning purposes only. 1, I need 5 addresses. .1, .2, .3, .4, .5. That's the reservation I'm putting in the DHCP for this land. Those will automatically get blocked off. Nobody can use them but until I apply them to a device.
And so those that you just reserved, you take those from the 1 through the 26 that you have?
Correct.
Okay.
So that means I have a printer. I have to go to the printer and physically do this in the settings. When it asks for the address, I have to go, 172.16.0.1 subnet mask 255.255.255.128. Hit enter. Now the printer works. Now you get it? I got a security camera. It's a private 172.16.0.2. I go into the application interface of the camera. I do 255.255.255.128. They all live on the same network. Those addresses never change. So if the power went out and it came back up, the router knows to give these same addresses back to those devices. Nobody else can use them but the device that presents the address to the DHCP. Does that make sense?
Yeah.
These are your critical ones. Correct. Following on the same network scheme. So now they all can talk. Okay, now watch this. I'm setting up another one. That's why we can do this all day. The other stuff we can learn, we can catch up on that. This is the stuff we need to do. All right. Here's the other one. I got a camera for the patio. I just set it up. I'm good, right? Good, right?
No.
Should that be 172.16?
Yes.
No.
Bingo, my man. This is the stuff you have to do on the exam. They will do this and say one device can't talk to another one because you didn't configure it correctly.
Yeah.
Then you'll have this.
Sir, should that third device stay as 0.2?
Oh, it's be 0.3.
Yeah, it should be 3.
Yep. Yeah. Correct. You found something else. See, that's what happens when you have to pick from a drop-down box and pick the proper configuration.
No.
If that second frame right there would have stayed as 18, what would have been like the response of trying to connect?
It wouldn't operate.
What y'all just said, there'll be a drop-down box, and you have to correct the IP address.
Yeah.
Or else it wouldn't connect.
It can't talk to nobody because you got the right subnet mask, but that 18 is that 18.0 somewhere in here?
No, so yeah,
that means that device is on an island by itself and can't talk to nobody. It's not even recognized. They'll be like, I don't know who you are.
Yeah.
You don't live on my street. Yeah. Your address is totally different from what I gave out. I have no clue who you are. And it will not allow you to talk to nobody. Does that make sense? Elaine, is this what you needed to see? And then you have an IP phone. 162. Now this is me at work rushing. Oh man, I gotta get to the game. 255. Hold on, I'm coming. Carpool's leaving. All right, boom. What? Michael, why? That's right. I rushed out the door. It's right. It's right. What's wrong with it?
255.242 is right.
No, the 242 is incorrect.
It is right? What's the chart say? The subnet mask. What's the 242 subnet mask?
That's for a /31 network.
Bingo. You just identified something that you'll see on the exam right there. I'm on a 25. I gave it a subnet mask of what? Of what, Michael?
31.
I gave it of a 31.
So it's not gonna talk.
That IP phone is can't talk to nobody.
Yeah.
So from the drop down menu, I have to pick the correct one. That should be on the 128. That's why I can't talk.
But will it have some kind of interconnectivity, or it'll kind of function because it's like on the right IP scheme, but not on the right subnet mask?
You'll get a steady green light to say, I'm getting a signal. It'll look like you're getting something, but you're not, because you have to do, this is what you do.
Oh, you have to config the address.
You have to do IP config / all to see, okay, does the telemetry from that computer match what they have in the DHCP server for this LAN, this local area network? If anything in there does not match what I loaded, it's not going to be able to talk to nobody. Those addresses, see it? I told y'all, Elaine's got the light bulb going off. I see it glowing.
Yeah.
Y'all good? Now do you understand it?
Yeah, so I used to so I'm pretty much I
Network mask 255.255.255, whatever. You are correct, Mike. If you're in there, that's why it's very important to watch what slash you're on. This tells you right here, oh, that's a Class C address. The first three automatically is 255 blank something. Y'all want to step the game up a little bit? Who's ready?
I have a question real quick.
All right.
So 128 and LAN 2 would be the number of hosts, and then the .88 is like the host number, like the name of the host.
That's the IP address that host snatched from the DHCP after they did DORA, discover, offer, request, acknowledge. That's the one that they got. Yep. Now, let's step it up a little bit. We're going to use this one. Y'all going to walk me through this one. Now, y'all noticed on that last one, I used a Class B address, didn't I? Who noticed that?
because you use the
I used the Class B address. But what mattered was the slash. Please pay it. This is where people fail the exam. That's why I'm spending so much time on this. Don't let the IP addresses fool you. I need you to concentrate on the slash position. Do you understand? If I gave you this, okay, here we go. Ready? Hey, what type of address is that? I don't need to know if it's public or private right now. I'm just trying to prove a point, okay? But you're correct. It's a Class A. So that means I need a Class A subnet mask, right? That means I need a Class A subnet mask, right? What did I just say? You just got fooled. You just got fooled for the exam. What did I, is it right, Mr. T? I got you, didn't I? Right, he just said it. No, James, you need a Class C. That bit position is in a Class C subnet. Fool me once, shame on me. Fool me twice, yeah. Watch this. Here's class A down here. Now, if I asked Mr. T if I did this, now it matters. Now I have to use a class A subnet mask. Go ahead, Mr. T, what you say?
Do you hear me? Yeah.
Yep, I hear you.
Yeah, that class A thing messed with me because I focus on IP address instead of slash. That's why my subnet say 2000.
Yep. So on the exam, they will fool a lot of people, or you'll get jumbled in your mind. You're like, what do I pay attention to? Do I pay attention to the IP address, or do I pay attention to the slash? If you're presented with a slash, pay attention to the slash first. Pay attention to the slash first. Nothing else. That will dictate your subnet mask. All right? Now, Elaine, Martin, what if I did this? Does that change anything for you?
No.
27? Oh, 29. Yes, it does change. Tells me I'm using a class C subnet mask. So I go back. Dot something. It's going to be dot something. In the category of a /29. Oh, it's going to be it's going to be a 248. Doesn't matter what the IP address is.
Yeah.
I'm in the 4th octet. Who's following me?
Yeah.
Okay, good.
Yeah.
No, you're getting there, Michael. Trust me, because everything you're answering, you're right on the flow. So you're on there. Jesus, you're getting it too. Charles, you're still there too. I see you. You just got to bring it all together. So that's why I'm bringing you this. What is it? What's the subnet mask for /24?
/24.
Zero, no?
24.
Zero, where?
25?
What's the whole subnet mask? What should it be?
It should be 255 times 3.0.
It is. That's what it is. You're correct.
Yeah.
0 is a placeholder. You have to skip it and drop the subnet mask over here. Yeah. Let's bring up the IP table. For a Class B address, meaning if you start messing with octets, darn it, I'm sorry, y'all. If I start messing with any octets from 17 to 24, I automatically have to use a Class B subnet mask right there. 255.255.0.0.
And both.
I could mess with the last one here. I was in the 4th octet. Look, 1, 2, 3, 4. Who's with me? Now that I'm in a Class B, I can mess with the first 3. 255.255.0. That's where your subnet mask goes right there. I leave this alone.
Okay, so
now,
both
when he told me my subnet mask was 255.255, where we at? Yeah, right up here. We're up here for this example. 255.25. There's the bingo. There's the subnet mask. This is a placeholder. We can't mess with it. That's for Class C.
So James, sir, if this was a Class A address and it was 255 times 3 zeros, would that mean that you changed the second octet?
Correct. And the rest will remain zeros.
Okay, so both. Okay. Basically,
Now you got it, Jesus. Okay. There you go. So as I move up with a different class of address, so Insider, it dictates what I can mess with. All right, so watch this. /24, you figured out that the subnet mask is 255. Why do we know this? It's right there. Wait a minute, it's not there. This all starts over here. This remains the same. This remains the same. So it will be 255/24. What will this be? See how this multiplies going up by 2? So 128 times 2 will be
256.
256 hosts I could put on here. I could put 256 hosts. 256 hosts can fit on a /24. Now, knowing this information, you should be able to tell me what the net ID and the broadcast ID will be, because there's only one LAN you can do. It's only one. Remember the bit? The one goes over? So what's the pool? What's the first one?
Net? Okay.
I'll start you out. 10.0.0. 10.0.0.0.
1.
0.
No, it's 0.
2. 10.0.0.2.
Oh yes, moved on by 1. Yes.
255.
Oh, you go 1 upon each.
I could put 256 hosts on here. 2 of them get backed out. The first one's going to be the net ID. That counts as a 0. That counts in binary. That's why we had to go 0 to 255, not 1 to 256. There you go. So that's what it would look like on the exam if you're presented with a /24. You have to know to adjust and move over. This is now where your subnet mask is at the top of that column. You leave this alone. You leave it as a 0 for the subnet mask. Your host ID will still be here. All your IDs will still be here. This dictates you are in the 3rd octet, because we have it right down here, 17 to 24.
So the question would have a /24 and give you the IP address and then ask you the rest for the net ID, the broadcast, the pool, and the subnet mask?
Yep. You just reverse it. Yep, you just figure it out. Because they'll try to trip you up here to say, here's a /24. There's a device on here that can't talk. You got to figure out, is that by using IP config /all, what's the IP address? And if it doesn't land within here, you got a problem. You'll find, and I'm gonna give you an example of what you'll see. All of this will be correct, but there's one device in there. When you do IP config /all, you're gonna see this as that device's IP address. What's the problem? This is the one you found. This is one device you found that IP address. You found it. What's wrong with it?
That one?
The one. So you'll see a drop down of a list of 3 available IP addresses you can change it to. One of them, the addresses that you can change it to, will be this. correct the IP address, put it back in the thing, you just solved the problem. Because 200 lives inside of here. On that same subnet mask, you just fixed it. Usually this happens. Go ahead, Mike.
That's a Class C, correct?
This is a Class A address.
Class A.
No,
You are in a Class, correct, yes. You are in a Class C subnet mask. So everything you do will have to have a Class C subnet mask. When you're messing with those binary bits between 17 and 24.
So the IP address up here, you said it's Class A?
It's a Class A address, but we're doing cider. I can do whatever I want. I can do whatever I want.
I'm trying to connect everything. It's not yet connected.
I got you. So here's the next step. In class full IP address, and I have to follow a preset chart. It is what it is. Don't mess with it. When I hand out 10s, it belongs to government agencies. I have to, these are the number in the network, so I could do blah. Here's the subnet mask I have to use. If I'm using CIDR and you see a subnet, if I'm using IP address schemes and I'm using anything in here as private, that subnet mask better be 255.0.0.0. Period. Exclamation mark. Don't pass go. Don't do nothing else. You're done. Easy setup, right?
So the subnet mask that you got that is wrong. It should be the 255.0.0.0.
If I'm using class full addressing, meaning I'm following a set of rules out the box. This is out the box, add water. That's all you do.
Oh, how are you doing?
If I want to
from the
create
US.
subnets using classless,
Where are you
interdomain
currently
routing,
watching from?
this is how you know. You'll see a slash. You'll be like, might be like, oh, they on that CIDR stuff. He created a LAN. He created a network. And now you got to figure out all this stuff. Does that make sense?
Yes and no.
All right, watch this. Dang it, I'm not in as administrator. Hold on. You can see it when you do it.
No, you just type the command round. That's it.
Oh, I did? Mm-hmm. Okay, all right, let me get out of there. I wasn't paying attention. Good catch. All right, let me go back in here then. All right, let's go back in. Boom. Let me slide it back over. IP config. Let me slow down a little bit. /all. Boom. Right there. Here's the IP address my hypervisor is using. Let me see if you tell it. Let me see if you can catch the difference. Let me get back to my regular home internet address. Okay. There it is. Is this class full or classless? Class full means it follows rules, it's set in stone, follow it. Used in the chart. Is this class full or classless? Meaning, look at the IP address. Does it fall into the classes? And does it use a predetermined subnet mask that I can't change?
Yes, class full.
Class full. Ain't nothing I could do. This is what my router's giving out. It's using a class full address. I can't mess with it. It's done. Yep. Nothing to see here, people. It's just handing out addresses. This is where it changes. Didn't I download a virtual machine?
Yeah.
My virtual machine uses this address.
240.
Now compare. You'll notice something's wrong.
That will be a class list.
Yeah.
Why?
It's not following me because you're in the class, you're in the class B, and with the, hold on.
I got you, Jesus. Let's see if Mike can, I want Mike to try to fit it. I see you, Jesus, you good. Go ahead, Mike. Let's talk through it. Let's talk again. What's the class of the IP address?
The third octet is should be 0. You're at 240.
That means I'm in my class list or not? I'm outside of
your class list.
So meaning, if you see 240 in the subnet mask, what's the slash? Ah, see, now that's where we're getting into finding stuff. That's the subnet mask. It's a 240. Now I can go up to my chart and be like, if all of this stuff starts, wait a minute.
Yeah.
If all of this starts over here, 23, 24, 22, 21, 20? That's a slash 20 right there. In the third octet. Oh, this stuff repeats. I just copy and paste this to the third octet. That's how I know. That's a 240. 1, 24, 23, 22, 21, 20. Oh, they're using a slash 20. Now, this is how you find out how many devices you can put on that network. 128. 128 times 2, 250. What's 128 times 2?
256.
256. Yeah. 256 times 2 is? I can.
Or
1 second. 512.
512, yeah.
512 times 2?
124.
1024. 1024 times 2?
2048.
Yep. So here we go. Slash 20. How many devices?
20.
Is it 2048?
Yeah, so 1, 2. That's what? 10 devices. 10?
I could put 4,096 devices on the slash 20. It just keeps multiplying by 2 as you go down. Slash 20. Oh, you can put 4,096 devices on there.
Multiply by 2.
Gotcha. We're looking at every aspect of this to figure this out. Jesus says, can you please go over the portion again, please? Which portion did you need, Jesus?
It was the portion where you got to slash 20 because I had assumed it was slash 28, so I'm trying to figure out from the 240 subnet masks how you got slash 20.
Okay, I got you. So in each subnet mask, in each octet of an IP address, didn't I tell you this gets used over and over and over again? Okay. So in subnet masks, for how many that you can use, this gets repeated over again in each octet too. So you'll see this and you'll see this. Does that make sense? It's just copy and paste. This is in each octet. All right. So all I did was say, here's my investigation. Mike began his investigation right here. He said, James, that don't look right. The difference between a class full and a class less is right there. In a class full, if I want to use a class B address, it has to be 255.255.0.0. Mike said, wait a minute, somebody put a 240 there. I said, you're right. Now that dictated, it's a class less. Somebody broke the rules. They made their own land. All right. So I simply went to the chart that we refer to over here. And hold on. And I said, 240, where does that live? So all I did was cut and paste both these two. I cut and pasted it in octet number 3 right here. And I counted backwards. That's all I did. 255 repeats itself on 1, and 255 repeats itself on 24. So 32 and 24, they both have 255. 31 and 23 both share 254. It repeats itself. So all I did was go down until I found it. 240. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh, they're using a /20. Do you see that? All right. That's all I did. I followed the chart in octet number 3. This repeats itself through all 4. Okay. Now, I use that same math. I said, it's a /20. So now I know 255.255.240.0. I can't mess with that. That's a class B subnet using CIDR. Then I went to a chart. Well, how many devices can I have on the class B? We did the math. Everything's times 2. It just keeps going up. Mm-hmm. So when we got to here, looking at the chart dictates on the /20, it's right there. I could put 4,096 devices on here. That's a lot. 4,096 times 2. If I get down to a /19, that's 8,192. The number just keeps getting bigger, all the way down to bit position 1 in the first octet.
Do we get this chart, or we have to just,
I dropped it in the chat yesterday.
No,
I can do it today.
No, on the test.
Oh, no, you don't. No, you do not, sir. They do not give it to you. Nope.
No chat makes.
Yep. Yeah. See, if we get down all the way to bit position number 1 and the numbers just keep doubling, 2,447,483,648 addresses can sit on bit position number 1 and octet number 1. Yeah. Yeah. You'll never go past this on the exam. You live here for the exam. Mr. T, I see your light bulb going off. You get it now, don't you? Yeah. Leah, you good? That's cool, Michael. Every step we get closer, you're fine.
Yeah.
Jesus, I think you got it.
I asked, are you saying that the bits themselves repeat within the slashes and that's how you get it? Because I'm still trying to correlate how you got to /20. I'm like lost in the sauce right there.
All right, here we go. Let me explain it to you another way.
Yeah.
I'm gonna use this. Let's just make some room down here. Let's just make some room on my notepad. Let me bring up my notepad. Let's just do this. How about that? Let's get all this out the way.
Yeah.
All right, ready? Here we go.
Yeah.
1, 2, 3, 4, 5, 6, 7, 8. Decimal. This is the first octet. The header at the top of that octet will be
That'll be octet 1 or
128. It's right here. 192. See how it's going? I will continually use that header information up here. That's how I got it in the third octet. So let's just change this to the third. And we're going to change this so you can relate. The first bit position in the third octet is 17. Here we go. 17, 18, 19, 20, 21, 22, 23, 24. Period. Third octet. Fourth octet over here. I think y'all know what that means. I don't want to go back and correct it. All right, here we go. 25, 26, 27, 28, 29, 30, 31, 32. Who's with me?
Yeah, good.
You good, Mike? All right, here we go. Now we're talking strictly devices. If I start with bit 1 over here, by each position, everything multiplied by 2, going right to left. Who's with me?
You said
all right.
Right to left multiplied by 2?
Dang it, how come the I don't want to stick? All right, here we go. This is your hosts, how many you can put on that land. Okay? We'll come back to the third column. We're going to leave that be for a second. So I'm going to put that as a placeholder. All right? Now, let's get to the top here. So here we go. We started out with 128. 128 divisible by 2, 64. $32, 16, 8, 4, 2. There it is, 1. Everything's divisible by 2 or times 2, whichever direction you want to go. So that means 128 times 2, as it keeps going from bit 32 all the way down to 1 to the first octet. Are you with me, Jesus? It doubles, 256. Let's get back to the top, since you got that now. We're in the fourth octet still. I'm past the decimal. Up here, we're looking at subnet mask. 128. What we did down here is we took 128 plus 64 gives us
192.
192. 128 plus 64 is 192.
Yeah.
192 plus 32 is, here's the chart right here. 224, 240, 248. $252. What's the next one? 254. 255. Who's with me? Each octet guess what? It's the same. They header for the subnet mask is the same. It doesn't change. It repeats itself over each octet. Now, here's your subnet mask.
And then that's what makes it a class A, B, and C.
Correct. Here's what changes. All right. When we get to here, things start to shift a little bit when you start getting over here. All right. 254. Okay. Am I able to get 254 plus 256 gives me 255 like we did over here? No. You got to shift a little bit. Remember that one I told you about? You got to move up one level. 2, 4, 4, 8. You know you're doing it right if you see 2 16s in a row. 32, 64, 128, 256.
And that's the available IPs.
That's how many subnets you can create. These are your LANs. Basically, this is how many LANs you can make.
So 0, 255 are not available before 1 to 254 are available, the pool.
Correct. Yes. So when you're looking at this is all right. We're good. Now we're moving in octet number 3/24. I can have 256 hosts on the LAN, but this is where it gets wonky. Now I can't do 128 plus 64 to give me 192. I have to, when it comes up here to give me the subnet mask, 254 plus 1 gives me 255. Right? So that's how I know here the subnet mask /24 is 255.255.255.0. Ah, James, I get it. Right? Over here on the /20, 240 is 240. Now here's the key. When we get over here, nothing repeats. You're done. Now it's just a matter of how many devices you can put on a LAN. 56 times 2, 512. 512 times 2, 1024. Who's seeing the math? 1024 times 2. You're there. Trust me. All of y'all are there. 1024. Where's my chart at? Somebody yell it out for me.
2048.
Chart.
It'd be
2048.
And then it'd be 4096.
This will be 4096.
And that's the available IPs that could be on the /20 network.
Yeah, correct. Yep. And this will be what, 8 something?
81, 12, 81.
Let me look at the chart. I can put it back for you. So it's for /19. It is. Yep, you're right. 8192. Yeah, you're right. 8192. So now LANs don't matter. The host gets so big. Divide what? Like for what? It gets crazy after a minute. See what I'm saying? And then on the /17, what is that going to be? That is, I'm looking at the chart. Dang.
Lot.
Oh, wait a minute. I had it backwards. That's a 19. Let me go back. I got ahead of myself on the chart.
/19. Yep. A lot.
Okay, I understand the whole class pool and class list, but but it doesn't follow its class list. Who decides that?
You do. You build out what you want to build out on the network. They're giving you the to do so.
So
Because
that
they
means
ran-
if you wanted to make it classless, you would have to type it in manually?
Correct.
Does the system automatically configure it for class full? And
Yes.
you just decide if you want to do classless. The system want to do classless. You have to decide, hey, I want to
You
do
gotta do
classless,
that.
and it still follow the rules if it's correct.
Correct.
Because if
When
it's
you when you signed up for internet service and got that router at home, you pulled it out the box and you just plugged it in, didn't you? Automatic class full addressing. It followed a predetermined chart, starting with the router's address, and it gave you a pool of addresses.
So I had
That's Xfinity.
I had missed a portion with the bits within the octets, and I think that's where I had lost translation, but I'm tracking now.
Yeah. And you know what? Keep asking it. That's what I'm here for, man. That's what I'm here for.
Can I make my
32.
router classless?
You can do that right now if you want to, but you got to configure the addresses.
Because if I do classless and mess up in the addresses, it won't work at all.
No, yep, it won't work.
Oh.
You can go in your router right now and give it the addresses you want it to have. See how this works now? Now do you see how it's coming together? At this point, we don't need to make LANs. Why? Look how many devices you sitting on them. That's why I told y'all, if I see y'all making a LAN with more than a /24, I'm gonna find you and hit you in the head. With a rubber band. Because all you're doing right now, at this point, you're causing issues for yourself. Who would agree with that?
Yeah, that's just.
I feel like a puffy meme right now. I really feel like that.
Huh?
That puffy meme.
The puffy meme? Okay.
Where they stare at each other? I feel like that right now.
Mm-hmm.
Like I understand.
You're about to get it, aren't you? So Charles says, and thanks for talking about this. Thanks for staying through break so everybody can get it at the same time. You need me. Everybody can get it at the same time. I'd rather sit through a break. We could take a long break and get it, right? Because I don't want to interrupt the process. So here's the question. Charles says, so would the IP address be 172.16.8192? No, sir.
No, there's.
Your address scheme would be if you're in a third address. Yes, correct, Mr. T. Remember, technically you can't go past 255 as an IP address, ever. It stops at 255. That's all. That's why I like Juvenile. You back that thing up to 255.
Yeah.
Because that's all you can go to. 0 to 255. That's where you live.
That's how I feel.
All IP addresses on every LAN cannot go past 255.
Okay, so.
Correct. Even when you create multiple lanes, you live between 0 and 255. Yep. Leah's getting it. I see. Oh, unless she's laughing at something else. I think
So
she
do
got
you
it.
you can have as many lands as you want then?
You can pick a bazillion lands.
Because you get the 512 and you got one land. Which obviously you have to have 2 lands because you can't go past 255, right? So
yeah. So generally, what happens is this number can continue and you could put it over here, but why would you even do why? Why do you want to do that? This is a placeholder. I can come over here and do 128.
it just doesn't count past the 2 then. Like who cares?
It doesn't count past
you can't have those.
Yeah.
It has to be 2.
You can't even use it. You
Right.
can't even use this.
Yeah.
This you can't even use that. Just like you can't use 32. 32 is off limits. See it? I'm sorry, I got this all out of whack. I apologize. See that? Just for intensive purposes. See that right there? I can't use that. That 30, wait a minute. I think I'm looking at the wrong column. Thanks for bearing with me, guys. Sorry about that. That 256 should be right there at the 1. Here we go. All right, here we go. For educational purposes only, just look right here. Just like bit position number 32, you can't use it. Look how many hosts are available.
Oh, just 1, 2.
How many addresses do you need for any LAN? For any LAN, how many addresses do you need? Minimum.
2 at
Broadcast ID, net ID. This only gives me 1. I can't use it. Just like you noticed over here, I could make 512, put 512 devices here, 1 subnet. I could use that, right? I can't use this. This is out of bounds. Just like I can't use subnet number 0. Because it gives a default subnet mask, because 255.255.255.255, and the default address is 0. Nobody uses it. That's a break glass in case of emergency address that only the system would use. So you can't use 1 and you can't use 32. They're off limits. Right? Leah, you getting it? Martin, you getting closer? Just a little bit closer? Be Weezy? All right. Yeah. Kevo. What? Okay. No problem. Mike is right there. He's about to break the glass. I swear it looks like he's about to jump so lost, James. All right. So what we're going to do, we're going to take a break. We're going to get back.
Yeah.
And then we'll have to get into a lecture probably at 4 o'clock. But until then, we could still just talk about network ID and stuff.
The lecture might help me out a little bit.
It has nothing to do with binary, though.
In that case, it will not help me out.
But I'll work with you when we get back. Cool? Let's take 10 minutes.
All right.
No. Take 15 because I robbed a break. 15 minutes. Welcome back, everybody. There is a minor correction I need to make. I was 1 bit off. I was like, why is my chart off? I'm surprised one of y'all didn't catch it. All right. 255. By 12. This is what it should be. I think I got off because my chart was kind of crooked. So here's the correct way to look at this. So do you guys see this here? I was wondering why my chart was off. All right, here we go. /23.
In this video, we'll describe the characteristics of the denial.
That's why I had the 24. That's what
attack, which involves a server or device simply being targeted and flooded with many packets or requests to the point where it simply becomes overloaded and becomes unable to perform its normal functions. Now,
if we look at the chart, this is how you figure this out. 256. This is where the decimal is, where the third octet ends, fourth octet begins.
But a DOS attack on its own,
right?
Typically a single
you have the one here. This will be 256, and
multiple systems, often referred to as drones or bots, all run the same attack.
That's the way it should read.
Target or maybe a few targets
for the third octet. Naughty outside. Sorry about my chart was off, so I apologize. So all this does is correlate to the bit position. So 24, 256 hosts.
Resources are simply consumed at a rate that overwhelms the network. So
this is how many lands.
Fragmentation, whereby disassembled packets.
Here's the VLAN.
Manipulated so that they can't be reassembled. TCP state exhaustion, which is typically
subnet mask.
Exhaust its capabilities in terms of
been talking this stuff all day. I'm getting rid of them. So that's what you would see for the third octet. Now, does that make sense? Correlates directly with the chart. /24, I could put 256 hosts on it. /23, I could do 512 because 256 times 2 is 512. Right? And even if I go over here and do a /22, as you can see on the chart, it's 1024, right? /22, if I go up, 252.
And a standard ping request stops after 4 requests and responses. But the command can also be altered so that it doesn't.
252 is the ID.
Now, this is not any kind of specially designed
of the subnet mask.
Ping is a standard built-in component of the TCP/IP protocol used for legitimate testing and troubleshooting. It can just unfortunately be misused.
23 is 254.
As an example, on a Windows-based system, the command of ping-t tells the originating system to just keep pinging until it's manually stopped. And
which tells me
-L
252 plus 2 gives me 254 right there.
Up to 65,527.
Subnet mask right here. If we go down,
default, which is only 32 bytes.
For bit position 22, it's 252. Yep. And we're good. All right. So now we got 1, 2. I guarantee that's 4. Because 21 is 248. There it is. It starts repeating itself. Now you start seeing the cycle in it.
All focused on the same target. You can see how it gets its name, the ping of death. Eventually, the target simply becomes overwhelmed.
And there you go. So that's what it looks like for /22, 23, and 24.
The sender receive a reply from the recipient.
There's where it repeats on your second one to make lands.
Disable that requirement. So
it flips. So instead of doubling going to the right, it doubles going to the left. For how many lands, how many subnets you can create. So this one will be 8.
Because the ping utility uses the internet control message protocol. A UDP flood sends repeated user datagram packets to the target with no application associated with the packets, thereby forcing the target to continually search for a port that is being used by any application, but of course none will be found. SYN or synchronization floods,
That'd be
which are
2048.
also referred to as TCP floods, work by sending repeated requests for synchronization because TCP establishes
Now we're looking at a
sessions
/21.
for communicating. But SYN requests require the sender to acknowledge the session, but the attacker who is sending these requests simply does not respond to the acknowledgements, and every
Then the next one would be, if you doubled it, this one would be a 16. It just goes up from there. But for the exam, you should see nothing past a 23 going
whereby the packets are disassembled so that they'll have to be reassembled at the target, but again,
third
they're
octet.
manipulated in such a way that they can't be reassembled. So the attempt to do so by the
Most usable things that you might see on the exam. So go ahead and write that down so you got it, or screenshot it,
might also
or snip it.
to ask, why do they occur? Well, the primary reason
I'll take a snippet for you.
be animosity in one form or another, such as a disgruntled employee or a former employee who feels that they were wrongly dismissed, or perhaps an unscrupulous competitor who would profit from your absence might be the motivation, and not just
And here you go. Put it in the chat.
but also for the potential damage to your reputation.
There you
which
go.
might cause you to lose customers to the competitor. Hacktivism is a combination
I'll
of
do
hacktivism
another one
and
solid
activism,
for you. I will
where
put
it's
this. Who wants me to put this chart
causing
back in here?
protest of your services or your organization in general.
Those who did not get
They
it.
could also be used as a means to coerce ransom from the target. For example, the attacker might state that if the ransom is not paid, then the attacks will continue. And believe it or not, in some cases, it is actually just for general troublemaking or sport.
Y'all look wore out today. This cider wearing y'all out.
Attackers are trying to see who can launch the most successful attacks.
Yes, James, you're killing us.
Or supposedly secure targets. So then, in terms of protecting yourself against DOS attacks, or at least
Subnetting cheat sheet. There you go.
this typically requires
Oh, can't open it because it's open over here. Let me close it. Now I can share it. And it won't let me share it. How about copy?
Every type of DOS
How about
attack
pasting?
will involve a significant increase in overall.
There you go. If you didn't get it, there it is.
Easier to identify when compared to that baseline. And you should also perform.
Okay, let's take a break from that for a second. Let's get into something else.
See how well your defense.
And then Kevin will circle back around. I'm gonna give you a mind break.
And if you feel that perhaps you don't have the expertise to do so internally, there are many third-party entities that can provide these types of simulated attacks as part of a vulnerability assessment. Then formulating a post-attack.
All right, let's talk about
to identify any vulnerabilities that were discovered.
configuring interfaces and switches.
Shore up your defenses in the event.
Let's do that for a little while.
Yeah.
Unfortunately,
Get into day 3.
the attack itself, because
So we just had a mind-blowing experience and got beat up talking about cider. But I think here's the thing that we came out of it. Jesus and Michael kind of, and Mr. T nailed it on the head here. Elaine, you did too. Kind of like all of y'all together kind of formulated it. When you get a router or all-in-one device from your ISP, it's already pre-configured. You don't have to worry about it. You plug it up, you're gonna get class full addressing. You don't mess with anything. As per the chart, it's gonna automatically address. Bam, you don't touch nothing. Cider is when you have, as we can see, thousands upon thousands of devices that you may have. You need to segment stuff to keep people out of certain computers and allow people to get to other computers. It's a security feature. Private addressing. So it allows you to make up your series of addresses that you want to use. And then for the chart that we created allows you to identify, like Michael said, I said, look at mine. And it had 255.255.240.0. Mike noticed, yo, that's cider. They made up that address. Yes, that's the important part. Then you have to use it to figure out what the range is and all that stuff. But that's how you do the easily identify knowing what the difference is. Jesus says, so will this be commonly used to configure? Yes, yes, and yes. Some SOHO companies you get to as the network administrator, they want security and they want you to lock out certain individuals, especially what if it's a small upcoming IT company? Do you think they want class full addressing for everything they have at work? No, they're an IT company.
Yeah.
They can be like, hey, Zeus, hey, thanks for getting here. We just set up last week, brand new building. I need you to segment everything. And then that's when you start chopping stuff up with slashes, right? And putting it in a DHCP server. So great question. So as it comes to what we need to know now, here's the important part. Please remember this. IP addresses or switches belong to the interface, not the port directly. You're actually configuring IP addresses to the interface of the port. Okay? No problem, Leah. To the port. Okay? So like if you have a range of IP addresses, they're configured to the, of course you have to enable the port. You bring up the port and you might put the range of addresses, but that's how we kind of do the network talking lingo. Because you can always move an IP address from one port interface to another. MAC address lives with the device. You can't move that. Okay? So the port is just the correct. The port will be just the endpoint, and you'll configure the port with either the range of addresses that's going to live on there with a local area network, or configure the interface to hold the IP address to the connecting device. Okay? As we get into this and talk about it, we're going to be delving into domain number 2 and 5. Domain number 2 talks about configuring switch and its features, given a scenario, troubleshoot the cabling, the interface, troubleshooting common issues, and use the appropriate tool. Now, we're not going to get through this entire lesson today. I just want to get into it so we can start talking about it. The objectives of this lesson, we're going to talk about the network types, characteristics. You know the OSI model layers, which is good. Bring up your chart so as we follow along, you can see the GIF, the graph around, and then explain the troubleshooting methodology. Now, we went through a couple of troubleshooting as we talked about CIDR. We've shown a couple of things that you might see on the exam that they will test you on. Now, this is the only thing I'm going to ask you about CIDR during this lesson. What things can you get wrong where computers can't talk to each other when you're using CIDR? You have to be careful when you configure laptops and desktops to get on the network. What can you mess up?
Subnets.
The IPs and the subnets. Yep. That bit position, that slash, tells you all the information you need to know. I lied. I'm about to ask you another question. I'm sorry. That slash tells you what?
Bit position.
We know the IP and the subnet. What else? One more thing.
Bit position.
Bit position. Now it's telling you what octet you live in so you can make the appropriate subnet mask. Not necessarily the appropriate IP address, but you got to get the mask first so the list of pool addresses can live on that street. All right, so good stuff there. So as we get into it, the network interface card, here it is a transceiver component. Right here is the interface where the RJ45 will be inserted. That's the interface, connects the host to the wire to wireless transmission, has the unique MAC address, and may have multiple ports. And the cool thing about the NIC card, you can get into that NIC and you can change anything you want. Common symptoms of NIC issues include if you start to have failure or what they call port flapping, you can get that too. Port flapping. I get connectivity and then I don't get connectivity. I get connectivity, then I don't. Then you don't get nothing. Then all of a sudden it comes back, right? That's port flapping. There's something's wrong in your configuration. We talked a little bit about this yesterday. A couple of things you want to check is, if you're at home on a Soho router, is it half or full duplex? What's the configuration? What's another thing you can check? Michael says flapping was a config issue or reseating the issue that came. Yep, you're correct. It might be the card. You're right. Somebody might have dropped it. And you got to make sure it's seated, right? Because all those little channels where the PCIe sit, not seated correctly. Here's an obvious one right now. What if you're using, let's say you got a 1 gigabit NIC. Tell me what the problem here is. 1 gigabit NIC, but you're using incompatible. My NIC card is on a high-speed highway saying, I'm ready for the gigabit connection. It's too slow. You're shoving a Cat3 cable in, and it can only handle 10 megabits per second. What the heck? What are you doing here? Like, the cable cannot keep up with what I want to do. It's incompatible. So you got to watch that too. Then you get device manager errors. That's when you bring up your device manager.msc Microsoft console, right click on it. Remember, you'll see stop signs or yellow stop signs that tell you that the device has been disabled or is not working properly, and then it'll give you a status under it or why it's not working. And then you get network setting error messages. Now, when we look at modular transceivers, now your NIC card is a transceiver. Let's not forget, it's just 2 words put together: transmit, receive. So if you have modular transceivers, as we saw in the video with the young lady earlier, they're right here. There's your transceivers that they put into the slot to help transmit and receive data. Now with this one, I'm gonna tell you right now, what connection is this? What's the terminator? RJ45. When you see these transceivers being used like this, this is what they call a fibre or fiber switch. Transceivers slide into here because you can't stick these in here and it goes. That's not gonna fit. You got to put a transceiver in the slot and connect the fiber connectors to it so the machine can receive the signal properly. That's what transceivers for. It continues the transmission of the medium to fit inside of the appliance. That's all. All right? It's just a continuation. All right? But you have to make sure your transceivers for a fiber switch can handle what the line is pushing. All right? The next thing we have is everything operates at the data link layer. This is the data link getting a connection. If you're having transceiver issues, mismatched ports, you got no link, packet loss. I think I saw Mr. T voice this. Slow. There's something wrong with the interface. You have to log into the switch or the router as an appliance you have to look around in the application interface to make sure everything's correct. These frames start moving. This is a shotgun question for Mr. Charles. Bits, frames, packet segments. What's layer of frames on? Bits, frames, packets, segments. He's studying this, y'all, so that's why I'm doing this to him.
Wait, what was the...
This hangs him up a little.
What was the question again?
What layer of the OSI model frames originate on?
Data link.
Correct. Layer 2. You the man. Thank you. All right. So with that, when frames start moving, you'll have the preamble. Tells you the synchronization sequence. Kevin dropped this in the chat the other day. Synchronization, acknowledgement, TCP traffic. Then you'll have this right after it. It's called the SFD, Start Frame Delimiter. Basically what it's saying, this is like a bookmark to say, hey, everything after this, here's the real information coming at you. It's a coming. Be ready for it. It's a coming. All right. So this is kind of like, hey, this is what you should be expecting when I start to transmit. And this says, okay, we're ready to go. This is the start finish line, the delimiter. And then after that, destination MAC, source MAC, Ethernet type, payload, and functional check. The MAC address, okay, is 48-bit alphanumeric identifier. And it's a pair of hexadecimal digits. The first 24 hexadecimal characters this is on the exam, truly, this is right here. It's the organizationally unique identifier. It's the OUI. Basically, it tells you the manufacturer. This in sequential hexadecimal will tell you the device's ID number and the day it was manufactured. 24 is the OUI. The last 24 is the device ID. Now, there are websites where you can look up MAC addresses by OUI. You can actually Google that. Okay. Now, when you come down to this, when you're trying to route inside a network, so to speak, everything can be brought down to what they call a MAC address broadcast. If one machine wanted to talk to another machine on the inside of a network, it would use a broadcast address, okay? And that address that they use, now you're still going to get a preamble, SFD, destination MAC, source MAC. The destination MAC for everybody is going to be, now watch this, 0, 0, 0, 0, 0. It's a default address. If we look at this, I'm in the wrong thing. Here we go. Doink. Now, if you can bring this up, if you want to look for a hexadecimal chart, this is what we're seeing. In a hexadecimal chart, oh, wait a minute. My screen share stopped. All right, here we go. In the hexadecimal chart, this is what we're looking at. Anytime now. Here we go. The letters that you're going to use for hexadecimal are A through F, 0 through 9. A through F, and 0 through 9 for hexadecimal. Okay. This is the hexadecimal code conversion. And here's the one that you'll see for ASCII. Everything that you type will be assigned a hex number. These are all the characters, what they really look like behind the scenes. All right. So that's good to have. There's several of them out there. Here's another one, a hexadecimal reference chart. If you want to get into it that way. Okay. So FFFF is the broadcast address for MAC addresses, for using a MAC, media access control. All right. And it just keeps going and going and going if you want to use it. Now you can this up, and there's several different charts that you can refer to. Quick question for you. During a new fiber optic link setup between a router and a switch, you observe no connectivity. Despite all equipment being operational, what troubleshooting step should you be considered to resolve? Remember I told you get these type of questions? They'll put you in the troubleshooting step model and say, what's your next thing? What do you got to do? You observe no connectivity. Now, it's saying during a new fiber optic link setup, that means you're setting it up. Okay? You observe no connectivity, despite everything that the equipment telling you is saying that it's working. What troubleshooting step should you be considered to resolve at this issue? A couple of folks are saying 2. Swap the fiber strands at one end to correct potential transmitter and receiver misalignment. Change to duplex settings, replace the switch, or reconfigure the router's routing table. Ooh. Which one of these is way too intensive that you would not even do? That's 1 and 4. 3 and 4, I wouldn't touch. That takes too much work. Something basic is wrong. It's either the simple thing, change the duplex settings, or swap. Now, out of these 2, which is the easier one to try first? You think 1's the easier one? 2, Mike says 2. Replacing a cable is always easier than trying to log in somewhere and change something. Right? All right, hold that thought. Y'all are saying 1 and 2, so we're gonna see. A technician is troubleshooting a workstation at MyCC. The workstation is suffering from intermittent connectivity. The technician notices that the STP shielded twisted pair cable pairs are not completely twisted near the connector. Which of the following issues may be experienced because of this? Ooh. Crosstalk, huh? Watch this. Bam. 2 is the right crosstalk, and you got it right. Swap the strands. The easiest thing you can do they want you to do the easiest thing first. The last thing they want you to do is taking stuff apart and messing with configurations, especially if they're presenting you with 2 of the easiest things you can possibly do. You want to throw this out. You do not want it. This ain't the first place you want to go. Replacing a whole switch and reconfiguring a routing table. All right. So good job on that one. Ethernet switches. Now we're getting down into it. Here we go. Now, if we're looking at this, let me do the slideshow. I want to have it in full view. Enable. All right, slideshow. Yeah. We'll do it that way. There you go. I think you can see it good there. Now, here we have hub. Is the hub smart or is it dumb? Yep, it's dumb. What makes it dumb? Mr. T puts it there. Correct. It just repeats stuff out. Just yells at everybody. Has no control, right? So if D wanted to talk to A and it goes through the hub yells at everybody. Yo, A, you here? A's like, I'm right here. Why are you yelling? Why are you yelling at me? Can't you just talk to me one-on-one? Well, that's what a switch does. A switch says, I don't need to yell. Hey, you still over there? Yeah, I'm here. Here you go. A hub is like, yo, y'all see Mike?
Yeah.
Yep. But a switch uses a routing table. It remembers, yeah, I saw A in here. They came in door number 1 before. Let me check to see if they're still over there. Yep, they're still there. Here you go. Right? So that's cool. When you're seeing bridges are pretty cool too. Now, this is something that you have inside of your router, all-in-one devices, switches, and layer 3. This is pretty cool. If you were to log to your router right now, you actually have a bridge function. Let me tell you what it does. All right. Here's Martin's network over here. He lives at 1001 on this street. Well, his neighbor in the next house over, they have a network. Martin and the neighbor become good friends, and they're like, yo, man, do you game? Yeah, I game. You in IT? Yeah, I'm in IT. Yeah, man, why don't we just bridge networks together and we can just share stuff directly? Martin's like, I don't know, man, I barely know you. Neighbor's like, man, it's cool, man, we're good. So they go into each other's router, they go into bridge mode, and what happens? They're gonna designate specific IP addresses for this IP to talk directly to his router, and then in his router, he's gonna directly put an IP to talk to Martin's router. Now they just opened a bridge. Now they no longer have to come out to the front stoop and drink coffee and chit chat. They can sit inside their homes and use the bridge to voice chat. Hey, what's up over there? I didn't do nothing. What you doing? Here's a file for you. So a bridge takes 2 networks and joins them together to act as one, even though they are separate. Right? Tells you right here, bring separate physical network segments together while keeping all nodes in the same logical network. Okay? So basically, what's going on, Martin says, I live over here, this is my stuff. This is you live over here with your stuff, but we'll bridge stuff together. But your stuff is still totally separate from mine. We'll just use it to move information back and forth. I'm giving it permission to leave my house, to go play at your house, to come back. All right? With switches, as we stated before, if A wanted to talk to D, A will go through the switch on the switch port number 1, out of switch 2, 3, and 4. The switch might broadcast to say, hey, y'all seen D? Or by the routing table, it knows D's over there and it'll just straight send it. It may use a broadcast to say, I can't remember seeing D. There it is. D will respond. And then they'll route to D. Okay? So it's might be a broadcast message that they send out to try to figure out where the computer was. Switches can come in different flavors, yo. The first flavors we see are unmanaged and managed. We gave an example of that when you have your class full addressing already put inside your router when you get it from Cox. That is an unmanaged switch. Take it out the box, plug it in, do the ... Step 3, done. Your router's up. Right? A managed switch, now Michael needs to go in there and configure CIDR. He needs to make sure he manages firewall settings, open and close ports. He's like, no go. Right? But you'll call Brian. Brian will help you. Brian will walk you through it. Brian's like, what? Yeah, I got it. He loves that stuff. And then that's when you have to manage the switch. You can have a modular switch versus a fixed switch. Here's the difference. A modular switch, you can marry it up with another switch to take advantage of all those ports. For instance, what if I have a 24-port regular switch and I have another, let's say, 12-port switch? But for one LAN, I want to use all of those and put them together where it's modular. I'll just connect or stack the two switches together, right? Create those to work for one LAN with separate computers in each port, or I can configure it with a whole bunch of VLANs. But I'm using both of those switches as one. That's modular. Fixed. Hey, it comes with a set number of ports. Ain't nothing you can do. Sorry, you're done. You got 12, you can only use 12. I'm not modular. This is what you pay for. Sorry. The next one you have is a desktop versus a rack. And this is very simple. This is on the test. Y'all ready? A desktop switch means you set it on the desk. Bad joke. You just set all you do is take the switch, you be like, I ain't got nowhere to put it. Nah, I just put it on my desk. That's all it is. It's not sitting in a rack. That's all. Nothing to see here. And in stackables, you can connect them together and they can be managed as a single unit. So stackable and modular can be interchangeable. Intelligence. Yep. This switch is intelligent over here. It has the address book that it used in there with MAC addresses, reduces network congestion, and it's not yelling at everybody. This operates on the physical layer, just a transmission medium. That's it. All right. Hub learns the MAC addresses of devices connected to it and uses the information to forward data only to the intended recipient. That should be over here. That is not right. Okay. Hub has no brain. So the check mark should be over here. Okay. And it learns the MAC addresses. All right. We'll go for 15 more minutes and we'll wrap up the lesson for today. Now, switches are pretty cool. They have this thing called link aggregation. Okay. Link aggregation simply means we're combining two ports together to make one logical channel. Seeing it right here. You take two ports. You have to go inside the switch and configure this. This does not happen automatically. You have to do it. You'll configure those two ports to work together, superpowers combined, and you'll get full bandwidth and connectivity out of those two, and it's good for redundancy. So if one port goes down, the other port will catch the slack, and things keep on going. As you can see here, there's a 2-port, 1 gigabit per second NIC cards in here. So what they did is they combined channels. Two ports became now 4. They have 1 each. Combined it to make 2 ports. So now you have 4 gigabit channel all in one. And then they'll aggregate here, what they call LACP. Ooh. All right. You're going to see this term on the exam. LACP. It is Link Aggregation Control Protocol. If I can sum this up, to not make this as much as it is confusion for you. All you're doing is opening up a super highway between two switches. One port transmits straight to another port. The other port receives straight from the other port. That's it. One direct IP address and port number straight to another IP address and port number on another switch. I don't need you to go through a routing table. I'm telling you where I want you to go. So I don't slow down bandwidth being transmitted on my network. We don't have time for that. I'm directly telling you, I want to talk to Kevin and no one else. Here's his address. That's Link Aggregation Control Protocol, LACP. When information is moved, traditionally, this is the default setting. MTU is set at 1500 bytes. Jumbo frames, remember I said 9,200 something? Boom, here we go. 92, 116 bytes. But you have to go into the NIC card and set that up. Okay, where did it go? I heard something go bling. Oh, here it goes. All right, here we go. Did I lose y'all? Y'all still there?
Yeah.
Oh, there you go. What's going on my computer? So this is what you'll see. So if I go down to my NIC card or network adapters, here's my Ethernet connection, go into my properties, or there's my virtual box Ethernet adapter. I can go in here and like change settings after I put in the administrator password. Okay. This is more like a super user, not really administrator. Here's my adapter. So if I wanted to do any advanced stuff, whoop, here we go. See it? Adapter properties advanced. What does that say? I can turn on jumbo packet on my NIC, especially if I got a lot of data moving. I can enable it. See, I could say 4088 or go all the way up to 9014 bytes. I could turn that on, hit OK, and it will install that. Next, speed and duplex. You'll see this on the exam, so please know how to answer it. You can go to your NIC card. Typically, it comes on default to auto-negotiate between half duplex and full duplex. Okay? But you want to go here and check if it's there. If it's not, here you go. You have to manually configure what you want it to do. When will you use this feature? We're all in the military, deployed on FOBs or on bases overseas. Why do you think they will want to do this? What's the purpose? You don't want it to auto-negotiate. You want to set it. If I'm overseas, Michael's setting up satellites to bring in internet to a forward operating base with 200 people on it. I have to be mindful of bandwidth, don't I? What if I want to regulate everybody's computer to only do 10 megabits per second? Full duplex. Now I'm conserving bandwidth on the base. Now you just can't sit there and, yep, it's a data cap. As a network administrator, this helps me out because I can look at all my telemetry coming from the satellite and I'm regulating how much you can use. That means you can't sit up there playing PlayStation for 10 hours a day. You're only getting 10 megabits per second. You're getting a weak signal, bro. No. Then you have your checksums, and this is where you do the wake on LAN magic packet. So if your computer is off, I mean totally off, and you wanted to push a system update, you have to turn on Wake on Magic Packet. So when the server sends that signal out on the network, your computer wakes up by itself and turns all the way on. That's how hackers can get inside of your computer. They can turn your computer on. They turn on Wake on Magic Packet while you're asleep in the middle of the night. Your computer's operating and they'll turn it off. You'll never be the wiser. Okay? So you want to make sure that that is turned off if you don't need it. In here, you can update the driver again for your NIC card, driver details, events if it's not operating right. It tells you the memory range that is put in memory when the driver loads it or when it's in use. And here's your power management. Allow the computer to turn off this device to save power or whatever you want to do, or only allow a Mac packet to wake this computer. So you have to check these in order if you want Wake on LAN to be used. All right. So what we're going to do at this point, I'm going to play a video, a very good video. I like this channel. She's called the East Charmer. East Charmer. She takes you to work with her in California. She's been around for a couple of years. And she walks you through all the network stuff that she does about setting up networks and such. So let's go ahead and take a listen to what she has to say. This video is about 10 minutes, so it'll take us to our next break. All right, here we go.
Hello everyone, welcome back to the channel. And this video is episode 3 of our Switch Upgrade Project series. And for this video, I'm going to show you how to set up and configure a Cisco switch, or particularly a Cisco 9300 switch from scratch. So if you're interested in today's video, please keep on watching. And without further ado, let's get started.
Can y'all hear that?
Also, before we get started, I just want to say, before you come to me in the comment section saying that I'm not entering all the commands one by one on the switch, I just want to show you how we do it realistically in production, and at work, we don't enter all the configuration and commands one by one, especially if we are deploying hundreds of switches, because that's inefficient and that is more prone to errors. Also, I made a video showing all of the switch commands that we're going to use. That is in the preparation phase of a switch upgrade project. So if you're interested to see all of the commands that we use for our template, you can check out that video. So let's get started. The reality is I'm using multiple AI tools. So when it comes to writing, I trust. Okay, so first thing is getting a new switch from our pile of switches. The first switch that I need to replace has 4 stacks with 2 48 ports and 2 24 ports, so I need to get the same type of switch. And you can actually look for the product number in the package to know which ones are 48 ports or 24 ports. So this one says C9300 24UB, which means it's a 24 port switch. Okay, so now that I've unboxed the switch, the first thing we're going to do is to power it on, of course. And when you unbox the switch, the power supplies are separate, so you have to put it in first. So the power cable that this switch uses is not like the regular ones. This has like a little notch in the middle which fits the AC power cord connector for this particular power supply. Now that the switch is powered on, you can see all the lights lighting up. Next thing we're gonna do is to access the switch so we can configure it with the commands and the OS and everything. So to get into the switch, physically access the switch, we need a console cable. So it's the blue cable that we can connect the network device into our laptops or computers. And the console cable now has different ends. Sometimes it has a serial end and you need an adapter like this. And sometimes, but there's new console cables now that is USB, so you won't need an adapter. So the USB end will connect to your laptop, and the RJ45 end should plug into the console port, which usually has the terminal icon here. So let's now go back to our laptop to see what port it's using in the device manager. So under ports, you should see like a USB to serial COM port, and just remember what port number it is. In my case, it's COM3. Now we will be able to console into our switch, and I'm going to use PuTTY for this. So on PuTTY, make sure that it's on session, and then we can select the serial in here, and just type in the port number, which in my case is COM3. And then click on open, and then it's going to show a screen now for the console, and make sure to press enter. And we now have access to the switch, and it's going to ask you if you like to enter the initial configuration dialog, and I just type in no for this. Also, I forgot to mention that in this video, I'm going to import the configuration files through the TFTP server. So I'm going to need to set up a management IP address first so we can reach the TFTP server. And we also need to connect the switch to the network, but unfortunately, I unboxed a blank switch, so we would need a network module for this. Luckily, we have ordered extras. We're going to use this NM2Y module, and this module has two 25 gig SFP28 module slots. Okay, let's go back to the switch, and after initialization, it's going to ask you for more options in here. I'm just going to select the return back to the setup without saving this config because we have nothing to save yet. So the next thing I'm going to do is to set a management IP address. I've also plugged in the switch to the same VLAN that I'm going to configure my management IP to. Okay, of course we're going to type in configure terminal first, and then we're going to type in the VLAN that we're going to use for management IP. And then we're going to type in the interface VLAN 100 command so we can put the IP address on the interface. And the command to set up the IP address and your IP address and the subnet mask.
I stopped that on Mike. Did you see it? Now that's why it's important to know your IP address ranges. All right, or what you want to put on that port interface in creating a LAN. Now, the reason why I stopped this is because do you really think they made a VLAN 100? It's usually VLAN 10. They put the 0 on it just to make it a 3-digit. All right. Or it's VLAN 1. They just call it 100. So you'll see the different type of flavor there. All right. VLAN 1 could be 100. VLAN 2 could be 200. VLAN 3 could be 300. Okay. Then you have, this is what you need to do on a PBQ because somebody didn't hit config T to start this, so it didn't take all of these settings. Once you hit that, you have to put in these settings at each line. And then you put in the IP address right here. All right, just putting it in right now. This is the IP address that I wanted to have, 161.255.255.255.0, and now watch this.
And now that we have an IP address, we can now reach our TFTP server so we can import our iOS and configuration files. So the next step would be to copy down our iOS version from the TFTP server. We just got the latest iOS version from the Cisco website and put it in our TFTP server. So this is the command: copy space the name of your TFTP server and then slash the iOS file. And in our case, we're just using a symbolic link called the current version. That is a shortcut to whatever the latest iOS file we have on the TFTP server. And at the end of our command is where we want to copy our iOS file, and it's the flash memory. And let's just wait for it to finish importing the file. And when it's done, it's going to say it copied the file, and it's going to look like this. Then the next step is to install the OS using this command. And it will start installing and will take a few minutes to install, and you'll get this message when it's done.
Now she's taking a switch straight out of the box. She's making sure that the updated iOS that the company is using is installed. She's basically imaging the router. The switch. Okay. Trivial TFTP server means trivial files. Yes, she is redacting data. She has to hide it. Yep. So this is nothing different than what you're doing for a computer that comes in from asset management. You get the computer, you connect through Pixie Boot, get the new image loaded on the computer. The back end is get a new switch, unbox the switch, connect it with an IP address, hook up to the TFTP server, trivial files, port 69, get the files and the configuration files for the switch. She's doing the same thing. Then she's going to go back and configure using a configuration file and load all the VLANs. Here we go.
And we can check if it's successfully installed by using the command show version. And the next step will be to clean off old files just to make sure that we are starting with a clean switch. And we can use this command. And I just said yes to delete all of these old files.
Awesome.
And our next step is to copy all of our configuration file templates to the running config. Once again, we already prepared a configuration file template, so we don't have to copy all of our commands one by one because that is very inefficient. So if you're interested to see what the template looks like, I also made a video about it. So the first template that I'm going to copy is the one with the basic switch settings like the host name and SSH settings. And same as the config earlier, we are going to copy the config files from the TFTP server. So we're going to do the command copy space TFTP and the name of your TFTP server / the name of the configuration file and space running config because we want to copy it to the running config. So the next template is for our global config template, and it's the same command, and we are just going to change the file name for this and save it on the running config. And we are going to do the same for the other templates that we have. We are just going to change the file name, but we are going to copy it from our TFTP server and save it on the running config. And after we copied all of our templates, we can also check if all the configuration applied by doing the show run command. And of course, don't forget to save your configuration. You can do a copy, run, start, or write memory command. Okay, so the last thing to do is to test if you can access the switch through SSH by using the appropriate IP address that you set the switch to. And once that's all working, your switch should be all set and ready to rack. So this will be the end of today's video, and if you're interested in how we rack this...
What you got, Michael?
Did you read the other information because of what she's showing us? That it could be easily hacked if we had all the information that she was actually presenting?
Yep.
Okay.
That's why she didn't finish the personal IP address for the host name.
Okay.
She left it at 192.168.
Okay.
You know why? Because we all use 192.168. So, but you don't know who she works for, and you don't know what the last ones are.
Okay, I was just wondering. I
That's-
was like,
Yeah. So from this aspect, this is where y'all are coming in as far as IT, working for a company. They want you to connect to a server, download the files, and configure the switch, meaning the network side configure the switches for you. They don't want you doing anything. They don't want you messing up nothing. All they want you to do is copy it, image the switch, put the configuration files on there. It automatically starts working. So big IT in your company is making sure it's error correction. There's making sure nobody is off doing their own thing in the company. So all of it's going to be the same. This is like what you're going to see on the exam with the commands that she was showing. You're going to have to use show run command, show interface, show route, and we'll get into all that yet tomorrow. But those are the different things that you'll start seeing, setting up switches. Woo! Brain hurting today, ain't it? Day 3. Yeah, I like it. Told you you're gonna learn a new language, didn't I? Didn't I tell you that, Jesus? Yep. Anita, now, yeah, it's a lot. I told you this one is a lot. It's fun, but it's a lot to learn. A lot to learn. Now, I know you may not have questions right now. We have to wait for the questions to formulate. But if you do have one, hit me up. Ask me. Or ask.
Yeah.
But are there any questions right now that's on the you need me to answer?
no, but the whole bad rap. I remember speaking about that for just a second. The reason why I said it is because when I used to work the Phoenix, it's only because we could only bring in like so-called an 8 meg pipe of data, how much we could bring in, but we also found out that we can bring in much more, and the data that we did need, we just like dump. We have a dump port. So we'll bring in the data, and then stuff we don't need to overflow, we just go to a dump. So that 8 meg would just keep on flowing in instead of getting congested.
We have the same thing in IT. It's called a black hole or a sinkhole. So we have the same thing in IT. Yep. You have to configure a port. If traffic comes into the network from an unrecognized address, it'll dump it. It'll go in wherever hole and never come back. So that computer would never get a response.
So you can't retrieve that data if need be?
Nope. We just get rid of it. Well, I take that back. Yes, you can. If you configure that, if you put Wireshark on that port, where it's always capturing packet data, yes, you can tap the port. And that's how you're figuring out telemetry from like hackers. How are they trying to get in? You can just record the conversation and go back and analyze it. But on a small scale, if you don't care, you just dump it in the void of foreverness. You don't want it, Jesus says, me get confused. Language too hard. Army brain hurt. Elaine, you're in here too. You know how to do, you've been working with Apaches and stuff, so you're in this vein too. So,
yeah.
It's good stuff. Don't worry, we're not even through week 1 yet. We got 2 weeks to get this right. So don't even worry about it. But go ahead and turn to, give your brain a rest and work on some work if you want. And we'll wrap it up for the end of a Friday here soon. Good stuff.
As financial information or other personally identifiable information for the purposes of identity theft. Other motives might include disrupting operations, also known as denial of service attacks. Now, in these cases, the objective might not be the personal gain of the attacker, rather the damage that might be inflicted against the target. For instance, a disgruntled employee or a dissatisfied customer might simply want to take down the operations of the target to cause them harm, rather than to gain anything personally, other than perhaps the satisfaction of having caused those issues for the target. Although an unscrupulous competitor might take down their primary competition for their own gain. And extorting payment or other type of gain, which is the common motivation behind ransomware, whereby important files of the target are encrypted or stolen and can only be decrypted or returned by paying the ransom. The attack vectors refer to the means of delivery for malware. Common examples include the Trojan horse, which presents itself as a useful or a necessary application, but actually does nothing more than to deploy the malware contained within it. Viruses, which again refers to a broad scope of malware, but the key characteristic of any type of virus is the fact that it is self-replicating, just like a biological virus. But it should be noted that in order to do so, the virus needs to hijack some kind of executable code, such as a script, to be able to replicate, which is why file types such as executables, batches, or scripts of any kind are most closely monitored by antivirus scans. Worms are commonly spread by email or compromised websites, but they differ from viruses in that they're able to self-execute and or self-propagate, so they don't need to hijack any other type of file. As their name suggests, worms are designed to crawl through as many systems as possible and spread as widely as possible and as quickly as possible so they can inflict more damage in less time. So how do we as everyday users protect ourselves? Well, first and foremost, by having some kind of anti-malware application installed that itself is kept as current as possible. In large organizations, this is usually deployed and maintained by your IT department, but for smaller organizations or even home users, it is, of course, up to you. But many devices and operating systems come with some kind of anti-malware application installed by default. For example, Windows systems now come with Windows Security, formerly known as Windows Defender, and it's pre-installed. And Mac comes with X-Protect, but there are also many dedicated third-party apps that you can also use. In many cases, something that can also be very effective is simply ongoing user education and training. If users in an internal organization are informed that a legitimate application will never be sent out by email, then they'll be able to more easily recognize worms and just delete the email straight away, or at least report it. And on the administrative side, simply making sure that all network security best practices are observed will most certainly help to protect your organization overall. For example, ensuring that you have implemented security devices and protocols around your perimeter, using proxy servers to filter web-based traffic, and of course deploying an enterprise-level security suite, and keeping all of your systems as up-to-date as possible will go a long way toward lessening the chances of becoming a malware victim. As will performing regular security audits, which can help to reveal previously unknown vulnerabilities or potential exploits so they can be addressed and corrected, and of course, simply protecting your data with regular backups with multiple copies stored in separate locations. For instance, if malware has infected your current data, as long as you have backups of that data, then you can simply delete the corrupted data and restore the backups. Similarly, even if ransomware locks you out of all of the data in your environment, if you have backups in a separate location, then you can still just restore that data and you're back in business. So, when it comes to malware, certainly be sure to implement the appropriate technical defenses, but due diligence and vigilance will also go a very long way toward keeping you safe. So in this course, we've examined various types of attacks and their impact on a networked environment. We did this by exploring DOS and VLAN attacks, MAC flooding, ARP poisoning and spoofing attacks, DNS poisoning and spoofing attacks, and rogue devices and services, evil twin, on-path, social engineering, and common malware attacks. In our next course, we'll move on to explore network troubleshooting methodologies and approaches.
are released, they will also increment those Wi-Fi numbers. So in the future, we should see Wi-Fi 8, Wi-Fi 9, and so on. There are a number of technologies used by 802.11 wireless networking, and the first is the frequencies that are in use. 802.11 commonly uses 2.4 gigahertz, 5 gigahertz, and 6 gigahertz frequency ranges. Sometimes there's a combination of those. You may have an access point that supports both 2.4 and 5 gigahertz, and some access points may support all of those frequencies at the same time. Instead of having to memorize individual frequency numbers, the IEEE has created groupings of these frequencies known as channels. These channels help us easily understand what frequencies we may be using. For example, on this access point, we're using both the 2.4 gigahertz range and the 5 gigahertz range. The 2.4 gigahertz range is using channel 6, which is centered on 2.437 gigahertz, and the 5 gigahertz band is using channel 44, which is centered on 5.220 gigahertz. You can see that referring to this as channel 6 is much faster and more efficient than saying that this particular access point is centered on 2.437 gigahertz. The amount of frequency that we use is referred to as the wireless bandwidth. And when I say that channel 6 is centered on 2.437 gigahertz, there's actually more frequencies that we're using for that single channel. Different frequency bands have different sizes of bandwidths that can be used, but it's very common to see 20 megahertz, 40 megahertz, 80 megahertz, and 160 megahertz bandwidths. Here's a diagram that shows the 2.4 gigahertz range, the 5 gigahertz range, and the 6 gigahertz range that's used by 802.11 wireless networks. We'll start with the 2.4 gigahertz spectrum. You can see there are 3 non-overlapping channels in that particular range, and it's using the 20 megahertz bandwidth to describe those 3 channels. Next is the 5 gigahertz spectrum, and you can see there are many more frequencies available in the 5 gigahertz range. You'll also notice that we might use different bandwidths depending on the access point that we're using. So we might use anywhere from 20 megahertz to 160 megahertz, and you can see the ranges that are available for those particular frequencies. And in the 6 gigahertz range, we have even more frequencies available, giving us options to be able to transmit and use these wireless networks without conflicting with other wireless networks that might be nearby. As you can tell, there are many frequencies available to choose from for your wireless networks, but not every frequency is going to be the best one to use. There may be differences in the environment where you happen to be, where one frequency might work better than the other, or there may be other access points that are already using certain frequencies.
He gambled and he lost. Co-pilot, now act as a judge and critique my closing argument.
I caution against using emotionally charged language without concrete evidence.
Good point. Let's run it again. Be ruthless this time.
Dial back the repetition.
We put it through the worst. So you get its best. Nissan, #1 in new vehicle quality.
You might also be using older devices that aren't able to communicate on the 5 or 6 gigahertz ranges and may only be able to communicate on 2.4 gigahertz frequencies. But if you have a modern wireless device, you might have options. Your phone, for example, may be able to support 2 or more different types of frequencies. It just needs to be able to choose the optimal frequency for where you happen to be. Your access points can be set up with a feature known as band steering. This allows you to specify how the users might be able to use the frequencies in the best possible way. For example, you might have a user that has a mobile phone, and that phone can support either a 2.4 gigahertz connection or a 5 gigahertz connection. And you might have access points that also support both of those frequencies. So which frequency does your phone choose when it's connecting to that access point? If band steering is not configured in the access point, the device will simply use the one that has the best possible signal. Sometimes that best signal will provide you with the best throughput, but that's not always the case. And you may find that you get better throughput using a different frequency, even though that frequency may not be the one that has the strongest signal. If band steering is turned on, the administrator of the access point can determine what frequency a user will choose if they have a choice. For example, if a user is connecting to an access point with band steering enabled, and that device can support either 2.4 gigahertz or 5 gigahertz, You can force it or steer it into using the 5 gigahertz frequencies by default. One of the challenges with these wireless networks is that each country makes its own decisions about how this wireless bandwidth is to be used. For example, in the United States, we have the Federal Communications Commission, and they are responsible for managing all of the frequency allocations in the US. Of course, the FCC can't control how other countries manage their frequencies, but they do work very closely with other countries around the world to make sure that everyone is properly managing these very important frequencies. Another challenge with this is that we are coming up with new technologies and new ways to use these frequencies all the time, and we sometimes have to make sure that different services can use similar frequencies without any type of conflict. The popularity of these wireless networks has almost required that all of these countries work together to come up with standards that everyone can agree on. A good example of these organizations working together can be found in the 802.11h standard. This adds a number of interoperability features to 802.11 wireless networks so that you can have many different wireless networks in one area, but still allow all of those networks to work together. There are a series of guidelines for wireless communications that are published by the International Telecommunications Union. The ITU provides a worldwide approach to managing these many different wireless technologies. One of the things that is included in these standards is called DFS. This is Dynamic Frequency Selection. This allows our wireless access points to use frequencies that are not going to conflict with other access points that may already be operated. This is one of the reasons that when you turn on your wireless access point today, that you don't have to manually configure any of the wireless settings inside of that device. It automatically looks at the frequencies that are in use and chooses a series of frequencies for you that are not going to conflict with anything that may already be operating. And if something does change with the wireless environment and your access point needs to change its channel, it will tell all of the devices on that network to also move along with the access point. Another interoperability feature is TPC, or the Transmit Power Control. Traditionally, we've set the power that we would use for these wireless networks on our clients, but TPC puts the transmit power control in the hands of the access point. This means that the access point can tell a client to use less power to be able to communicate over this wireless network. This means that we can have many devices communicating at their optimal power level without having any type of conflict with other third-party services.
People can go crazy trying to stop a cyber attack. Acronis take the headache out of IT security.
People who pick post-university for an MS in Business Intelligence and Analytics expect classes on their schedule, on their budget, taught by real-world professionals who know what it takes to move ahead in their field. Are you a post person?
When we think about wireless networking, we often think about connecting to an access point. But of course, you can communicate directly to another device without an access point. We refer to this as Independent Basic Service Set, or IBSS. You might also see this referred to as an...
You said Alexa? No, no, that's classes from a particular individual based on the certifications that I'm doing. So that is what's playing, if that's what you're referring to.
ad hoc connection. This allows us to configure one device as an ad hoc connection, configure the other device as an ad hoc connection, and simply connect those two devices to each other over those wireless frequencies. You might have used this functionality when you've configured an Internet of Things device, such as a door lock or lights in your home. This is a way to connect to a device over an ad hoc connection, provide that device with information about your existing wireless network, and then have that device connect directly to the access point. And in most environments, we have an access point that many different devices are connecting to be able to network everyone together. Behind the scenes, we're using different parameters to configure this device. Two of those parameters are the SSID and the BSSID. SSID stands for the Service Set Identifier, and it's the name.
What AI assistants are you talking about? Oh, are you talking about the HAS feature that is on the videos? Is that what you're talking about? Or I'm not sure what you're referring to when you say AI assistant. Because on some videos you have you have the ask button, so you can ask, and the AI will do a summarization of the video for you, or at least the title, but mainly the video and what it is based on. Yeah, so new features that are coming out now. It's a lot of IT and AI help. So you don't necessarily have to go based on the summarization. You can watch the videos. You can go from the title or from the description, but that's just another way that you have AI being incorporated into just about everything now that we're doing. So if that's what you're referring to, yep, then that's just another implementation that YouTube is not implementing. So it summarizes the video or what the video is about, or maybe just a description pertaining to the title.
Name of the wireless network that we're connecting to. So you might have an access point with an SSID of SGC1. And when you bring up the list of all of the available access points in your area, you will see that SSID name appear in your list of available networks. Of course, this same SSID
From the Well, my current topic for this particular live is based on cybersecurity, IT. So the doing the certifications, actually going through the courses, and eventually acquiring the certifications. So that's what this particular video is based on. So you from time to time you'll hear classes going on that are particularly referring to subjects pertaining to IT. So later on, after this video, then I'll have another video pertaining to what the subscribers wanted to talk about. So if you go to my community section, you'll see just a little bit more detailed of what videos I'll be doing geared towards what you guys want to talk about. So I'll have that live differently. Explain what cybersecurity is. So cybersecurity is based on providing the security based on the virtual internet that that we all use each day. So it's basically putting up a wall or firewall against attackers or people that want to hack into your stuff. What is my suggestion for cybersecurity? In terms of what? Because that is wide. Are you asking that pertaining to getting a certification, or what what software to use on your computer, or I'm not sure what you're pertaining to, because cybersecurity covers a vast amount of area. Are you asking for something that you can use on your computer? Like for the everyday just the common computer user, or are you trying to get a job or a certification? I'm not sure what you're referring to exactly. Or what details you are asking about. The cybersecurity is just it covers so much.
Might be configured on multiple access points, especially if you have a very large home or you're in an environment where there are multiple.
Okay, fraud and scam. So cybersecurity does cover that and a lot more, but particularly fraud and scams. So if I was to give you like precautions, is you want to be careful about clicking on links within your email, or if the email looks like it's something that you're not supposed to be clicking on. So emails in particular, we all have email account. If you get an unfamiliar email, you can just go ahead and delete it, or don't click on it. Or even if you made the mistake of clicking on it, don't click on another link that's within that email if it looks like it's nefarious or it's mostly unusual. Just go ahead and delete it. The same for text messages. When it comes to scams and hacking, when you're browsing the internet, then you're gonna want to have like at least an antivirus software running on your computer, or use website that you know that is trustworthy, that you can go on that website without having to worry about someone trying to hack into your computer. When it comes to hacking, the most you can do is to use the passwords, complicated passwords whenever it comes to having a password on any of your accounts. Also, two-factor authentication, which means you have a password, a PIN, also possibly a passcode, or you want to use one of the passcode application, which is an authenticator app. So a lot of your accounts a lot of the accounts that you use, even logging into any of your apps or your bank account,
This is a /23.
just get two-factor authentication on that. So it also goes back to your cellular phone or to your email, which notifies you just to verify that it is you that's using the account. And when it comes to website, you just want to stay away from most websites that it's may seem nefarious, or you have just randomly windows opening up just for no reason at all. So websites like that, they do a lot of stuff like phishing. It's different terms that they use in cybersecurity and IT, but if you've been using the internet for a period of time, you'll notice that when you click on a certain website, you'll have different kind of windows just popping up out of nowhere. Yep, that's another way as well. That's they have different terms for stuff like that. They can do it through different apps, messages, or even through your email. So if you don't recognize it, I wouldn't recommend clicking on it or even trying to respond to it.
It's okay. It's all right. Give your mind a break. It'll come to you.
So even though the IT world is mainly pertaining to getting a job or a career in it, it's it's very useful in your everyday life because we all use the
So for
computer, we
this
all
one,
use
this
the
is a
internet,
class
so you
B
can use it for
address.
there as
The
well.
most important thing you're looking at is the bit position to what
And
octet
that is
it's
really
in.
crazy for
That's the
you
most
know,
important. Yeah.
clicking on a
That's the most
message or
important
something
thing you
in
want to
an
look
app,
at
and then
because the octet position
your account is
with the bit
compromised.
number, the /23, tells you what the subnet is going to start to be.
So a good step would be just to self-educate, or you can go just about anywhere on the internet right now, even on YouTube, and get tutorials and tips on how to take the precautions.
Make sure y'all fit in a break. This is our last break of the day, so make sure you get your 10 minutes in.
Areas of the building, and you want to have wireless connectivity wherever you might be in that building. To be able to differentiate between one access point and the other, we need some type of hardware address on that access point, and that hardware address is known as the BSS-ID. This is the basic service set identifier. So although there is a wireless network name that we see, such as SGC1, there is also a hardware address that we normally do not see behind the scenes. In this case, this wireless access point has a BSS ID of 603 Delta 26112233. As we've already mentioned, in your home or a very large business, you may have tens, hundreds, or even thousands of access points to manage. All of these access points need to be able to work together so that as you are passing from one building to another or from one area of the building to the other, you're able to seamlessly move from one wireless access point to the other. This is often done by using the same SSID or wireless network name on each of the wireless access points. We refer to this shared network name that's used across access points as an ESSID. The E stands for the Extended Service Set Identifier. With the ESSID configured across all of these different access points, you can start on one end of the building, walk to the other end of the building, and you will be moving automatically and seamlessly from one access point to the other. Here's a configuration that uses ESSID to provide that seamless roaming from one access point to the other. In the middle at the top, we have a network switch. This switch has an Ethernet connection to an access point on the left and an access point on the right. And you can see that the BSS-ID, or the Basic Service Set Identifier, which is the hardware address of the access point, is different on this access point than it is for the other. Although these are obviously two different pieces of hardware, they are sharing the same SSID. You can see it's configured as SGC1 on this access point. It is also configured as SGC1 on the other access point. As we move outside the range of one access point and move into the range of another access point, that access point will automatically pick up that we are nearby and seamlessly connect this device to that same SSID without any notification on your mobile device. This means you can continue to surf the internet, transfer files, and use the network normally, even if you happen to be moving at the same time.
This is the newly redesigned Dell AI PC with Intel inside. It's not just an AI computer, it's a computer built for AI. So you can do the stuff that slows you down way, way faster. Like that. And that. And yeah, that too. It's a U multiplier. So you can get more done quicker, which means you get to be done sooner.
Wow, every time. Yeah. When you first connect to a wireless access point, you may be prompted with a screen that gives you information about the network or requires you to authenticate to gain access to that network. We refer to this screen that appears and the prompt with the authentication credentials as a captive portal screen. For this captive portal to work, there is a centralized access table that identifies individuals that are already authenticated to the wireless network. And if it notices there's a new device that has not previously authenticated, it will present this captive portal screen to the end user. On the Captain Portal screen, there may be a series of terms that have to be agreed to, or it may prompt for a username, a password, or some other type of authentication factor. If those credentials are entered properly, then that information is added to the access table and you gain access to that wireless network for a predefined amount of time. For example, your captive portal may be good for 24 hours, and at the end of that 24-hour period, you have to re-authenticate to gain another 24 hours of access. There are many different ways to configure security on a wireless network, and if you look at the configuration of your access point, you may find that there are a number of different options that you could choose from. For example, on this access point, the security level is currently defined as WPA2 Personal. This access point can also disable security. It can configure a security mode on this access point known as OWE, which stands for Opportunistic Wireless Encryption, which effectively allows someone to connect to the wireless network, but prevents them from communicating directly to any other wireless device. This access point also supports WEP, different flavors of WPA, WPA2, and WPA3. An open system, of course, means there is no security, there's no authentication process, and anyone on this wireless network can communicate to anyone else on this wireless network. This access point supports WPA, WPA2, and WPA3 using a personal type of security. Sometimes you'll see this referred to as PSK, which stands for Pre-Shared Key. This means to gain access to this wireless network, we need to provide someone with a pre-shared key that everyone will use. For example, you may be at a coffee shop and there may be a notice at the coffee shop that the pre-shared key that everyone can use to access the network is hot coffee. Of course, if you're in a business environment, having everyone share the same password for the wireless network is inherently insecure. So most enterprises will use a different type of wireless security known as Enterprise or 802.1x security. This allows the network administrator to require a username, password, or some other type of authentication to gain access to the wireless network. And most people will use their own personal credentials to be able to provide that access. This means you would use the same username and password you would normally use to log into other devices in that same enterprise network. This means if someone leaves the organization and their account is disabled, they no longer have access to that wireless network. If you look at the different antennas that are used on many of today's wireless networks, you may notice a number of different styles. The style of antenna that you see connected to this access point is an omnidirectional antenna. It's a very common antenna type to find on our consumer or home-based access points. An omnidirectional antenna will evenly distribute that wireless signal on all sides of the antenna. So you can put your access point in the middle of the room, and everyone in the room will have the same signal strength as everyone else. This means you can put your access point in a centralized area, and anyone who's nearby will be able to gain access to the wireless network. But this may not be the optimal antenna type to use. For example, your access point may be in the corner of an outside room, and you're effectively only seeing a portion of that signal while the rest of it on this omnidirectional antenna is sent to places where no one will ever connect. In that scenario, you might want to use a directional antenna where you can take that wireless signal and send it into a single direction. This allows you to focus the transmission and receiving of wireless signals to a device that may be in the corner of a room or may be connecting different buildings to each other. You'll often see these antennas measured as a total number of decibels. For example, a directional antenna may increase the performance of that signal by a certain decibels of gain. For example, you may see in the specifications of a directional antenna that it effectively increases the overall power by 3 dB. And for every 3 dB, we are effectively doubling the amount of power available. One type of directional antenna is a Yagi antenna. This is an example of a Yagi antenna. It is very directional and has a very high amount of gain. We also have other directional types such as a parabolic antenna where multiple signals can come in and bounce into a single feed horn in the front, so it's focusing all of those signals into a single point on the antenna. This is especially useful over longer distances where you need to collect that signal and focus it into a single spot.
Co-pilot, let's make a meal plan for my 9-year-old. No peanuts, green things, or hummus.
Sure, here's a plan to keep lunchtime stress-free.
Thanks, Mom.
I'm being told this is Lebo Evo from Liberty Mutual, who helps save you hundreds by customizing your car insurance.
And his partner Doug is the gentleman under the security guard.
Only pay for what you need.
Liberty, 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 liberty.
Most of the access points that we use at home are autonomous access points. This means that the access point doesn't require any type of additional hardware or software to be able to operate. It's effectively a standalone device that doesn't rely on anything else to be able to maintain that wireless connectivity. But in an enterprise, you may not be using autonomous access points. Instead, you may be using lightweight access points. This separates the wireless functionality into the hardware that you would mount into the ceiling, and the configurations and intelligence of that device are often maintained on the switch the access point is connected to. This not only allows us to have less expensive access points that we can deploy, it also gives us functionality for being able to manage those devices. One standard for managing wireless access point is known as CAPWAP. This is control and provisioning of wireless access points, and it allows you as the network administrator to manage and configure all of these wireless access points from one central management station. We refer to this central station as a wireless LAN controller, and allows us to connect and view the entire wireless infrastructure from one single screen. We often refer to this as a single pane of glass. From this single management station, we can deploy new access points. We can monitor the performance of our existing access point infrastructure. We can make changes to the configuration of our wireless network and deploy those changes to some or all of our access points. And this might also create reports showing us how much of the wireless network is being used and by whom. This wireless LAN controller is often paired with the wireless access points themselves, so you're often getting the access points and the wireless management station all from the same manufacturer. There are a number of different ways to connect and configure wireless networks, and in this video we'll look at some of these different wireless network types. One popular wireless network type, especially in home-based environments, is a wireless mesh. This is where you would have multiple access points that can all communicate to each other within a relatively close area. And then you would have other devices that are located on the outside of those access points that are able to communicate to that single access point and ultimately to the rest of the network. This meshing of access points in the middle is something that you would configure on the access point, and if you were to add additional access points onto this network, they would also be included in that same mesh of access points. Of course, this doesn't have to be access points. There are some devices that can mesh amongst each other in an ad hoc form. This allows for different options for sending data over these networks because all of these devices are now communicating to each other. And if one device leaves the network, it can automatically identify that that device is no longer there and self-heal itself to maintain connectivity to everyone who's left on the wireless network. If you only have two devices, you might want to connect them together without an access point. We refer to this type of connectivity as an ad hoc connection. This is where you would use the 802.11 wireless functionality of your device, but you would not be directly connecting to an access point. This uses the 802.11 wireless network functionality of this device, but instead of connecting to an access point, you simply connect to the other wireless device. You might also see this referred to as an independent basic service set, or an IBSS. This might be something that is a very long-term connection. If all you have are two devices, you can simply connect those two together and they will communicate as long as that connection is available. But you might be using this on more of a temporary basis. This might be used in conjunction with an Internet of Things, or IoT device, where you would initially connect to the IoT device over an ad hoc connection. This may allow you to transfer configuration details, such as the name of your larger wireless network and any security configurations that have to be included to connect to that wireless network. At that point, the ad hoc connection is then disabled, and the Internet of Things device can connect to the larger access point network using those configuration parameters. Some wireless access points allow you to connect two devices directly to each other over a point-to-point mode. The point-to-point mode is commonly used to connect larger distances to each other. For example, one building connecting to another building. I've run this exact configuration between two homes, so you could have an access point in one house connected to a switch and all of the internal devices of that network connected to the same switch, and then you would have the same configuration in another home and have all of those networks now connected to each other over that point-to-point mode. Not all access points support this point-to-point mode, so you want to be sure that the software of the access point supports point-to-point, and you'll want to be sure that the hardware on this device is also able to transmit over that extended distance. You may, for example, require additional types of antennas to be able to bridge that gap between the access points. There might also be a requirement to change the power output between these two devices and to make sure you're using frequencies that are able to communicate over that longer distance. And perhaps the most common way to connect to a wireless network is in something called infrastructure mode. This is where you would have a centralized access point, and this is probably the type of wireless networking that you're using at home and in your office. All of the wireless devices in your home or office connect to that central access point, and you're able to communicate out to the wired network or between other wireless devices over that same access point. Some wireless access points give you the option to allow devices to communicate with each other over that wireless network, or to isolate each of these wireless devices to only be able to communicate directly to the access point and any networks beyond that access point. You'll want to check your access point to see how it's configured for these devices and make sure the proper security is configured on that device.
You're going to find out that it's on LAN 1, and I did this on purpose. When you're looking at this IP address, we already established that this is a Class B.
Tackling your security concerns starts with a prompt.
Class B address.
With Sola AI, you get answers to the security questions you really care about instantly. Get started with Sola, the AI you need to get security done.
Dear friends, let's put good times in gear.
You get it.
Toyota Tracks.
Right now, get 2.99%
So this is typically what you'll
financing
find.
for up to 48 months on Tacoma. Toyota, let's go places.
Net ID 172.
The wireless networks we use both at home and in our businesses are sending
LAN
private,
1, that's the very
confidential, and
beginning of
sensitive
IP
information
address.
all the
The
time.
last address
And
in
we're very
that
concerned
is
that someone might have
That
access
means
to that
everything
data,
on the
especially
510
on a
you
wireless
use, those are
medium
usable
that
address
effectively
ranges.
could be tapped into and listened to by any device that happens to be nearby. One
Now,
way that we
typically,
provide
what you'll
security
find
on this
is-
wireless network is to limit what you
Give me 1 second. Can y'all see my screen or no? All right, here we go. I picked this address for a reason because you would have defaulted to do this anyway. In class full addresses, class full, okay? No matter what, when you start using this, 255 and 255 are both the network. The last 2 digits will dictate the host location if you're using class full. Okay? Because all those bits are turned on, it dictates the network. Same thing, it'll follow the same convention. It means the last 2 will tell you where the host is on the home page.
Yeah.
Okay, let me look at this again. How about that? Cool?
Oh, yeah,
All right.
good.
No?
Yeah, it's good.
Is it good now?
Yeah, it's good.
Okay, thank you. So generally, when you look at in a class full addressing for class B, network, host. Network, host. network, host, right? But the thing about this in classless, when I put a slash on something, doesn't matter. Doesn't matter at all. Because the main thing I'm concerned about is the block size that I could use to create networks on that slash. You understand where I'm coming from? So in classless addressing, when I'm making up addresses, this is nothing to me. I can use any address I want in classless. My main concern is that slash and where and how many devices I'm putting on there. That's when I'm breaking the rules. So when I look at my chart, this is all I'm concerned about. How many devices can I put on that network?
Users are able
And the
to
subnet
access
mask.
the network. We would commonly do this.
That's why I can start with
sometime
any IP address that I want, all right? If somebody walks up to you like I just did and says, hey, Leah, can you figure out what's going on? And Mr. T, can you figure out what's going on with 172.116.25.400? It's having a problem. It can't connect. /23. I've already given it to you. It's already on the network. You just got to figure out what's wrong with it. You understand what I'm saying? Now, it's different if I walked up to you and said, hey, I need y'all to set up a network, and here's your starting address. Right? Now, that's totally different. Now you're right, Leah. Now you have to figure out where, okay, he gave me this address to start at, meaning now I got to figure out where does it fit in. And I need to ask him or her, him or her, how many devices do you want on there? I might say, I just need 4. Then you just need a /30, man. Like, we're going through all this. The way you said it was like, I needed 1,000 addresses. You get what I'm saying? And now you could work with that address from a /30 and just go and give me everything I need. That's it. So these little nuances, I'm glad we're talking through, because there's always something new that comes up about it, and it will help you on the exam to be like, oh yeah, we talked about that. Or I slightly remember that. I don't think we can use that. Like, all right. Now here's another thing that makes a big difference. If I'm using the class full chart, this comes into play. I have to pay attention to the network and the host ID. If I needed you to put in an address, this is what I would do if I'm using class full. I'd be like, hey y'all, I need this. That 25.400? Yeah. When I say I need information like that for a class full, your response is going to be, James, man, that's easy. The first 2 octets are the network. The last 2 octets for a class B, because it's 00, that's the host ID. That means it's LAN number 2, device number 400. Automatically, because that's the automatic IP address that it's gonna get. 100/23. You'd be like, dang, now it's with the information you just gave me. Now I gotta go find what LAN it's on, and blah 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 blah. It's like reverse engineering, basically. Hopefully that made a little bit more sense. A little bit more seasoning on there. Yeah. But good. You got it in the end.
authentication method, such as a username, a password, or some type of multi-factor authentication. And of course, we want to be sure that everything sent over this wireless network is protected, so we need to add confidentiality in the form of encryption. And to be sure that we've received the correct information over this wireless network, we include a message integrity check so that we can verify the information that we've received is exactly the information that was originally sent. One of the first encryption types on wireless networks is a method known as Wired Equivalent Privacy, or WEP. Unfortunately, WEP was discovered to have some significant cryptographic vulnerabilities, so we needed to very quickly replace WEP with something that was much more secure, and that replacement was known as WPA, or Wi-Fi Protected Access. WPA was implemented as a temporary stopgap between the insecure WEP and a more secure version of WPA. This first iteration of WPA was designed to work on exactly the same hardware as that older style WEP that we were replacing, but we knew that we would need enhanced security that we would not currently have available in this initial WPA. This replacement WPA we named WPA2. This is Wi-Fi Protected Access version 2, and it's a version that's been around since 2004. You often see WPA2 referenced with a block cipher mode known as CCMP. If we were to spell this out, it would be counter mode with cipher block chaining message authentication code protocol, or counter/CBC-MAC. This effectively combined encryption and integrity in the same protocol. The encryption was available with AES, and the message integrity check was enabled using CBC-MAC. The update to WPA2 is WPA3. This is Wi-Fi Protected Access version 3, and it was introduced in 2018. This includes a different and more capable block cipher mode known as GCMP. This is Galois Counter Mode Protocol. This continues to use AES for data confidentiality, and we are using a message integrity check with the Galois Message Authentication Code, or GMAC. If you're planning to implement any type of security on your wireless network, you want to use the highest level of security available in your access points and on your client devices. And if you have the option, you should consider upgrading all of your devices to use the most capable security method available.
This is the new Dell AI PC, built for AI. It's like a trusted personal assistant. Learning your habits, keeping you on track. But it can't make your coffee yet.
Organic and dairy-free? Woo! Woo!
Here we go.
Third time today.
At Sprouts, our shelves are filled with new, exciting, and delicious discoveries. This is that Sprouts feeling.
A distribution
Adding RAM, make sure it's the same brand, and make sure it's dual-sided.
Usually involves punch-down blocks like the
SODIMM,
one we see here, could be
dual
patch
data
panels,
rate,
or any other method where we are terminating those cables.
45-degree angle that you put it in. Make sure the pins are the same as what you have in there. Recommended pin size for your laptop, because all the channels are something different.
That are coming in for your local area network and voice communication. And although the punch-down blocks and patch
We
panels
talked about
that we have
MTS.
overall are technically the distribution
Sometimes they
frame,
fool you with
we
the
often
packaging,
refer to
saying
the
it's more when it's
entire
actually
room
not. It's
as
actually
the
cut in half. When you look at it, it just says MTS next
For
to it.
example, the primary distribution frame is called the main distribution frame, or MTS.
And max out
We often
that
refer to the
channel
entire room
like
that's
that.
located as the
If you can
MTS.
put 32 gigabytes in
A
it,
single
gigabits, do
often
it.
the data center or central point of the
Yes,
network.
where
This is where
ESD
we might
something,
bring in wide area
or
network
demagnetize
connections,
yourself some kind of way if you don't have
along with all our
a strap.
internal local area connections as well. Since we have all
Usually you
these
can run your hand
connectivity
across some type of
in
metal
place, it is a
and
perfect
ground
testing
yourself
point,
before you touch it.
especially if you need to test both your internal local
Charles says he bought
networks
the little
and
kit.
your external
Smallest
wide
part
area
to kill
network
everything.
connections.
Yep.
And even if your
Unplug
network
it,
doesn't have
unplug
this
it,
large set of
unplug
punch-down
it.
blocks in the back, we sometimes even
When you
often
go to
refer
power it
the
off,
central data center room
hold it
as the MDF.
for at least 3 seconds after it goes off to discharge anything, and then
Contains a number
let
of
it go.
different racks with computer equipment and the networking components
That's about it.
as well. Here's another MDF. You can see a large number of punch-down blocks or patch panels that are on the single rack.
I have one. Do not touch the metal channels at the end with your fingertips. The oil from your fingers can fry that soda chip because it's like cooking oil because it's on your fingertips. Yeah.
Disaster recovery, on the other hand, refers to the process and procedures an organization has in place to recover and restore.
Using the GUI shutdown, bring everything to a halt. Let the system bring itself down all the way. That's usually the best way. Then unplug it.
In this course, I'll explore how to
You can wear regular rubber gloves. You can actually. That's better than nothing. Like you can get surgical gloves or them doctor gloves or rubber. Yes, that's better than nothing. Yep. It protects you from ESD. Yep, you're right. That's a good trick. Don't use the powder. Don't use gloves with a powder on them. Don't want to do that. When your computer comes up, pay attention when it goes through the RAM and boots up. Go to System Info and make sure it reflects the new RAM. So like before, if it was just 8 GB, bring up System Info, it should reflect the total number of what's new in there. Sometimes it doesn't. If it doesn't, it might not be seated all the way. You should hear a click when it goes in. It should go click, click when you put it in. You should hear an audible something.
For any unauthorized access issues. This information provides insight to the overall health of the network and trends for future network requirements.
Mr. Miller, you got a request from Mr. T.
Or SNMP is a set of commands and tools that can be used to gather information from network devices and control them remotely. Like every network protocol, SNMP has evolved over time. Currently, V2 and V3 are supported on most networking devices. V3 is desired as it includes encryption of the transmitted data and authentication on network devices. Some key features include traps and the management information base. Traps are alerts that can be triggered to notify administrators of specific network conditions. For example, an administrator can set a trap to send in a notification when the available network bandwidth drops below 10%. The management information base is a small database stored on the network device that can contain monitoring information, which can then be gathered by network monitoring software. Flow data is information on patterns of traffic in the network fabric. This information can reveal trends or bottlenecks over time and can reveal possible locations for upgrading the network infrastructure. Capturing actual data from the network gives the administrator the ability to examine all the information in the transmitted data, like addressing, protocol information, and other details. This can help troubleshoot problems in network transmission protocols and devices. It can also reveal possible threats to the network. Using flow data and captured data, the networking team can create network use baselines and use those to detect anomalies or changes in network use. This could indicate problems with the network fabric or threats against the network. This information could also provide proof of compliance with the organization's security policies or external regulations. Another source of network operational information are the logs stored on networking devices. Log aggregation tools have the ability to scan each of the networking devices and collect the logs and deliver them to a central location for analysis. These tools can scan logs looking for warnings or serious errors and display these in a summarized format, which can identify problems more easily. Syslog is the name of the software on a network device that generates messages that can be displayed locally or sent to a central server for collection and analysis. These syslog messages include codes that identify the purpose of the message, for everything from a configuration change to an interface going up and down. These codes are particularly useful when scanning the logs for specific types of activity. An API, or Application Programming Interface, provides a method for programmers to create third-party applications. These applications provide more functionality than the software from the device manufacturer and may offer further insights into the data collected. They can also help automate configuration of network devices. Port mirroring is a technique of choosing a port on a switch where a network traffic is currently flowing and copying that data to another port where a monitoring station is attached. This allows the software on the monitoring station to collect a complete stream of data for analysis. One of the first tasks in any network monitoring scenario is establishing baselines. This is a set of metrics about normal network activity. Metrics for daily or weekly use can be gathered or even for longer periods. These present a picture of the network under normal load and serve as a starting point for analysis. Once you have the baseline, you have something to compare new readings taken from the network. Now, one could continually monitor the network in this way, but automated software can watch network activity and then create alerts whenever a parameter chosen by the administrator is triggered. This is a much more efficient way of continually monitoring for anomalies in the network, and because it's instantaneous, it can help resolve issues before they interrupt network operations. So those are just a few points about monitoring the network. In today's interconnected and highly available network scenarios, it is vital to continually monitor the network for performance and potential problems. In this video, we'll introduce network monitoring solutions. Network monitoring applications can provide an accurate overview of network operations and can also provide detailed information on any configuration changes. Network performance and network traffic patterns can be closely monitored through a centralized interface providing real-time telemetry on network operations. This information provides an opportunity to network administration staff for proactive maintenance and control of the network fabric. Trends can help predict possible future performance issues and can kickstart the planning process for increasing network resilience. For example, say an examination of network traffic flow shows that there's an increasing amount of network traffic because of new interactions between specific departments in the organization. The network administrator can take this analysis to management, who can provide more information on the future collaboration needs between these two entities. The conversation may lead to a need to upgrade the link between these departments, and budgeting and planning can take place before the network link becomes saturated and performance suffers. One of the first actions in network monitoring is discovering what the network looks like. Network discovery is the process of cataloging every network device, every endpoint, and every connection in the network. This can be a daunting task in a large interconnected network. However, there are software tools that can significantly reduce the effort in network discovery. Manual inventory will still be an important part of network discovery, but the effort involved would be greatly reduced by automated discovery methods. Another important aspect of network discovery is the ability to identify devices that are not authorized. Ad hoc discovery is only run on an as-needed basis. An organization may go through a hardware refresh where new equipment was purchased to replace old equipment. The organization may also extend its network because of a recent expansion. Both of these scenarios may justify an ad hoc discovery cycle. Scheduled discovery runs continually and can be invaluable for tracking changes in network topology or network devices. Any type of change in a network needs to be closely monitored, as any unapproved change may interrupt network availability. Besides the devices in the network, the traffic in the network should also be tracked. Traffic analysis methods are used to monitor the data flowing through the network and is used to recognize usage patterns. This can identify underutilized or overutilized portions of the network. This analysis can help network administration identify the best use for equipment in the network. It may be the basis for justifying reconfiguring the network topology or the purchase of new equipment to maintain optimal performance. There are software applications specifically designed to monitor traffic flows and provide insight into latency and bandwidth usage. These same applications can also separate traffic based on the applications generating it to provide further insight into potential traffic issues. As an example, broadcast traffic in a network is especially troublesome in that a broadcast is received by all nodes in the local network segment. This traffic is usually intended for only a single node, but disturbs all nodes which have the processor at some level. Network monitoring can identify this type of traffic and the application generating it. Network administration staff can then discover solutions to reduce this type of traffic, increasing the overall performance of the network. Being proactive means dealing with potential issues before they occur. By monitoring traffic patterns over time, one can form a comparison to detect which types of traffic are on the rise and which areas of the network are being affected. After it has determined that the traffic is required and continued support is necessary, the IT staff can begin to plan solutions before the network forms any bottlenecks. Besides increasing bandwidth and speed capabilities of the network, traffic can be prioritized by application, giving mission-critical traffic priority over traffic from other applications. Besides the performance of the network, the availability of network services in the network should also be constantly monitored. Software applications are available that can be configured to monitor specific network services, and these can generate alerts when a service becomes unavailable. This allows the network administration personnel to react quickly and minimize downtime. These services could affect the entire network, like DNS resolution, or be application-specific, like SMB, which is a file-sharing protocol. Quick action is vital if operational functions are not to be interrupted. Networking devices use configuration files that determine how data is to be routed and filtered throughout the network. Each of these devices require their own unique configuration, and any change can cause major network disruptions. Software applications that monitor these configurations are available and recommended to ensure that network configurations have not changed. They can also back up configurations and continually check and revert any change to its original state, which helps maintain a secure and stable network. Some best practices for configuration management include regularly auditing the network, ensuring the changes are documented, and that every device has the correct version of its configuration files. This ensures the network configuration is consistent and the devices are secure. So those are a few aspects of network monitoring. So in this video, we're going to examine one of the concepts in disaster recovery, the Recovery Point Objective, or RPO. When backing up an organization's data in case something disastrous like a fire happens, one must decide how up-to-date the backup has to be. That is, how much data, representing how much time, can the organization tolerate losing? This decision is critical because it will determine how often the backups will be taken. It will also determine the choice of technologies, strategies, and even the location of the backup to ensure minimal data loss during an outage. There are a number of factors that come into play when determining an appropriate RPO. How critical the data is will help determine the RPO. Some institutions, like financial, would not be able to tolerate any loss of data. Also, how fast the data changes will be a factor. Some types of data, like engineering plans, change little after they've been created, whereas sales data for a large vendor would be constantly changing. Also, the impact on the business must be considered. Downtime translates into reliability, and extended downtimes means the loss of confidence in the organization. When evaluating acceptable data loss, the organization must also consider costs. Lower RPO values means higher costs associated with more frequent backups. Cost isn't the only factor. The organization's risk tolerance and overall goals must also be considered, and balance struck between the two. So, as part of the backup recovery plan, backup frequency will affect the cost because it requires more storage, and depending on the backup strategy, backup resources. The more frequent the backup, the lower the RPO. Different backup and recovery solutions will incur differing costs. A local backup strategy could involve the tape backup device and backup tapes. Increasing backup frequency will result in the cost of the extra tapes, but also the time personnel will spend performing the backup. Cloud-based solutions can be automatic, but may also be more costly per gigabyte. As the organization's needs change, so will the RPO. Monitoring and adjusting the RPO to align with these changes will ensure that gaps aren't left in the backup and recovery strategy. Recovery Time Objective, or RTO, is the maximum amount of time that an organization can tolerate from the start of a loss of service or a business function to the time that service or function is fully back online. But when we say tolerate, we mean before the company starts to suffer significant negative impacts. This will include time when the service or business function stops working, the time it takes to identify the issue, begin the restoration, then begin to bring the service back online, to having it finally available to users. RTO is central to planning for the tasks that will have to be performed to ensure business continuity. Correctly estimating the RTO allows disaster recovery planners to determine which strategies are required to restore operations. It will also help determine the resources required to achieve the recovery goals. Different organizations will require restoration of services over different timelines. In the example of healthcare, lives are depending on many services being available 24/7 and can tolerate very little downtime. Operations like manufacturing may have sufficiently completed inventory to be able to tolerate longer wait times, like hours or even days. For example, a factory manufacturing newsprint may have sufficient paper created to fulfill orders for the next several weeks. So, some factors affecting the RTO include determining the effect being offline will have on business through a business impact analysis. This will normally include how the business operation will be affected. Customer service should also be considered. Does being down longer have a larger effect on customer satisfaction and company reputation? And of course, the organization will lose revenue during the outage. IT outages can affect other business aspects. For example, in an industrial setting, bringing the IT infrastructure online may only be part of bringing manufacturing equipment back to operating status. In some industrial settings, it may take days to bring boilers up to operating temperature, or machinery that has been shut for a period of time may need maintenance before it can be restarted. Putting a system back online requires the correct personnel with the correct equipment. Bringing together the required expertise and equipment takes time, and this also must be accounted for in determining the overall RTO. When bringing a system back to operating status, some components will be critical to the startup, while others may be delayed or may be optional and enabled after the operation is restored. These components need to be identified, and a critical path to re-enabling business operations should be created. Different business departments or stakeholders may have different timelines for the restoration of services. Some may tolerate longer wait times than others, and this information can help determine the order in which services should be restored. Estimating recovery time is just that, an estimate. This component of the recovery process should be tested to determine the actual times for restoration. These can provide a more accurate representation of RTO. Continual testing can keep the RTO in line with changing business needs and changes in infrastructure. As previously described, SNMP, or Simple Network Management Protocol, can be used to collect information from networking devices and can also be used to configure them. This protocol can prove valuable in reducing the mean time to repair, or MTTR. The mean time to repair is the average amount of time it takes to resolve the failure of a network component or system. This number can indicate how well the organization responds to issues and can reflect the company's ability to keep the network in operating order. So by lowering the MTTR, the organization can demonstrate a higher reliability to their customer base. A failure in a network increases operational costs through lost productivity. Lower MTTR numbers translate into reduced costs. A number of factors will affect the MTTR. Things like how complex the issue is, the skill level of the individuals attempting the repair, and parts availability will affect how long it takes to bring a system back online. Using SNMP, the network team can be more proactive in identifying potential issues before a failure. This monitoring could indicate a need for preventative maintenance, and using the control commands can automate configuring systems. If system failure can be prevented or anticipated, then replacement parts or systems can be pre-ordered, or preparations for system upgrades can be scheduled, reducing or even eliminating downtime. So, regular preventative maintenance, like reconfiguring network devices for improved performance and reliability, or adding extra capacity, can avoid bottlenecks in the network and prevent downtime. There are numerous automated applications that can monitor network configurations and traffic patterns and can, through the use of automated alerts, notify network personnel of anomalies before network failures, or immediately if a failure occurs. Software applications can also be used to keep IT teams updated on network issues. Coordination between teams can reduce delays in response and coordinate efforts, reducing overall MTTR. Business continuity is the ability of an organization to be always available to its customers. Disruptions in services reduces business stability, which reduces the customer's trust. High MTTR values can indicate that an organization may have extended periods of downtime. This can also negatively affect company revenue. High MTTR levels indicate extended repair times, which cost money through increased labor costs, operational costs, and even penalties from service level agreements not being met. A service level agreement, or SLA, is an agreed upon set of terms for services provided by one organization to another. Many of these agreements stipulate how much downtime will be tolerated before penalties apply. The MTTR is often included in these agreements as a measure of stability and availability. The agreement may also stipulate the MTTR value as an indicator of reliability for the customer. In this video, we'll explore mean time between failures, or MTBF. Mean time between failures is the average time that it takes for a system or component to fail. This value is meant to represent the average number of failures over time. It's used to indicate the reliability of a component. Now, an individual component or system may fail earlier than the time indicated in the MTBF, or may not fail for a long time after the MTBF. So it's not meant to indicate a guaranteed lifetime of a product, but an average lifetime over many products. MTBF values are used for planning and maintenance in networking systems. They can help determine preventative maintenance cycles, as well as plan intervals for equipment replacement or upgrades. High MTBF values indicate more reliability over longer periods of time. Some factors affecting the MTBF values include the operating environment, the quality of materials, and ongoing preventative maintenance. Let's take preventative maintenance as an example. Computer systems, for example, tend to have shorter lifetimes in higher temperature environments. Dust can affect the heat retained by a system. This dust should be removed from the system on a regular basis through a preventative maintenance schedule. The amount of dust in the environment will determine how often the system should be cleaned. So, how is the MTBF calculated? The mean time between failures is calculated by taking the total time the system has been operating and dividing it by the number of failures that have occurred during that time. The less failures, the larger the number, indicating a higher reliability. So let's say a system has been running for 1,000 hours and has failed twice in that time. 1,000 divided by 2 is 500. So the mean time between failures is 500 hours. If the system has failed 5 times in that time, then the MTBF would only be 100 hours, indicating a less reliable system. Now, using a calculation as simple as this doesn't account for things like when those failures occur. If a system is getting close to the end of its useful life, it's likely to suffer more failures than when it was newer. External factors can also cause failures. A fire or a power surge can both cause a failure, but don't indicate the reliability of the device itself. Both MTBF and MTTR can have an effect on the reliability and stability of an organization's network. But while the MTBF measures the likelihood that a system will fail, the MTTR is a measure of the average time it takes to bring a system back online after a failure. If one has an indication of when the system is likely to fail, then a maintenance cycle can be scheduled before the failure is estimated to occur. This can help an organization avoid failure by taking preventative measures. Magnetic disk drives, for example, typically have MTBF figures. Disk mirroring can help mitigate this issue by keeping a duplicate of the data on 2 drives.
Hey, Kevin, I'm checking your time right now just to make sure.
Drive can be used to populate
Did you?
a new replacement drive while the system keeps running. The likelihood of both drives failing
Forgot to clock out for lunch.
is much less than
Oh no, man.
Don't worry, let me fix it real quick. Hold on one second.
You got it?
Yeah, I'm gonna clock you out, but I need you to clock back in.
All right.
Hold on one second. And watch your clock in time because you lost an hour this morning for some reason.
Well, that's weird.
Did you?
Oh yeah, I got clocked in
class. Okay, gotcha. All right. In that case, I gotta leave it alone.
No worries.
Hold on. All right, hold on one second. Let me clock you out. Then you can clock in, and I'll adjust that though for you because I know you were here after lunch.
Where an organization can go to continue to operate in case the current location for the
That
business
one I could
is no longer
take care of.
There could have been a fire or a natural disaster like a hurricane or flood. The whole operation needs to be relocated to a different physical location. So let's say a disaster occurred and the business.
All right, go ahead and clock in for me, sir, and I will adjust.
If there were no backup location
Refresh
and
this
no backup
page.
of the important
Clock me
information
in.
the company needs, then the business
All right, says we're good.
exist. Having an alternate location with the tools required
Let me
to
fix
continue
that.
operating could mean the organization would be up and running in a matter of hours. Now, there are different types of disaster recovery sites. A cold site would be basically a building, a place where the company.
Okay, that one I can fix. You're good.
All right. I appreciate you, James.
All right, no problem.
Be set up. The data for the organization would exist in a backup, but would have to be copied to the new equipment once it was installed, configured, and running. Among the types of sites, this would be the cheapest alternative, but as you can imagine, would take the longest to set up. Depending on the type of organization, the days or weeks it would take to bring the site to operational status could be unacceptable. So, the warm site is closer to operational because the network hardware is in place and it is either partially or fully configured with the necessary setup. If a disaster occurred, then those systems could be powered up and any final configuration completed. Then, the company data could be restored and testing could be completed. Potentially, the site could be ready in a number of hours or perhaps days. The cost would be
T1
higher than
says, was it always a clock in and out model? Yes, it's always been there since day one.
Now, the hot site is a fully configured.
Clock in the morning, clock out for lunch, clock in from lunch, clock out at end of class.
Now, you can imagine the cost of having such a site would be high.
So with this program, it's kind of tricky, just to let y'all know. Like the one he just did, like he forgot to clock in after lunch. But because he was here and I saw him and he never clocked in, I can kind of help you in that aspect because I saw you here, so I could, when you clock in, you're there, right? I can account for your hours. If you wake up late or come in late and you do that punch and it says you got here 2 hours later, but you were never in Zoom, like, I ain't nothing I could do. Yeah, that's kind of like, and if I do that too much, my leadership would be like, why are you changing your times? Yep. But like this scenario, I can work with a scenario like that.
Would be a lot less than paying for the rent, personnel, equipment, electricity, and ongoing maintenance of a hot site. Depending on the equipment required and the cost of copying data from the original site to the backup site, the cost differences between the cold, the warm, and the hot sites could be several orders of magnitude. You could be talking about differences of thousands of dollars to potentially millions. The recovery time objectives need to be aligned with the organization's goals. Different aspects of the company's operations may have different tolerance levels for recovery time. A mix of cold or hot sites may be the best solution to not only maintain continuity, but also to do it in the most cost-effective manner. Where the backup site is to be located is another important consideration. Depending on the location, a disaster like a hurricane could affect a very large area. The likelihood of such an occurrence is also dependent on location. Southern climates are much more likely to face this kind of calamity. However, northern climates...
Yeah, they actually watch them, just to let you know.
Which can also affect...
They'll go back, so like if they have to do... I'm totally transparent, so I don't care. If they needed to do a review on me to make sure, let's say I'm talking to you guys professionally, I'm making sure I'm passing the information, right? Or let's say, Mike, can I use you as an example? Say like your time ain't adding up. And then they're looking, they're like, well, I see him here. He's here. How come the instructor is not adding his time in? So then they'll get on me like, you need to make sure their punches are there because it's important for Michael to pass his courses. Like they'll get on me. Or they'll do the reverse. Let's say you say, I was there. They'll go back to Zoom. And if I'm correcting time, they'll be like, we went back and looked at the recordings. Michael was not there. Why did you give him time when he was not in class? Yep, so it can work the other way too. Yep. And the VA uses it as auditing to make sure that you are a live student in class on camera. Yeah, so it's so many different aspects to why they record it, but it's more of a quality assurance feature and safety. You know what I'm saying?
Organizations must be available all the time and can't tolerate any sort of interruption. Public health facilities, airports, and banks are good examples of services that need to be available at all times.
So it's a safety feature too to make sure everything's cool.
Are two approaches to a highly available network infrastructure. An active example could be a number of computer servers all running to maintain an application, such as email. All the computers are operational and maintaining and managing incoming and outgoing emails. All servers share the load, and if one fails, then the rest keep running and share the load of the failed server. In this model, there is no interruption of service and no time waiting for the load to be picked up by the other machines. The active-passive model is similar, but one of the servers stands by and doesn't handle any processing. Its running hours...
Mr. C put something in the chat for everybody. Oh, Mr. T did. Okay, here it is. The screwdriver 12. Oh, okay. That's Amazon link. I'm gonna say that just in case I have a student that wants to. I'm gonna say that in my bookmarks. That's a pretty neat toolkit. You ordered it last week, Lane?
The active passive model does have a small switch.
Yeah, that's a pretty only for $25. What?
Take the load of the failed unit and
$25? You can't go wrong.
Now, looking at this in terms of advantages and disadvantages,
You should always have your own toolkit.
The active model provides higher redundancy due to it not having any failover time and operations continue.
Okay, Brian said that's the one he got to.
Another advantage is that all servers are in use and therefore no processing power
If you got time this weekend and got a little bit of cash to waste, surf your local Savers or Goodwill or Salvation Army. Look for a busted computer that they'll let go for like $10 or $7. Bring that to the house, rip it apart. See if you get it to work.
Active configurations are more complex.
That's the best thing you can do if you want a hands-on one. Start pulling that thing apart and try to put it back together. Look up the specs. You know what I'm saying? No matter how old it is. Go to the manufacturer website. Figure out what type of motherboard it is. What sound card is on it, right? Troubleshoot it.
Which approach to take.
I think there wasn't many options where that much versatility and various, yeah. Leah, you got the Airman's Attic on base. You on Air Force Base or Army base? Army?
Demanding that the active model be used.
Oh, it's a co-op. Air Force. So you should have a Airman's Attic. Yeah, you might go over there and find a computer, just pick it up and walk out with it.
Again, active setups are more complex and therefore require staff with higher levels of expertise. Larger networks typically involve
all right. With that being said, it is 6 o'clock. Don't forget to clock out. Y'all have a magnificent weekend. If you have any questions, please let me know before we get out of here for the long weekend. Well, it's only 2 days, but it feels like it's going to be long.
Yeah. Yeah.
My mind is gone. Michael's like, we'll re-engage on Monday.
Yeah.
All right. But if you need something, call me. I have my business number that forwards to my email.